Good morning, everybody. Welcome to the second day of this AGB conference. Given that there are no LOC announcements, we can start immediately with the talks. And the first one will be given by Michele Trabucci on the pulsations and variability of AGB stars. So, Michele, the floor is yours.
No.
Sì, non so come.
Okay, thank you. While the slides are set up, I'll take the time to express my gratitude to the Scientific Organizing Committee for inviting me, and most importantly, for bringing us all together once again. It really feels great being here. So, I have a confession to make. As you can see, the final part of the title shrinked because probably I won't have time to go into that, but I'll try. Instead, I'll tell you about pulsation and variability. Basically, this will be about what I have learned on these topics and what I'd like to share with you. Pulsation and variability are two distinct things we know, although they are sometimes discussed interchangeably, because pulsation results in variability of the periodic type, but variability then, of course, doesn't necessarily come from pulsation. So just to be clear, by pulsation, I will mean radial oscillations due to acoustic pressure waves, not because they are the only one in AGB stars, but because even though the title of the conference is 3D winds, I'm still doing 1D stuff. And variability, I will mean periodic variability, of course. Once again, not because it's the only one in AGB stars, but in this case, I feel with confidence saying it's the most important one, at least on dynamical timescales. These slides it has the flavor of theory versus observation. That's because I kind of want to go down that path. We observe variability. We use the theory of stellar pulsation to bridge it to information about stellar interiors and stellar properties. And the basic connection comes from the period. Pulsation has a period. We observe a period. In photometry, in radial velocity, they should be the same. So we make this assumption, actually, and we can apply our theory to infer properties of the star. So there is a one-to-one connection that actually kind of becomes more blurred when we recognize the AGB stars are more complex than that. They are the site of multiple pulsation modes coexisting, resulting in observed multi-periodicity, which in a way can be useful because we can use, for instance, period ratios of different modes to get information about the density stratification of the envelope. But it makes things more complex. For instance, we're used to having a regularly sampled time series with seasonal gaps. Periodic signals are not necessarily monochromatic. They can have harmonic components. It gets much more difficult to disentangle them. So what we're used to do is we say, oh, look, there is a pulsation mode that is much stronger than the other. There is an observed period that is much stronger than the other. We call them the dominant mode or the primary period. And we implicitly do the assumption that that primary period is representative of the overall pulsational behavior of the star. It's convenient because we get to plot one single period per star in the period luminosity diagram. And of course, it's wrong, as we will see. It comes down to the growth rate, of course. So when we cast the physical problem of stellar pulsation into the mathematical language of an eigenvalue problem, so the Sturm-Liouville problem, every pulsation mode is characterized by a complex frequency, real and imaginary part, a period of oscillation, a time scale for the exponential amplification or decay of the oscillation. And there is an observational counterpart, not really a one-to-one correlation, but clear a connection to the amplitude of variability. And in the end, it depends on the existence of a driving mechanism operating in a star that keeps the oscillation alive, allowing us a chance to detect any variability at all, find the dominant period, primary period, and apply this kind of scheme. which breaks down as soon as there is another form of variability, periodic, in particular, but not necessarily binarity. So this kind of layering complexity, I believe, reflects a little bit what in the decade we learned from LPVs, pulsating AGB stars, the progress in our capability to interpret these stars, and in particular the period luminosity diagram. So this is an example of, well, I wasn't there, but some of you, I guess, remember that. It's a pioneering study by Fist and collaborator, where a very boost happened in the study of the period luminosity relations of Miras through infrared astronomy. This is in the LMC, if I remember correctly. In the 1990s, starting, I believe, with a paper by Wood and Sebo 1996, it was realized that there are additional period luminosity relations, a second relation in the LMC populated by semi-regular variables, and later confirmed in 98 by Bedding and Zylstra in the solar neighborhood with the Palco spiral axis. Then large-scale ground-based microlensing surveys arrived, changed the game. Wood and collaborators 1999, then Wood 2000, displayed with much data the existence of multiple period luminosity relations, and the current picture is provided basically by the optical gravitational lensing experiment, Ogle 3 in particular. So layering complexity associated with the realization that there are extra sequences, likely due to extra pulsation modes, but also a layering in the complexity of the classifications. We have now Miras, same regular variables, Ogle small amplitude red giants. So it's very tempting to assume there is one-to-one correspondence between period luminosity sequences or relations in the diagram and pulsation modes. And operating under this hypothesis, Wood in 2015 did this exceptional piece of interpretational work where he compared in the diagram with two mass infrared photometry against Ogle periods detected in the optical. This is the LMC. He compared with models, and he came to the conclusions, I quote, that fitting pulsation models to the period ratios in multimode pulsators shows that the sequences C, C prime, B, and A prime correspond to pulsations in radial order 1 to 5 respectively, which basically means from the fundamental to the photovertone mode, 5 sequences, 5 modes. This was a great work. The missing piece was a dense sampling of the space of stellar parameters with models. Peter didn't really use a large number of models. So he set me up to do it when I was working in the Stalky project of Paolo Marigo. So I was a PhD student computing a very large grid of models for the purpose of building a grid and applying an interpolation grid-based approach to attach variability information to evolutionary tracks and synthetic stellar population models. This is a very powerful approach, and it gave results. For instance, when applied to evolutionary tracks, it gives us a chance of peer into the details of the evolutionary path of these stars in the PL diagram. And we kind of confirm something that was already basically understood. Take an AGB stars in a relatively early stage of its evolution, relatively faint, not too cool, relatively compact. It typically pulsates in a set of modes, mainly overtones, possibly the fundamental, identified by this kind of pie chart, where typically an overtone mode such as the second overtone dominant. So the composition of these oscillations results in a light curve that is not very regular, typically of an Ozark variable. Then the star evolves, becomes brighter, larger, cooler. What happens to the pulsation modes is that the highest overtone tend to disappear. Dominant mode switches toward lower radial orders. The light curves tend to become a little bit more regular. It's still not very regular. Eventually, you're left with a couple of modes. This is probably a semi-regular variable pulsating biperiodically in the fundamental and first overtone mode. And then you're left with the fundamental mode only and a Mara variable. So there is also an evolutionary sequence of a kind in terms of variability types. Now, I will show you that there is a physical reason for the transition from other semi-regular variables. Unpopular opinions, the transition between semi-regulars and Myers is arbitrary, up to debate. But this is something that we worked on with Nami Molavi and Thomas Lepzelter, and it's something that was already known. We systematically analyzed data in the LMC and found that there are semi-regular variables that are very similar to minor, so not really a reason to separate them. So if we apply this method to synthetic stellar population models resolved stellar populations, we can simulate a PL diagram. This was shown already yesterday by Yoshi. And I invite you to note a few things. First of all, look at these short period sequences. There is a one-to-one correspondence between observed primary periods on sequences A and A prime and simulated third overtone and second overtone mode. Not fourth and third, as Peter said. We actually simulated the third overtone. It's not there. It doesn't correspond to any sequence. Second point, there is no one-to-one correspondence between B and C prime and the mode. They are both described by the distribution of dominant first overtone mode periods. Then there is obviously something off with the fundamental mode. It's systematically overestimated, and we do not have any sequence D, because most likely, but it's debated, it's not due to pulsation, at least not the kind of these ones. So let me focus on this item first. So why are my model wrong? I asked myself as a PhD student, let's see what the other people do. So I computed fundamental mode periods and first overtone periods from prescription in the literature for the same simulated population. And well, luckily or not, they are all wrong, so to speak. They all overestimate the location of the Myers sequence, basically. So they all have in common that they're based on linear pulsation models. Bottom line, do not use prescription from linear pulsation models to predict the fundamental mode periods, at least not in large amplitude pulsators. So this was originally noticed probably in a work in 1996 by Yari and Tuchman, who found out that if you let evolve a model of a Myra, it readjusts on a thermal timescale due to nonlinear effects. It changes the envelope structure on average. They computed 5 models, I think. So we said, let's compute more models. And the result is this. So this is period as a function of stellar radius, so basically increasing along the AGB. The curves are linear predictions. The symbols are nonlinear predictions. After a certain radius, the linear prediction systematically overestimates the results from nonlinear models that are clearly more realistic. And this is due to the fact that if you let the star evolve, it will tend to become slightly more compact on average in the pulsating layers. This is the density stratification, basically. So comparing the curve, which is a hydrostatic structure, with the dots that sample the average hydrodynamic structure, it's more compact, denser. There is a period mean density relation. Denser means shorter period, which is good. It points in the direction of the observation. If we compare data with linear models, bad agreement. Nonlinear predictions, much better agreement. And luckily, this stands the test of 3D models. So this is from a paper by Ahmad Freitag and Höfner, very recent, where they compare the results, that's red line, of the nonlinear 1D models I computed with their results, and there is, I would say, nice agreement. So this is useful because, for instance, we can study the period-age relation of fundamental pulsators based on models. We did that in 2022 with Nami Molavi. There is nice agreement with the observed periods of LPVs of known age that are in star clusters. So, problem solved. Let's go back to the other issue. So, first of all, summarizing, A prime is due to the third overtone, A to the second overtone, both B and C prime to the first overtone. C is the fundamental mode sequence of Myers, and this mode identification was confirmed based on astroseismic study by you and collaborators 2020. But still, why do we observe 2 sequences and predict 1? Well, as I mentioned, the primary period plays a role. We see sequences appear because we select the primary period in a star. If the nature of the primary period changes, for instance, because there is a mode switch, we see another sequence. What if the nature of the primary period changes because some other kind of variability appears? So if you have guessed long secondary periods, good. It seems that as a star pulsates dominantly in the first Overton mode, at a certain stage, a strong long secondary period appears, so we tag it as primary. And we said, well, good, that's representative of the overall pulsational behavior of the star. Wrong, and we are completely ignoring information about pulsation. So the result is an observational bias. A few words about LSPs, because I think we will hear more about them later. They are unlikely to be due to oscillations, but that's debated. They seem to be due to binarity, that's debated. My take is some due to pulsation, some due to binarity, diplomatic answer inspired by the venue. So recently, the binary scenario was repopularized, among others by Służyński 2021, who detected secondary minima in mid-infrared curves along secondary periods and attributed them to secondary eclipses. So the scenario is you have an AGB star, it loses mass, there is a substellar companion that gathered ejected dust, forms a dust cloud, the dust cloud eclipses the star once per period, once per orbit, and if the cloud goes back of the star, the thermal emission in the mid-infrared from the dust cloud is eclipsed from the star. So secondary eclipses. There was a paper by Goldberg and collaborators in 2024. They used Gaia radial velocity time series to depict a different scenario. According to them, the star is surrounded by a dust shell, and the passage of the companion pierces a hole through the dust shell, so to speak, and reveals the star once per orbit. It's interesting because there is a lot of research on this. Very recent paper by the same collaborators, they actually did a 3D simulation and shown that this may be compatible with the formation of density wake due to the passage of the companion on an eccentric orbit in and out from the dust-free zone. So there's a lot of work on this, but I'm interested in this because there is a clear connection between observed long secondary periods with a strong signature on sequence T and pulsation periods that we would otherwise see between these two sequences B and B prime. So we did this exercise with Peter Wood in 2017. Let's first remove all long secondary periods, re-identify primary periods. We are now sure that they are all due to pulsation. And then we find that basically these two sequences form kind of a single one. So we have 4 more than 4 sequences, back to something comfortable. So what's interesting is that as this kind of extra phenomenon arises, we have a transition. The star moves from being an OSUG to a semi-regular as the LSFP appears. On average, this is not something that happens all the time, but looking at many stars, there seems to be a trend there. Additionally, as we transition from between these two sequences, there is a step up in mass loss rate, as we noticed with Ian McDonald in 2019. So it's not a strong mass loss transition, but from low levels to moderate mass loss rates. And then again, we have a transition from and also to a semi-regular variable. What's the nature of this oscillation? Last year with Giada Pastorelli, we did a test. We computed nonlinear models of the kind I've shown earlier for combinations of stellar parameters that are representative of OSUG stars. And they do not pulsate. They are intrinsically stable. But we do observe them to vary, to oscillate. Whereas if we compute these models for semi-regulars, they do pulsate. So the take on this is semi-regulars are self-excited pulsators, whereas OSUGs are not. So by exclusion, it's very likely that they are stochastically driven oscillators, much like their solar-like red giant branch cousins. So there is a lot of evolution that we can now see in the p-luminosity diagram, we can provide an extended interpretation. Summarizing, we have intrinsically stable also access stochastically driven by some turbulent convection-related process that should probably be visible, as we have seen yesterday from Bernd Freitag in 3D models. They don't really lose a lot of mass. They are dominated by overtone pulsation. They become semi-regulars, pulsating in the fundamental and or first overtone mode, self-excitedly. And that's interesting because one would be tempted to say that coherent pulsation, as opposed to stochastically driven, enables a moderate level of mass loss at an early stage. So there is an effect of coherent self-excited pulsation in initiating the mass loss, clearly detectable in the pattern of period luminosity relations. And this can be detected as, well, this enables the detection of a potential secondary companion through the interaction with the newly ejected dust in the circumstellar medium. Things that happen later are more complicated. The star becomes a mirror, pulsating only in a fundamental mode, self-excitedly, but then the mass loss becomes really large, and it seems that long secondary periods disappear, which is also interesting by itself. Now, how can Gaia help with this? Well, pointing out that, in my opinion, for studying long period variables, we still need to rely on something like OGLE, but we will soon, well, relatively soon have LSST, which will be comparable in level. Gaia can help a lot because Gaia is providing us with homogeneous sets of radial velocity time series for these objects. Okay. So we can actually use them to understand simultaneously the pulsation and potentially the effect of binarity. And Gaia is also giving us a bulk way to more or less distinguish between oxygen-rich and carbon-rich stars through low-resolution spectra. This is a method that was already implemented in the Gaia catalog of using the systematically larger distance between maxima in the low-resolution spectrum, tracing the width of the molecular absorption features, distinguishing between oxygen-rich and carbon-rich sources. And will be applied for DR4, that we will cover a much longer temporal baseline, giving us this kind of information both about variability and chemical type. Then, of course, there is a lot to expect from LSST. So my take here is there are opportunities to use this now that we see there is an increasing complexity in the pure luminosity diagram that depends on the presence of a lot of hidden information that we can extract. This is, I'll just mention, this is based off a project that I'm carrying out at the University of Padova, where we want to try to find a way to use observations in the optical of long secondary periods to put some constraints on the mass loss rates from the stars under the hypothesis, still debated, that they are due to some form of binarity. So I'll just leave my conclusions here quickly. There are layers of complexity. I'll say it many times about the pulsation and variability of AGB stars to distinct things. And we can interpret it with a very powerful approach that is grid-based synthetic population models. So looking at the very details of this kind of patterns, simulating them, it allows us to detect issues in modeling, biases in observations, and it's really necessary to understand and interpret massive data sets that we're expecting. And it provides an opportunity to understand deeper connections between different types of variability, pulsation, the mass loss, the binarity, that it's reasonably the time to try and exploit. Thank you very much.
Thank you, Michele. You're very well in time. So we have Still 7 minutes for questions. So, who would like to take the floor?
Hi, Yoshio Mori from Monash in Australia. Thanks for the really great talk. On the topic of whether Myras have long secondary periods or not, could it just be a matter we don't have long enough time series to accurately see if they do?
Well, yes. I mean, I will not state 100% that Myras are single periodic stars, but there seems to be quite some evidence of that, both from observations and from modeling. I would also not state with 100% certainty that they do not have long secondary periods. Again, it seems to be a trend in the data. But this is a very important point. We need long time series for studying these objects. That's why OGLE is very good, and I hope OGLE 4 for the LMC LPVs will arrive at some time. This is what this is why GAIS is useful, although it clearly has a different kind of sampling and cadence of OGLE, and this is why LSST will be very enormously useful to this kind of study.
Other questions from the room? Michele, at least I have one or two for you. You were saying at some point that if the LSP appears, others move towards semi-regular variables. I have to admit that I did not understand very well.
So there is no logical connection in that statement. It's an observation of the fact that these things are roughly observed to happen, so to speak, at the same time. So there is a coincidence. The logical connection is in the interpretation that the transition from an Ozark variable to a semi-regular variable, which will link to the onset of self-excited pulsation on the AGB, has something to do with the appearance of long secondary periods. And the take is coherent pulsation is better than stochastic oscillations into driving a low-level moderate mass loss, giving the subcellular companion something to play with to show a long secondary period, so to speak. It's very qualitative, okay? But it makes sense. So I hope we can get a clarify on this.
We'll try. Does anyone follow whether there are questions online? Okay, I first go to Theo.
Thank you. So thanks for the very nice talk, Theo Koeri, Chalmers. Can you explain so I have heard you several times present this non-linear character of the fundamental mode. Can you explain for someone like me that doesn't really understand what that means?
Okay, I'll try. We usually employ linear models because they are fast. Okay, it's numerical approach, it's really fast. On my laptop, I could compute the periods for a stellar envelope in 0.1 second for a star. For a nonlinear computation takes 15 minutes. It's not much, but when you have a large grid, it makes a difference. The higher efficiency of linear models come from the assumption you make. You assume that the pulsation, the variation, is infinitely small in amplitude. So the result is that you have an underlying hydrostatic structure that has tiny oscillations, but the tiny oscillations do not affect the structure itself, okay? Nonlinear models account for the possibility that as the star oscillates, what's underneath that determines your period, that determines what modes are excited, can also be affected by the pulsation itself, okay? As long as the amplitude is small in these stars, the linear approximation is fine. But Myras are not small amplitude oscillators by the very definition, okay? And we can see that in nonlinear models. So as the model starts pulsating, it changes what's underneath, changes its average density stratification. The envelope tends to be a little bit more compact, so it affects in return the period itself. So it converges to a kind of hydrodynamic equilibrium at a certain point, but the average, time average structure is not the same as one in hydrostatic equilibrium. I hope this was useful. Thank you.
I'm looking around. Angela.
Angela Speck, University of Texas in San Antonio. So one of the things that, okay, full disclosure, I'm a DOST person. One of the things that is different between semi-regulars and Miras is there is a difference in the DOST. And so I just want to know whether you can speculate on why there would be a difference in the DOST, or what would be different in the DOST forming region as a star evolves, or whatever it does to change its pulsation going from semi-regular to Mira.
So the question is how the pulsation behavior shapes the dust properties of the star. Full disclosure, I don't really know, but I can speculate. For reasons similar to what I just said, the average density structure of the atmosphere, standard atmosphere where dust form, changes as a result of pulsation. So at the zero level of approximation, when you get a different density structure with on average higher density at any given distance compared to an hydrostatic non-pulsation model, it's supposed to be easier to form dust. But I'm looking at the dust people around to confirm this. So the basic idea, as far as I understand, is you change the density and thermal stratification of the outer layers, you enable that kind of dust mineralogy that results in drastically different properties between semi-regulars and Miras. Then again, my unpopular opinion is there is not really a drastic cut between semi-regulars and Miras, okay? Clearly, the largest amplitude ones are Miras, the smallest amplitude ones are not. The things in between are very blurred.
Thanks, Michele. Given the time, we have to close here. Thanks a lot for the excellent talk. And we now move to an online talk given by Beth. Courtney, Beth, can you hear me?
Yes, I can hear. Can everyone hear me okay?
Perfect. Beth, I will, you have a 12 minutes talk. I will interrupt you after 7 minutes so that you know that you still have 5 minutes left. Is that fine to you?
Yep, no worries.
Yeah?
Everyone
Okay.
can see my screen okay?
Yes, it's perfect. Thanks.
Perfect.
Beth, the floor is yours.
All right, thanks everyone for having me. So the title of my talk is No Companion Needed. Admittedly, this is a provocative title, I guess, to say that companions aren't always needed to explain long secondary periods. So I hope I can convince you of that a little bit today. So to start with, I was going to introduce long secondary periods talking about the period luminosity diagram, but I think Mikhail did an excellent job of introducing this. But the main thing to take away, there's a bunch of sequences and they correspond to physical mechanisms that cause these period luminosity relations. Sequence D, which has the longest periods, are long secondary period variables. And the thing is, these affect a huge population of stars, of up to 30% of RGB and AGB stars. So it's really a galactic shaping population of stars that it's still uncertain the actual mechanism that causes this. So, I mean, this has been studied for many decades. So we're starting to get a bit of a better idea of this. In particular, there's two kind of leading hypotheses of what's causing sequence D. So I'll provide a brief summary. The first one is this oscillatory convective mode hypothesis. So this is that idea that there's some really coherent thermal profile in the outer convective layers of the star. And this was really put on solid theoretical grounds by Seo in 2015, and he showed that these really arise in non-adiabatic conditions where the modes become overstable and self-excited. And the key thing that he noted was that when you consider the dipole mode for this oscillatory convective mode, it follows the period luminosity sequence and falls almost exactly on the sequence D. So this has been tested with observational data, looking at multi-band photometry, and it seems to fit a lot of the profiles there. The other hypothesis, which Mikhail also talked about, was this dusty binary hypothesis. So this really is predicting a low mass companion where it has a dusty envelope around it, and that leads to the observed variability that we see in the light curves. This has very much been popularized also by Szynski's recent finding of these harmonics in the light curves, particularly in the infrared, where we see these secondary minima appear. So this is really consistent with the binary scenario where we have the secondary eclipse as the dusty companion moves behind the star. Lean has also done a lot of modeling. I think she's going to present this later about eccentric orbits and then time and dust, and how that can also be used to predict the infrared behavior and especially photometric phase lags that we see. So these two theories are, there's a lot of evidence for them in the literature. They're debated, but quite often they're really looking for a single mechanism that's causing this. And I'm with the same diplomatic opinion as Mikhail. I think that it's quite likely that it's a little bit of both. So we could have a dual mechanism that's actually causing this. So, I mean, a lot of the observational constraints on long secondary periods are really from indirect methods like photometry and radial velocity surveys. So, optical interferometry is a really great way to break the degeneracy between these two theories. This is especially evident in the wavelength dependence of the closure phase. So essentially, if you do basic Monte Carlo simulations of a oscillatory convective dipole mode and the dusty companion, what you can see is that with the dipole mode, you really get the asymmetry is really confined to the photosphere of the star. So you really get significant closure phases as you observe towards shorter wavelengths. On the other hand, if you look at the dusty binary scenario, the closure phase really increases typically with longer wavelengths, with typical, orientations and, companion sizes that you would expect. And with current facilities, it's a really, great opportunity with VLTI, Chara, and ALMA, of course, to do these types of studies, and in particular with upgrades that are coming. So this is what I really wanted to set out to do, is to look at a long secondary period with interferometry. So I looked at a nearby variable, RT-PAV. It has a very strong 1 magnitude LSP in the visible with a 757-day period. So we observed this for 30 hours on the VLTI with 3 instruments, Pioneer, Gravity, and Matisse, covering 1.5 to 5 micron. And the key thing was that we observed this at a LSP phase where, under the binary hypothesis, the companion should really be out to the side of the star. So this is really where you have maximum contrast between the two theories. So in terms of the results, so first, after I put in this proposal, Guy released the DR3 astrometric solutions, which classified RT-PAV as a single star. So this doesn't necessarily mean that RT-PAV is a single star, but any companion there that is causing the LSP, we can draw pretty reasonable constraints on how big it could be. And it's unlikely that it's going to be bigger than about 1/10 of a solar mass. Similarly, we can look at Kepler's law and be like, okay, if the LSP is caused by a binary, then what are viable orbits or the maximum angular separation that we can expect? And even considering eccentric orbits, it's hard to say that we get separations bigger than roughly 5 or 6 milliarcsecond from the primary. Now, with these results, there was already a bit of tension with the binary hypothesis, because if you consider the photometric variation in the visible light curve, which is roughly 1 magnitude, you can draw a reasonable lower bound on what the size of any oculating object would be around that. So what the minimum radius is that could, create these photometric variations. And then if you compare that to the Gaia constraint and calculate the Roche globe radius, so the area where dust is really gravitationally bound to the companion, you find that this radius is significantly smaller by various factors than the lower bound based on the photometric variability. So this already starts to create a little bit of tension for the binary scenario. Following up with the interferometric data, when we look at the wavelength dependence of the closure phase, we find that there's really no significant non-zero closure phases towards longer wavelengths, which is what we'd really expect in the case of a binary scenario where we have up to 1 magnitude variability in the visible. Instead, we see significant non-zero closure phases at shorter wavelengths, at spatial scales where we start to resolve the photosphere of the star. So this becomes a little bit more consistent with the oscillatory convective dipole model. So in terms of parametric modeling, we fitted a bunch of baseline models to this, including the oscillatory convective dipole and a binary. So with the binary fits, we fitted each instrumental band individually. And so you would expect that we should get a clustering of fitted companion positions in a certain area if there was a coherent binary signal. But instead, we find that there's quite a bit of scatter around that, as we can see in this plot. This is plotting the fitted best fit positions for the companion where the colors encode different wavelengths. Also, we find that almost 50% of the best fits aren't consistent with the LSP constraint given the angular separation. So sometimes the binary scenario provided the best fits in terms of the chi-squared, but it's not always consistent across different wavelengths. On the other hand, the oscillatory convective dipole, where we could test it at shorter wavelengths and where we resolved the photosphere, provided a reasonable fit. It wasn't quite as good as the binary fit, but not far behind it. We fitted a dipole amplitude of around 200 Kelvin. And here's the fitted closure phases with a square visibility. Interestingly as well, when we took the best fit dipole model and then we propagated it in time forward and backwards, it actually provided a very good fit to the observed visible light curve as well, even though this wasn't used at all to fit the actual model, nor did it have any prior on the fitted model. Lastly as well, when we analytically removed the dipole mode from the data and tried to refit a companion there, we essentially got a null detection. The fitted flux ratio for the companion on the residuals was below the 3 sigma detection limit that we had. So this indicated that... Yes?
And still 3 minutes.
Thank you. This indicated that the oscillatory convective dipole could explain the residuals or spurious companion fits. Finally, we did image reconstruction using both informative and uninformative priors. This kind of revealed a similar picture, that we have a mild asymmetry across the photosphere at shorter wavelengths, and we essentially reconstruct a blob at longer wavelengths with no coherent circumstellar structure. So in summary, it is hard to conclude that RT-PAVS was LSP is caused by a binary. The oscillatory convective dipole model provided a more coherent picture that didn't violate any of our constraints. So we've submitted a paper on this to ANA, so it should be out soon. And in terms of what we really need as a follow-up for this is really to have temporal sampling across the LSP period to see how these asymmetries evolve over time. And so this is something that we're proposing to do with the new instrument Asgard, and in particular Bifrost, which is going to be one of the shortest wavelength instruments on the VLTI with high spectral resolution to do temporal sampling across a collection of LSP variables to see how these asymmetries across the photosphere evolve. Just finally as well, I mentioned that I was going to talk a bit about this. So I noticed when I was fitting the oscillatory convective dipole models that there was an interesting feature because we have quite large temperature amplitudes across the star. At particular observational wavelengths, you hit kind of the nonlinearity in the black body function, and this produces harmonics in the light curve. So this is very interesting because these harmonics were similar to what was used to argue the case for binarity in terms of causing a secondary minima as the companion goes behind the star. But the harmonics for this dipole contrast to that in that they predict secondary maxima rather than secondary minima in a small subset of data where we can view this dipole kind of at an edge-on inclination. So this arises because the second hemisphere becomes partially visible. So this really motivated me to go back and have a look in the data if I could find signatures of this in the OGL catalog. So essentially I isolated the harmonic sequence of sequence D, which is very clearly there in the OGL data. And I did a Fourier decomposition and looked for, essentially isolated the fundamental and harmonic periods, and then looked at the phase difference between them. And essentially with this, you can characterize whether it's a secondary maxima or a secondary minima. And what I've found is that the majority are secondary minima, consistent with the binary scenario. But there is a small and significant fraction I found corresponding to a secondary maxima. And this number roughly aligned with what would be expected geometrically if you considered just a randomly oriented dipole axis in space. So this is an ongoing study and something I'm looking into, but it could be an interesting signature to kind of differentiate between the binary and oscillatory convective dipole model. And I think with that, I'm pretty much just on time. So I'll just leave my conclusion slides up and just say once again that I think in the case of LSPs, it's quite likely that we have two mechanisms or various mechanisms causing sequence D rather than just a single one, and trying to find ways that we can conclusively differentiate between the two cases, I think is going to be important going forward. And the final note, I'm finishing my PhD very soon, hopefully in the next 6 months. So I'm open to postdoc opportunities if there's anything available that people know of. Feel free to reach out. And thank you.
Thanks, Beth. Very clear, a nice talk. Are there questions for Beth? Okay. Elvire.
Hi, Elvire de Beck from Chalmers University of Technology in Sweden. I have a question because I don't do LSPs at all. But what kind of bugs me, I'm doing quotation marks here, you can't see that probably. What kind of bugs me is that if it would be both binaries and this dipole mode that explain the LSPs, why do they line up so neatly in the period luminosity diagram? Why do they happen to fall together? I mean, it's convenient from an observer's point of view to have two different scenarios that can explain it. However, what are the chances that these periods would be the same?
Yeah, very good question. So I think it's been theoretically shown that these modes do exist and that they happen to fall on sequence D, which is a bit of a coincidence. Also, it so happens that binaries close orbiting binaries with a low mass also fall naturally on sequence D. So I think it's quite possible that you just have this coincidence that there's two physical mechanisms that follow this period luminosity relation. And if you look at it, it's quite thick as well in the period it's not like a very linear line. Like there's quite a lot of scatter around it, which would leave open the interpretation that there could be two mechanisms kind of jammed in there that have some stochastic width around them and they merge together. But there could be overdensities, particular luminosities and things like that. So I think really nailing down where we expect to see these two modes on the sequence is an important point and question that you raised. I hope that answers it.
Thank you very much.
Matthias, we are slightly beyond time, so if the question can be short.
It'll be very quick, yeah. It's Matthias, also from Chalmers University of Technology, and also know nothing about LSPs. But so in any given system, do you think you have either the one or the other method, or could you have both at the same time?
Potentially. I mean, they might be related as well. I mean, I'm very speculative here, but it could be that the binary or some merging event of the binary creates these oscillatory convective modes in the star. That's a very speculative thing to say, but all I can say, I haven't done huge population studies for this, so I can't really talk about the demographics of how much one or the other could be caused. But yeah, sorry, I think I maybe lost the point of the question there.
But you partly have answered it, eh? So
yeah,
indeed,
okay.
sometimes it can be
Thanks.
both. Okay, I think there are still other questions, but we have to move to the next talk that will be given by Emily Siderud. Emily, the floor is yours. Your talk is not yet up. Ben, thanks again for your talk. We haven't said that yet. Emily,
Yeah.
go ahead.
Thank you. So hi everyone, I'm Emily. I'm a final year PhD student at Uppsala University under the supervision of Susanna Höfner and Kjell Eriksson. And this work is a part of the X-Wings project that was introduced yesterday by both Bernd and Joachim. So I will start with giving a brief overview of, or reminder of the Darwin models that is used in this work. So this is 1D radiation hydrodynamical code. So we assume a spherically symmetric star. The inner boundary is situated just below the photosphere, and then pulsations are simulated as temporal variations in radius and luminosity. Simultaneously, the hydrodynamical equations, radiation frequency transfer, and the grain growth equations are solved. So this includes complex physical processes such as propagation of shock waves and also grain growth and destruction. So the outer boundary follows the outer layers of the atmosphere, and if a wind is developed, it will follow the outflow until about 25 stellar radii. So the input parameters for the models are a range of stellar parameters such as effective temperature, luminosity, current stellar mass, and chemical composition. We also specify the pulsation properties in terms of the period, velocity and luminosity amplitudes, and also specify the microphysical properties of the dust and gas. So the output consists of radial structures of the atmosphere and winds. So this means that the mass loss rate, wind velocity, and dust properties are direct results of the simulations. So in this work, I have focused on the pulsation period. So as I mentioned, the pulsations are described by a temporal variation in radius and luminosity. So this is defined by a pulsation period and also velocity and luminosity amplitudes. And what we know from previous work is that timing in terms of when dust is formed in a pulsation cycle is very important. So dust formation happens around luminosity minimum and at low temperatures. And the dust is accelerated when the luminosity increases, so we have higher radiation pressure. And then the grain growth time depends on the densities in the atmosphere. So the period matters because that affects all these criteria that I just mentioned. The period is not an independent parameter in the models. So in this work, or in previous models, the period has been set by this period luminosity relation that we've heard about. So this is luminosity dependent, derived from observed stars. And here you can see a figure from Arif Ahmad et al., where the lines represents two such periods relations. And this is derived from the observations in red. And in this paper, they computed global star-in-a-box models, 3D models, and were able to derive mean density relations from their models. So here's another plot that shows that relation, and we can see that their models, which are all these symbols in different stellar masses, we can see that it actually agrees well with the period luminosity relation as well. So here you can see a comparison of the two when we calculated the periods for variation of stellar input parameters. So we have temperature on the x-axis and luminosity on the y-axis, and the color represents the period in days. So we can see that for a single luminosity, it ranges several hundred days in the period mean density relation. And this also will change depending on mass, as it's also mass dependent. So if here I've taken the ratio between the two, so we can see how they compare to each other. So here, values below 1 means that with the mean density relation, the period is shorter than in the period luminosity relation. But again, keep in mind that this changes with mass. So when we go to lower masses, it switches. So then the period luminosity will have the shorter periods of the two, of most of the stellar parameter combinations. So I'll move on to some of the results. So we computed many different models with varying stellar parameters. So here's an example of one model. You can see the input parameters there. And this is a mass shell plot. So each line in this plot shows the movement of individual mass layers as a function of time. So here, so we can see the shock waves are shown here where the trajectories bend. And this is where sort of dust formation is formed in the wake of these shocks. So the colors here represents the condensation fraction of silicon. So, so here we can see like a dust shell forming in the wake of one of these shocks. And then how it's, when the luminosity increases, it's accelerated outwards. We can also see that some dust is actually following a more ballistic trajectory, falling back towards the star, but then another shock wave comes and pushes the dust outwards. So this is an example with a 485 days period. And then when we compare it to this longer period, we get a slightly different behavior. So now we can see dust is forming, but then it also evaporates and is falling back here. So we can see, yeah, slightly different behavior than previously. So with a less efficient model in terms of the dust formation and wind acceleration or the outflow. Okay. Yeah, a reminder of the timing I was mentioning earlier there. Okay, so here's an example of another model. So this actually looks quite similar to the last one I showed. So where we have some dust forming and then evaporating, and then you can sort of see that it's not as strongly accelerated as the first model I was showing you. So we have less dust forming, some dust or some the gas then falling back to the stars, and then shock layers that sort of builds up the density, and then but still we have a wind. But in this example, when we go to the longer period, there is no longer a wind because here the timing is off. So dust is starting to form, but then it quickly evaporates before it can be accelerated outwards by the radiation pressure. But in this example, we also computed a few models with periods between these two to see sort of what happens as we approaches the no wind model. So here we have a slightly longer period compared to the left one. And we can see sort of a more periodic behavior. So again, some dust forms and falls back, but it's also sort of, as I mentioned, it builds up. So in over time, and then so all these layers. So the more dust will be formed as it is, pushed outwards. All the layers, all the shock waves are triggering more dust formation, and then eventually you get an outflow of material. But yeah, but this can happen more periodically in this model. And if we have a look at the next one, they look very different, but I just realized that they're not the same scale here. Sorry about that. But they're actually quite similar, but it's two quite different snapshots. So in this particular one, we can sort of see how it's building up, like the densities are building up. So after a while of these types of pulsations, we will sort of enter an era with these where more mass builds up and we have sort of stronger outflows. So we see a variation in mass loss rates and wind velocities over time. And then if we just increase by a few days, we end up with a model with no wind. So how does it look then for several models? So as I mentioned, we computed a large range of stellar parameters. So here we can see a comparison of the two models. Oops. So we have the period luminosity on the x-axis and the 3D models on the y-axis. And the color here represents which of the two models that has the shortest period to see if we can find any relation with the period length. But actually, we don't see a clear trend when it comes to that. As you can see, it's scattered all over. However, we can see that some models line up here along the axis, and that means that we have a wind in one of the version periods, but not in the other. And in this case, it's always the shorter period that wins, or that develops a wind. And I've also colored this in the various stellar parameters to see if we can deduce anything from that. So here's a mass, but again, it's quite spread out. Same for the luminosities that we've used. So when I mean spread out, I mean like between these, the ratios. And effective temperature, again, also very spread. And here's an example with the piston velocity that we've used. And here I have a comparison with some observations. So here I'm showing the mass loss rates versus wind velocities. So the period luminosity relations on the top and the period mean density relations at the bottom. And we can see that they span quite similar space or distribution in these plots. But as I showed before, individual models may change significantly. But yeah, the overall distribution is similar, so it's still in good agreement with observations. So this leads me to the conclusions. So yeah, period matters. As I've shown, some individual models may change significantly, and the shorter periods are more favorable for the winds, as we've seen. And also this, so in Arif's paper from 25, they computed more 3D models and also compared them to Michele's models, and they agreed really well, as Michele also mentioned in his talk. And so for the future, we're looking to implementing more parameters from the 3D models regarding the pulsations. So we can, for example, look at velocity and luminosity amplitudes, hopefully, but also on the shape of luminosity curves and phase shifts. So yeah, thank you.
Thanks, Emily, for the nice talk. Questions for Emily? Hans.
Hans Seneca from University Autónoma, Chile. Why does the short period win, or the wins? I didn't quite understand that. Can you show that graph again?
Yeah, sure.
I mean, and by how much? I like the wine glass.
I saw it as a trophy, but I guess it can be a wine glass. Yeah, so I guess you don't really see it in this plot other than you can see the models lining up here. That so the colors show that they are so in blue it's the period luminosity that is the shorter period of the two, and here we only have wind in the period luminosity version of the model. Sorry. Oh, the physics. Yeah, I mean, that takes me back to these plots, I think. So here is an example where, so this is a shorter period and the longer one here. So as you can see, when the period gets longer, yeah, the timing is off. So dust is formed slightly and then quickly destroyed. So there's no dust when the luminosity increases. There's no dust to be accelerated outwards. So. Yeah. Thanks.
Hi, Ilek Elmela, Universitat Politècnica de Catalunya. Thanks for the very interesting results. Similar question, like your shut-off period right here, you mentioned that you were focusing like on silicon-rich dusts. How sensitive is this shut-off period to the type of dust you're considering?
I've only tried it with this silicon dust. Yeah, so the M-rich models. Okay. So yeah.
Thank you.
Thanks.
Thanks, Emily. Given time, we have to close here.
Thank you.
Thanks a lot. The next talk will be given by Theo Kurig from Chalmers University. Theo, we are still waiting for your slides to come up. Here we are, at least at the screens at the bottom. Yes, we can go.
Yeah,
Theo.
thank you. So hi, everyone. So first, thanks to the organizers for inviting me to talk about this. This is, of course, done in collaboration with a lot of people, especially at Chalmers, but many of whom are here as well. So yeah, I'll talk about high angular resolution observations of nearby AGB stars with ALMA and SPHERE, and what we can learn through detailed studies of just a few sources. So this is a schematic view to kind of bring everyone to the same page. We have the AGB star there. We have heard a lot about these hydrodynamical simulations of the pulsations and convections, and how this builds this extended atmosphere where dust can form and grow. And our idea is that if you form dust that couples well enough with the radiation field, the radiation pressure on this dust will lead to an outflow. And I will be talking about oxygen-rich AGB stars, for which we expect the grains to have to grow to relatively large sizes for scattering to be the dominant way that they interact with radiation, and that have enough cross-section to then lead to an outflow. Yeah, so I think that's more or less the motivation. And I'll be talking about ALMA observations in which we see molecular lines, and we derive the properties of the gas, and about SPHERE observations with the VLT, in which we see scattered light, in which the light gets polarized, and then you can derive the properties of the dust grains. And this is just to give a little bit more context. So this is a model from Suzanne, about 10 years old now, surprisingly, and in which we see formation of aluminum oxide close to the star with potentially very efficient depletion, and silicates further out. And this has also been, a scenario like this has also been supported a lot by observations and abundance constraints and interferometric data of nearby AGB stars. Okay, so then we ultimately, we want to compare what we are observing to this type of models that Ben and Joachim showed, in which we see these clumps of gas extending away from the star, in which you see dust condensation, as they showed before. And as I'll show later, we think we see something like this. We still have to work out the details of that. So the goal of what I'm going to show is to determine the distributions of gas and dust close to two AGB stars, Aldorados, which is a semi-regular variable. And I think that will connect very well to what we just heard this morning, and Myra, which is a Myra type variable, is our imperfect archetype. So let's start with Aldorados. And I added this side note here. Is a paper by Wouter Vlaming, is also at Chalmers, in which we were observing Aldorados to constrain the properties of the gas around, but the angular resolution of the observations was so good that we resolved the stellar disk super well. And luckily, Alma had to observe the star 3 times to reach the sensitivity that we wanted. So then we saw how the brightness distribution on the surface of the star is changing as a function of time. And that allowed us to say something about this brightness distribution and the characteristic scale of these variations, which is something similar to what Claudia had done for Pi1 GRU a few years before. So then Wouter used these visibilities measured by the interferometer to distribute the data into the power at different structure sizes, and then constrain the characteristic size of these convective cells in the region that we were looking here. And then he was able to put a second point in this plot, close to the one that Claudia had before, in the characteristic size versus log G with considerable error bars. But it's very interesting that we can do this type of stuff now with ALMA for nearby AGB stars. Yeah, and this is now W Hydra that Keiichi talked about yesterday as well. It's not always boring. The continuum sometimes show like hotspots and interesting things. And Miura and Bezad back there will talk more about continuum later today. This is Myra here on the right. Yeah. Okay, so then let's move now to the gas. This is very similar to what Keiichi was showing yesterday. There is a star here. The column map shows the continuum. We see absorption, the dashed line against the star. It's not uniform. It changes as a function of time. And we see the emission coming from around. So this is so we have a number of different transitions. This is a relatively low excitation transition, CO in the ground vibrational state, J2 to 1. But even these very low excitation transitions, which are basically excited everywhere in the envelope, they show this very bright ring around the central star. And as I will show later, that's just because the densities there are so high. So then if we kind of take spectra, using different apertures towards the star, we see absorption. When we look at the star, so now we have velocity and flux density, and we get these negative values because we subtract the stellar continuum. And when we look around the star, then the emission from around kind of overwhelms the absorption, so then we see an integrated emission profile. And then we look at several different transitions. This is a paper from last year. And then we see that very high excitation transitions like CO in the first vibrationally excited state only come from this very dense region where the temperatures are high as well, close to the star, while lower excitation transitions will trace gas in a broader region. So I went through the effort of modeling these observed lines as a function of size of the aperture and for the different types, different transitions of different molecules. I was very proud of this model. Took a lot of effort to get to, but what is really interesting to get out of this is this type of plots in which we have velocity, density, and temperature as a function of radius away from the star. The density and the temperature vary. We can get a model that is more or less, it's basically spherically symmetric to fit the observations. And we can see that from the images. There's not super strong departures from symmetry to start with. For the velocity field, we have to make some modifications to fit the line profiles, but overall, fairly spherically symmetric model works very well. One thing that is interesting is that the temperatures are extremely steep of the gas. It cools down very quickly, and that's, I think, it's very well constrained because it's basically related to amount of absorption that we see towards the star compared to the emission from around it. So when we get to 1.6 times the stellar radius at this wavelength, the gas has cooled by more than a factor of 2 already. And then we get a structure like this, in which we have this very high density region, but it's relatively narrow, which we see as a bright ring here, and then a lower density region further out with a transition at about 1.6 times the stellar radius. And the densities that we get here are kind of consistent, or are consistent with what we would expect if we extrapolate the large scale mass loss rate densities inwards. So it seems that from here on, basically the wind is driven for our door, and it has a mass loss rate of about 10 to the minus 7 solar masses per year, which I think is interesting with what Bernd and Joachim were talking about before. Okay, so then now we have a description for especially the density as a function of radius for the gas. Now let's look at what we see for the dust. So these are the observations at visible wavelengths now with sphere. The star kind of surprisingly looks to have a similar size in these two wavelengths, even though the opacity sources are very different. Free opacity in the submillimeter, and molecules and dust in the visible. But what we're interested in is in diagrams like this. So now this is a larger region than what we were looking at before. The star is in the center, is again dark because we're looking at polarized light. So the direct stellar light is not polarized. When it gets scattered by dust, and we primarily see dust on the plane of the sky in this type of observations, then we see polarized light coming from around the star. And then Thibaut Schirmer, that was in Chalmers with us as a postdoc, did a very careful modeling of this data. So we have these 3 wavelengths, and he used spherically symmetric models to then retrieve the dust density as a function of radius. And one thing that I always like to point out is that we basically see dust as soon as the star ends. There seems to be dust basically at the visible photosphere. And what Thibaut came up with were this type of plots, in which now you have the gas model here in the dashed line, with the uncertainties that we had, with his dust models. So he got a lot of different models that fit the data, and those have different grain sizes here. So here's just a comparison of the densities, and here we divide the gas model by the dust model to get gas to dust ratios. So the colors are still the different dust sizes, and now we have added a constraint which is based on the depletion of silicon. So Marie had a paper from 2018 in which she estimated the depletion of silicon, which would be this red region here. And this line marks full depletion of silicon for solar composition. So we would expect models to be above here if they are fitting our depletion constraints. And then what he did next was to calculate for these grains that we were deriving with the sizes that he was finding for MgSiO3 and aluminum oxide, what would be the radiation pressure divided by gravity that this dust would provide. So if we want to have a dust-driven wind, we want the models to be up here, in which this gamma factor is more than 1, and that they respect the depletion constraints. Or maybe in the D region if we relax these depletion constraints. But what he finds is that we don't get any models there. And the models that come close to gamma equal 1 require very unreasonable amounts of dust with respect to the gas densities that we see. And his models are consistent with this picture that I showed in the beginning, in which you have aluminum depletion in this very high gas density region. So we probably have a lot of aluminum oxide there. That's consistent with his models. But further out, you need silicates to explain the amount of dust we see. The problem is we don't get enough radiation pressure from the grains that we find. So this is what I am saying here. So I think this is very interesting, especially in relation to what Bernd and Joachim talked about yesterday, is that it seems like the dust is not driving the outflow of adoradas, but it's still forming quite some dust with a gas to dust ratio of 1,000 or a few thousand with 10% silicon depletion. But the dust seems to be a consequence of the outflow, not a reason, which if they find these models that have winds without dust formation, maybe that's what we are seeing for this star. Okay, so Myra, and it's very interesting to have these two stars because they are completely different, one from the other. So again, we start with the gas. We have these ALMA observations with several molecular lines, and they show a very interesting structure. So Joachim showed this image, which is polarized light now, but we start with the gas. And we see this type of heart-shaped structure for all basically lines that we observe in Myra. This is data from 2017. And what is interesting is that we got some later data in 2023, and I'm showing now one transition of sulfur monoxide here, and we see that this structure expands within these 8 years between these observations. And then I went to and we see the dust, we see that it mostly kind of occupies the same region. So that the gas emission would be here, kind of a lot in the same region where the dust is seen in the polarized lights. But I went to the Sphere archive and I looked for observations of Myra, and it turns out that there is 6 observations over these 8 years, more or less. And we can see how these lobes expand as a function of time also in the scattered light images. So there is a structure down here that doesn't seem to change much between these different epochs, but you can see this edge of the lobes, how they expand as we move from 2015 to 2023, when they are very big. One thing that I was very surprised by is how strong the relative variations of the brightness in these polarized light images is between the epochs. And the only way that I can understand this is if the star shines a non-uniform radiation field, like a lighthouse effect that sometimes brightens up things in one direction and not in others, which will make it a nightmare to derive the properties of these things, but maybe it allows us to reconstruct the stellar brightness distribution as a function of time in different directions, which is something that we can potentially compare to models as well. So it takes one thing away, give us something else potentially, but I was very surprised to see these variations. But what we can do then is we can fit the position of the edge of these lobes as a function of time, and we managed to fit it very well. Unfortunately, we managed to fit it so well that we don't know what the ejection mechanism is. It can either have been a very high velocity ejection that follows a ballistic trajectory. Those are these lines from starting here. Or it can be wind that has basically a constant velocity. So they both feed the data. We are not able to tell what ejection velocity actually was. So then looking at the gas again, we have these 6 lines of SO2, which are very conveniently spread in excitation energy from about 30 Kelvin to 1,000 Kelvin, which is kind of the temperatures we expect for gas in this region. So then I use this to constrain the properties of the gas by doing a population diagram map, I think is how I would call it. So for every pixel, we have a population diagram in which the steepness of this line here gives us the temperature of the gas, and then we can derive the column density of the molecule as well. And then we get these maps for the excitation temperature and the column density. But looking at SO2 is not the best because we don't know what the abundance of the molecule is. It can vary a lot with radius, so we don't know if we are looking at a molecular abundance variation or to a true gas density variation. So then what I did was to use 13CO, for which we think we know the abundance much better, and to use the same type of, excitation temperature that we got from SO2 for 13CO to then construct a gas column density map. So then the question is, are we seeing something like this, in which you have one lobe here and some other lobe in another direction? Maybe, but as I'll say later, this is still puzzling, even if it is what it is. So then I use this now temperature and density maps that I get to kind of as a first guess to a radiative transfer model, and that fits very well with the lines. I compared the lines to the observed ones in the same way that I did for our door, and we get this type of velocity, density, and temperature distributions. This part is coming from these lobes only. And the first thing is extremely steep temperature profiles. So I think that's something really that we have to take into account. This gas cools very quickly as you move away from the star, which of course helps dust formation and just things in general. But the other thing that is also very interesting, how much time do I have, Lane? Okay. I'm going much faster. I'm going much faster than I thought. I hope you guys are keeping up. So then the thing that is interesting to me is that we see a lot of mass in these lobes. So about a few times 10 to the minus 5 solar masses, which is very significantly more than what Myra seems to be losing per year or per pulsation period. So then the conclusion would be that this type of event is a very rare ejection that happens only every almost 100 years, which is kind of surprising. But I think I'm already at the end, yeah. But since I still have 5 minutes, I'll go back. to make things a bit more complicated, because unfortunately, and I know a lot of people like binaries now, but in this case, it's unfortunate that Myra has a companion, which is this red dot there. So that kind of is at 50 AU from the AGB star. So we don't think is affecting things close to the AGB star in principle, but it will prevent us from following this ejection for a much longer time, because it eventually to get disrupted by this gravitational field that has a white dwarf not too far away. So that complicates the interpretation. We don't think that the ejection has anything to do with the companion, but the companion will kind of limit how far we can follow this for Myra. But the idea is that we follow it and we see what happens with this ejection now that we see that is there. And I think having these two stars that I told you about today are Dorados, which is a semi-regular variable, has a mass loss rate that is not much lower than Myra, but for which we seem to see that the dust is a consequence of the outflow rather than the cause. It's very interesting. And then to see Myra that has this kind of structures which resemble a lot what we expect from these 3D simulations, but seem to be very massive for what we'd expect for the relatively low mass loss rate that Myra has. And unfortunately, there's a companion, which kind of complicates this translation from what the AGB star is doing to what is actually being lost by the system as a whole in the end. So hopefully we'll look at another Myra type variable, our Leo, that Leia has just joined us and has started to look into that. And hopefully we won't find any companions around our Leo to complicate things. But I think it's very interesting how these two stars, which in principle have relatively similar mass loss rates, they do have very different dust properties. So our door has much more aluminum oxide rich dust. That's connected to what Angela was asking before. Myra has this very clear silicate feature. So I think it's very interesting to have these two sources with similar properties on one side and very different properties on when we look at them in detail. Okay, I'll stop here.
Very interesting, Theo. I see hands already many, but we have time for questions. I go first to the person just in front of you.
Hello, it's me, Jaime Alonso from the Spanish Center for Astrobiology. I have two questions. The first one is, Myras is an X-ray and ultraviolet emitting AGB star, so maybe it's photodissociating the molecular gas in close to the star. May this thing produce an underestimation of the mass loss? And for this reason, there is this disagreement between the mass of the lobes and the mass loss.
Yeah, so that's a very good question. Thanks. So one thing that we see is that in this SO line, for instance, we see something that seems to be carving out here, and I think that probably has to do with the companion that is somewhere there and is emitting this energetic radiation. There was also an X-ray flare from Myra A that people observed with Chandra, I think. And that when we saw these lobes, I was very convinced that that was the ejection time would be the same as the X-ray flare, but it's not. It's about 10 years after. So it's very difficult to blame the X-ray flare for this ejection. But yes, I think it could be, in principle, that we are underestimating the mass loss rate of Myra. But Myra has also this very long tail that people have seen in the UV. I don't know which wavelength it was, but it's very long tail, and people have done hydrodynamical simulations, and the tail seems to match this relatively low mass loss rate, and that I don't think would be affected by dissociation. So, but I also don't know if the tail is also consistent with a higher mass loss rate. I think people haven't explored that. But
it's very
the answer is maybe.
Yeah, it's very complex. It was just to put this thing over the table. The second one, very quick. Did you mention that you found dust in the photosphere, but do you mean inside the photosphere or just in front of the photosphere? When you
So
talking about
we basically see dust as soon as the star ends. And I think there were some papers by M. Ireland. I don't know his first name. Yeah. Like 15 years ago, I think, and they were talking about the photosphere of the star being also defined, well, the dust opacity contributing to setting the photosphere. So where you reach this tau equals 1 surface, more or less. And I think that's probably the case, that we have dust below what we would call the visible photosphere. And that opacity also contributes to setting the size of the star in these wavelengths.
Okay, thanks a lot.
Okay, next question. Keiji?
Very interesting results. And I have a question about the grain size you got on Dorados, 0.1 micron. But the one of the first papers that reported observational evidence of large grains, large transparent grains, Norris et al. Included Dorados, and they got 0.3 micron. So I just wonder if the grain size can be temporarily variable.
Yeah, that's a good point. If I remember right, they only assumed a value for Ardor. They derived for the other two sources they had, which I think was W Hydro and Arleo, if I remember right. And then they assumed that the same size would apply to Ardor as well, if I remember right. But it could be that it varies on time, but we have observed Ardor a lot, and it always looks the same. It's very different from Myra, where we see this very clear evolution, very clumpy. Ardor doesn't seem to be doing much as a function of time.
Yes, Julien.
Hi, Theo. Julien Drevon from ESO Chile. Just a short and naive question. Would it be possible, if you look at your sphere image just before, that the shape is, so you told us that the companion is not responsible of what we are seeing, but what about a third companion closer to the star?
Yeah, it could be, but I think we have enough companions for unless someone shows me a picture of the companion, I won't believe it. But yeah, it could be that there is something going on close to the star. But seeing the models from Bernd and the Uppsala group yesterday, I think what we are seeing could be explained just by these very large pulsations that Myra has. And apparently, it can be that these are very rare ejection events, which is different from the picture I had 2 months ago. But yeah, I think if we don't need a companion, shouldn't bring it up.
Thanks, Tori, for that really good talk. So I have two questions, but my first question is, do we know if this system hosts a maser? Because if that does, the plot you showed of your change in surface brightness is actually quite interesting. So do you have any observations for that?
Yeah, they both have masers, I would say all of them, but
right.
I'm not 100% sure, but they do. But one thing that kind of bugs me a bit with this is that Myra has this super regular light curve. So if the star starts shining differently in different directions, I don't know what that does to the light curve.
Right.
I discussed it a bit with Suzanne a few weeks ago, and it looks like even though the light curve is very regular in period, the peak to peak, there's some peak to peak variation that maybe there could be, that the star varies how it shines in different directions, and that would still be hidden in the light curve.
Okay.
But yeah, so they both have all masers.
Okay. May I ask my second question as well? Thanks. So Theo, my second question is, and this is maybe just my lack of understanding, you noted non-dust driven outflows. What did you mean by that? Could you clarify? How do you have a non-dust? Yeah, and you also noted winds without dust formation. So I was very curious.
That's something I also learned recently. I had always this dust-driven picture in my head, and we were very surprised to see that for Dorados, we couldn't explain the wind with the dust we were seeing. But this goes again back to the models that Bernd showed yesterday, especially Joachim showed afterwards, in which even when they turn off dust formation, they still get a mass loss rate, which I assume just comes from convection, pushing things out. But that was surprising to me that they find that in the 3D models.
A very strong mass loss rate, but we can discuss that.
Yeah.
Thank you.
Since I'm here, I maybe pose also my question. If you don't have a dust-driven wind, for Erdor, what is then your claim for Myra? Can it have a dust-driven wind? Or you'd also say dust is a consequence of the wind?
So the thing that we haven't done for Myra yet is a second step, is to model the polarized light and try to retrieve the properties of the dust. And it will be more complicated because it's very non-spherically symmetric. So that will depend a lot on the orientation and on the grain size. So it becomes harder, but we can try. So I don't know. At the moment, I don't know.
And also maybe to complement to your question, I will show that on Thursday. Florian Driessen, one of my postdocs, has done a simulation. And just by putting in a companion at a mass of 0.1 solar masses on an eccentric orbit, you can increase mass weight by a factor of 5 to 20 easily. So it might be indeed what Steve was saying for Erdor, that it's not the dust that is driven the wind, but if you have even a hidden companion, you don't have to see them. They can be the cause of the wind, and then combined with dust, you can have this kind of a complex pictures. Okay.
But I think we need less companions, not more companions. But one thing that I'll say is that our door is rotating, which it shouldn't be. So maybe there is a companion. I don't know.
Let's discuss that. Good. Thanks a lot. We're sharp on time. We go to the coffee break. Thanks a lot for all of the nice talks this morning, and enjoy the coffee. I didn't realize that the outcome of Schiller's thing was that the wind would not be dusted.
Hello, everyone. Let's please find our seats. Everyone, we have to start. It turns out it was my job to get everyone back from the coffee break, but I didn't realize, so we are late. So the first thing is that we have a QR code there for the voting form. And we found a bottle. So please vote. And if this is your bottle, please, come get it. Okay, so we have the first talk of today by Behzad Boynord Arbab, and he's going to tell us about dynamic atmosphere models and high angular resolution home observation. You have the microphone. Okay. Go ahead, Behzad.
I'm waiting for the presentation. Yeah, hi, I'm Behzad Boynord Arbab. I'm a PhD student at Chalmers. And if my voice is cracking a bit, if my voice is cracking sometimes, occasionally, it's not because I'm emotional about this observation, it's because I have a bit of cold. So I'm very interested in the dynamic atmosphere of these stars and the inner region very close to the star. And I will show you some of the results about the high resolution observations with ALMA about specifically one of these stars. So I think you're completely, you know what the AGB star is. And so I'm trying to looking at the inner regions here where the mass loss is at the outer region, we see the dust formation, but the inner region dictates the density and temperatures in the higher regions and how the shocks can go through these regions. So this is very important to look at and to quantify so that we can see if the models are fitting what we can see in the observations. So I'm looking at this with radio, with ALMA, where specifically I'm looking at the continuum. So what I'm looking at, you can see that we have, of course, different bands with ALMA, so we can observe in different frequencies. And I have looked at the continuum in the different frequencies from band 4, 7, 8, and 9. So, and it's very interesting in these observations, we have high resolution, so we can resolve the surface of these stars. And the main opacity is here free emission. So the free emission, just a very short overview, that this is the acceleration of electrons in the vicinity of a positive ion, which can emit photons or absorb it. So in the densities and temperature of these atmospheres and the frequencies that we're looking at, we assume that this is the main opacity. And this opacity also has this property that if we go to higher frequencies, the opacity decreases. So if you're looking at higher bands, higher frequencies, we can see deeper and deeper into the atmosphere of these stars. And that's very good. So, and the expected physical model that we see here, and what we expect to see from these observations, if we are looking at the free emission continuum, and then we expect to see a disk because the temperature and density fall rapidly, and we can see still very small wings, but the main expectation is to see a disk. That was a brightness temperature profile. So to get most out of these observations, we directly fit the data to the observation. So we don't image it, we fit directly to the visibilities. And because of that, we can also estimate the parameters directly. So, and we use a Bayesian nested sampling so that we can get the posteriors for each parameter. And also on the left side here, you can see brightness temperature profile. And this is and you can see two regions. These are the confidence intervals of 1 sigma and 2 sigma of the profile that we see, we have fit based on the observations. So we can see what we expect from this observation by the model. So I think I can skip most of this because Theo has talked a lot about that. And so I go directly to the results. So here I showed a fitting of a disk on the profile of these continuums. And to measure if a model, for example, a disk or a disk and a Gaussian or different models are working well or not, we can do it in several different ways. We can take the residual visibilities after removing the model and then image that and see if there's any structure remaining, or we can look directly at the visibilities. And, or we can also, because we are doing also nested sampling, we can look at the Bayes factor and compare between different models. But here in band 4 for our LEO, it seems that the disk model is working pretty well. And on the right side, you can see the model shape. Is it working? So, do you hear me? No? So on the right side, you can see the model shape, and this is an elliptical disk and a cutting line. And here is the profile if we cut this shape from that line. And you can see that it shows a disk, which we wanted it to. And in different frequencies within that band with different spectral windows, we can see that these are also like different colors are showing different spectral windows, and they match pretty well within the uncertainties that we show with the credible intervals. And if we look at it at different directions, also this stays. And for band, this is what I was talking about. So in different dates, we can see that these are 4 observations through 1 month. And we can see that the profile stays almost the same in band 4. The small changes are within the uncertainties that we can see, I mean, by the shape, but the sizes change and the brightness temperature also changes a bit. So if, I think you cannot hear me. You cannot? I don't know what to do. I can sit there. Can
Hello?
you?
Hello?
Oh, yeah, that one.
Hello? Hello? Up? Maybe use that one.
Yeah, I can. Can you hear me? Yeah. Okay. So this feels more political. So here you can see that okay, I don't have enough. So in band 7, we don't see that the disk is working well because on the right side, you can see the residual after removing the visibilities, the synthetic visibilities from the model. And it doesn't work well. So what we do is to add a Gaussian. And now this works pretty well. So what it shows in the profile is that now the disk the profile of the disk seems to be a disk plus a very small Gaussian, very small in the amplitude, but very large in the size. So, and you can see in 25 days later, it changes a bit, but we can also look at it and study that too. When we go to higher frequencies in band 8, then this becomes more problematic because the disk plus Gaussian doesn't work either. And I've gone to like disk plus 3 Gaussians, so I'm adding some structure to that to see how the shape is. And it seems that with much more complexities, we can get something out of it, but I'm not showing it here. And in band 9, we can see that the Gaussian component becomes very strong. And as you can see, the star is different in different spectral windows. And this might be the change you see from band to band, and might be from the fact that we cannot correctly completely isolate the continuum in higher bands because we have forests of lines, and very small lines can produce a pseudo continuum, which doesn't correspond to the free emission anymore. we've tried a lot to remove those, but it doesn't seem to go away. So from these observations, we also estimated some of the parameters. For example, here you can see the flux density versus frequency. And the fitted line shows a spectral index of very close value to 2, suspiciously, very close to that. And what it means is either the star is not changing at all, which cannot be true, or the temperature is varying as r with the power of minus 2. This is in large ranges of frequencies, but if we look at it at lower ranges, for example, within each band, then this doesn't stand. So at those frequencies, if we look at very small frequencies close together, then we can see the layers that we are looking at is expanding or changing in size and brightness temperature, and that doesn't show the overall spectral index that we can see. It shows lower and higher spectral indices. You can also check it with the models from the previous paper. So also from the stellar sizes, here you can see the best models that were fit on each of these observations. In band 4, you can see on the left side, and this is the size versus date, and on the right side is versus frequency. On the left side, you can see that in band 4, we are seeing the changes in the size, but if you compare it to the band 7, the green ones, you can see that band 4 is always looking at higher altitudes, which is what exactly we expected. And but in band 8 and band 9, which is the yellow and the red one, you can see that we are looking at higher altitudes, and we are not seeing what we expect from a free emission. So I think, oh, I have 1 more minute. Okay, so I think I should go to the summary. So here, this is one of the stars, one of the 3 stars in this project, this ongoing project, that we have shared with you. I've shared with you the continuum. So, and this is only for the observations from 2023. We have also added other observations from 2025. So we are also studying those. And it seems that if we want to study the continuum, we need to stick more to band 4 and band 7 observations. But in band 8 and 9, it's very interesting to see what is happening and why this pseudo-continuum exists. Anything? That's it. Thank you.
So we have time for questions for Behzad. Hans, go ahead.
Thank you. Very nice observations and talk. Have you tried to estimate whether you could detect radio recombination lines from these ionized regions?
From these observations, we couldn't find a good recombination lines so far. But we submitted a proposal. It wasn't approved.
But have you tried to estimate the expected line strength, or?
Not yet. Actually, we did, but I don't remember now. Yeah, because we used that in the proposal. So
would be a very interesting probe, I think.
One quick question, if yeah, Javier, go ahead.
Javier Colea from OIN in Spain. Nice talk. Had you considered that maybe you have dust contribution in the higher bands of ALMA? And that's not only pseudo-continuum, but dust. So you have both free and dust contribution in these higher bands?
it can be, I think that's a very good point. It can be from also dust, but at least we know that from when we were removing the lines, there was no time that we were completely sure that we have removed all of them, and they go through like the noise levels, you can still that they go through that. So I think I don't have a good idea, but we haven't touched completely about what this can be. This is the first like speculations about that. But yeah, of course, dust, and so far we have thought about dust and the lines, but yeah.
Okay, thanks again, Behzad. So now we move on to the talk by Daniel Jadlowski, ALMA and VLTI imaging of cool evolved stars. As soon as the slides are up, feel free to go ahead.
Okay, thanks. So, hi, I'm Daniel Jadlowski from Maastricht University in Czech Republic, and currently I'm doing studentship at ESO
Daniel, please keep the microphone close to your mouth.
Okay.
Thank you.
So thank you for the opportunity to present our talk on joint ALMA and VLTI imaging of cool evolved stars. So first, let's briefly introduce masers, which are one of the main goals of our imaging. So some evolved stars emit very strong maser emission, and due to the strength of this emission, this allows us to trace the inner circumstellar environment of these stars. So as you can see in this image, the masers form near the molecular zone and dust formation zone. So there are different kinds of masers depending on which molecule is responsible. So in this work, we focus on SIO masers, as I said, which form closer in the launching region. And then there are also other masers, which typically form over larger distances that can be used to study terminal velocity of the wind and the shape of the nebula and so on. And let me briefly mention some previous results on SIO masers. So usually they are ring-shaped, which is due to tangential amplification. This was shown in VLBA observations by Witkowski. And then also, however, in other cases, like in Atomium project for P. Grui, actually these masers had different shape, and here it seemed to trace the spiral structure due to a binary. So let me quickly introduce our observing project. So these observations were carried out in summer 2021. Both proposals were led by Markus Witkowski, and so observations in ALMA were taken in the highest possible angular and spectral resolution so that we could compare to the resolution of VLTI. And so for VLTI, we got Pioneer, which has angular resolution up to 1 milliarcsecond, and also Matisse in mid-infrared, which has slightly smaller angular resolution. And the target were 3 oxygen-rich Mira stars with suitable size for this combination. So RPEC, RR Aquila, and R Aquila. And as I say, the goal is to compare or combine these observations, mainly the molecular bands in mid-infrared, the SIO molecular bands, which we could combine with the SIO masers, because these bands and masers should form in the similar location, and thus we could combine the kinematical information with the images from VLTI. And overall, the goal is to trace the pulsations and shocks as they trace from the surface out into the dust formation zone, and to study the mass loss process. So let me introduce the observations for the first star. So I show here one of the profiles of the maser for RPEC in band 7, and you can see that it appears as a single feature, but as I will show in next slides, actually we can resolve very more precise measurements in each spectral bin. And so also we include some thermal lines, which are typically more extended. And in our observations, they are the goal of our project, but usually these thermal lines show more extended nebula, and which is diffuse. And so then we also have continuum windows, and the continuum images that we get from ALMA we can use to combine with VLTI to kind of align the ALMA and VLTI images. So then onwards to the masers. So masers, as I was mentioning before, are very unique probe because due to their strength, we can fit their position with very high accuracy. And actually the accuracy can reach up to a few milliarc second. And so we did this fitting in APES package. And as you can see on these images that we got for our pack, on the left is band 6, and on the right is band 7. And you can see that in band 6, these masers still are kind of ring-shaped as in previous studies. However, then in band 7, these masers get much more extended and they trace very surprising structures, especially in this transition where we see some kind of spirals or blobs. And you can also see that really the resolution, position accuracy due to the strength of the masers is quite high. And when we combine these masers together, you can see that these different transitions kind of complete each other. So when you combine band 6, you get more or less ring-like structure. And then also these masers from band 7 complete each other. And also we can plot them all together. And you can also see that some masers form in front of the star, which is also not expected. And so then the main question is, what does these masers in band 7 trace? Could it be magnetic fields or shocks or maybe binarity? So for this star, for example, when you compare to velocity maps from Cobalt, we can actually see that maybe some of these structures are quite similar to the asymmetric outflows present in Co5 bolt models. So likely maybe these masers, they trace the shocks and pulsations and dust formation zone, perhaps. However, so let's compare to VLTI images, so that's whether we learn more. So for VLTI data, for this star, we have a lot of Pioneer data and also MATIS in L band and N band. And so for imaging, we used MyRAV wrapper by Julian Drevon. And so in Pioneer, which is the lowest wavelength, we see the surface of the star. And in this case, because of nice UV coverage, we can also resolve some structures on the surface. And then as we go to longer wavelengths, we see increasing diameter because then we see molecules which form farther from the surface. So there is MATIS L-band image and N-band image, for example. But now let's compare to the ALMA images and see if we recover the similar spatial scales. So first I here compare the ALMA continuum image with the Pioneer image, and we see actually the agreement is very nice that we get, especially in band 6, we get nearly exactly the same size of the diameter, which should be the case, as you can also see in this compared image when we plot together all diameters from Pioneer, MATIS, and then in the M band. And you can see that the diameters in Pioneer indeed are similar as they should be tracing the photosphere of the star. And then in the mid-infrared, we have contribution from molecules. Here I show just SiO molecules, which are the most important for this work. However, there are also a lot of other molecules like water and CO. And we get also from 9 microns, we get silicates and other dust. And you can see that also the radius in that point increases significantly. And so now we can compare these masers to the location of VLTI images. And so this is the SiO band at 4 microns. And we can see that this kind of gives a minimum radius for these masers, or at least the ones that do not form in front of the star. And then we can compare to pumping band head at 8 microns. And this gives more or less average radius of these masers. And then also in silicates, we seem to get kind of maximum radius. So it seems that there is clear relation between the masers and VLTI images. And basically it seems that the innermost SiO layer is also the minimum radius for these masers. And then it seems that none of these masers form above the dust. This is the radius of the dust zone. So, and now let's compare the other star. And here actually we find that it's completely different. So then we have our Aquila. It has extremely strong maser. And you can see also on these channel maps that there is several components, and they form farther from the surface. So this is one band which is weaker, but then in this band we see very elongated structure, and it forms at 7 or 8 stellar radii from the surface. And overall it's much farther. And then also there are VLTI data, so we can do the same exercise again. So we can compare, here the UV coverage is slightly worse, so we don't cover so many surface structures. And then we can compare the diameters again, and actually here is interesting, then the diameter in band 6 is much larger than in band 7, and the one in band 7 corresponds the best to the Pioneer. And we don't have N band, as I mentioned, so only L band. And then we can compare this, and if you compare this to the previous images, this is completely different because basically there are no masers, or only very few masers in the same distance as this molecular layer in L band. And when we zoom out, as I said, these masers form very far, and especially in in one location, there is a concentration of the strongest masers, but also there are on some on the other side. And then also for this star, we also got SIS emission, and this one also peaks in the same position as the masers. So it's very interesting what this could be tracing. And we can also see this kind of S-shaped structure here. And also there is a previous image from VLBA from 2010 where this elongation was also seen, but it was in different direction. So it's likely that there is maybe some companion or some component which is masing very strongly at this distance. So this could be maybe related to a binary companion, but I'm interested to hear thoughts from more experienced people on this. And then we also have Araquile, which is where we have only one band, and this one seems more similar to RPEC, where we have a single feature very close to the first surface. And then it's also interesting for this one that it has very extremely large expanding nebula. This is one of the thermal lines. And basically this expands up to several arc seconds. This was also reported for other species in Atomium project. And then we get these masers again. And it's kind of similar like RPEC, but there is less. There's basically a single feature in this single spot. And there is also this kind of maybe structure, but it's close. So this one seems similar as RPEC, and we have only Pioneer and one band, so we couldn't do imaging for this one. So for conclusions, as it's clear, these masers are a very unique probe that allows us to trace the circumstantial environment at very high resolution. But it's apparent that for different stars, it seems to trace very different processes. Like in the case of RPEC, it traces very well the pulsations and shocks. So this could also be used to maybe verify the cobalt simulations. However, then for other stars, maybe when there is a binary or something like that, then this traces different processes. And then so I would be happy to discuss with people who do maser codes and study masers about their thoughts. And then also if I can steal a few more seconds, I would just have a bonus slide for binary people. So recently we submitted a pilot study on relative astrometry for evolved binaries, and it's already available on Arxiv if you want to check. So basically we found out that for some interacting evolved systems where you have hydrogen emission lines associated with the hot companion, you can use VLTI gravity to trace at very high resolution this companion, and so you get astrometric orbit, and then when you combine this with radial velocity, you get precise dynamical masses, which is the most direct way of measuring masses for evolved stars, because you don't have to do any modeling, and you can directly measure this from the astrometry. However, if somebody's interested, please catch me later. Now let's focus on masers. Questions for Daniel? No, Hans, go ahead.
So do you have an explanation for why the SIO 6-5 and 7-6 masers show such very different appearances? I mean, they're very close in energy and...
I think in some previous studies or in modeling, they also showed that these masers in larger bands can form at larger distances. However, I am not aware that there was exactly something for this. And also the reason maybe is that usually these observations were usually in band 6 or lower, or in VLBA, which was around 50 gigahertz. So I'm not sure if there were other studies which did masers in so high frequency like band 7. So maybe there's also a reason that nobody maybe saw this before. So I'm also interested to find out why it's so different. Yeah, Shazri.
Thanks so much for the great talk, and very excited about the masses coming out. I had a question about the smaller scale structure connecting to the larger scale structure. Could it be that on smaller scales we see all of these pulsations, but eventually, and maybe this is something for the modeling people, Bernd and them, that eventually things smooth out and eventually make something more spherical at larger distances so that you can connect them, they're just part of the same process?
Yeah, it should be possible, but then depends, I think, in the larger distances, it usually gets more asymmetric, as far as I know. At least I think, so I'm not sure if it... But then on the other hand, I think here we can also see a relation of these, for example, masers that are in front. They appear maybe in the same space as these bright spots on the surface. So maybe these are related to the pulsations or shocks or convective cells propagating from the surface. So I think here we could also try to connect very nicely probably the pulsations and whether we recover some, and we recover the, some concentration of masers in the same spot. And then, yeah, depends on the large, we don't have right now data for the larger scales. And the coverage is also great, but maybe the imaging so far is preliminary. Maybe once I try more things, maybe I can recover also more, in the end, some more images that would correspond even better to these masers. Okay, so we have to move on now. Let's thank Daniel again. And now we have Miora Andrian Salaraza talking about Myra and its hotspot. I think the title is more or less that, right? I don't have it.
Yes.
Okay, go ahead.
Hello, everyone. My name is Miura. I'm a postdoc at Chalmers University of Technology. And today I will talk about our work on tracing hotspot activity on Myra using multiple ALMA observations. This work is done in collaboration with Pesad and Theo here and with Wouter Vlemens. So we have seen already during the previous talks today that high angular observations are really important in characterizing the dynamical atmosphere of AGB stars. Some examples that we have seen today showing VLTI and ALMA data that they revealed this complexity, asymmetries and structures on the stellar disk of AGB stars and even tracing the convective motions. However, what I'm going to talk about today is slightly different from these convective motions using these high angular observations from ALMA. It was discovered that there were these bright spots in these three most well-studied AGB stars, Ardor, W Hydra, and Myra. In the case of Ardor, it has been found to have a spot with a brightness temperature about 3000 Kelvin higher than the stellar disk. And in the case of W Hydra, they found a small spot of a brightness temperature larger than 50,000 Kelvin. So these are indeed hot spots. And in order to understand these hot spots, their properties, and how they affect the mass loss of AGB stars, ideally we would like to have observations monitoring these stars, given the variable nature of AGB stars. But unfortunately, we don't have that. But what we have is actually quite a number of ALMA observations of Myra A at high angular resolution that were taken for different purposes. But we have gathered them in this project to investigate the properties of these hotspots. So what we did is that we went to the ALMA archive and we collected observations in ALMA band 4, 6, 7, and 9. I think all of the PIs of the projects are in this room. We have took these epochs for band 4. We just had one epoch. For band 6, we had several epochs. We can see some of them were taken a few days apart, and some of them are more than a year and a half apart. And then we have band 7 and band 9, which are relatively new data. We have angular resolution that go down to 10.2 milliarc second. Since Myra is variable, I put here a plot of the phase of Myra. So if we look at the plot, we see that a majority of the observations were taken near to maximum light. We also have some observations down here, and also this one isolated observation here as well. So first, let's look at how Myra looks like when it is at this phase close to maximum light. Right, so if we look at first at band 9, we see that there is some asymmetry, and we see the presence of this bright spot, which is not located at the center of the stellar disk. You can see it from these 2023 observations. If you move to band 7, which were observations that were taken at about the same time, we also see these bright spots also located in the southwest quadrant of the stellar disk. But if we move on to band 6 observations, we can see here one epoch in 2021 and one epoch in 2023. We can see that the position of the bright spot has actually moved from the northwest to the southwest quadrant. Now, if we look at how Myra looks like when it is at a lower brightness, we have a slightly different picture where we don't see anymore these bright spots that were located at offset positions from the center. So here it's obvious that the spots are not as obvious anymore. So we see a clear difference between the maximum and minimum light in terms of occurrence of these spots. And then we also had this one observation that was somewhere here at the almost 0.2 phase. Do we still see a hotspot here? The answer is yes, but it is larger than the hotspot that were found when it was brighter. The star was brighter, so we have a less compact spot at this epoch. So what we did to characterize these spots was to fit the visibilities. So the method was described earlier by Behzad. So this is just one of the preliminary plots that I had, but just to show that when we fitted a stellar disk, just a disk here, we had a residual that corresponds to, well, this is one of the band 6 epochs that has still some bright residual. In this case, about 10% of the flux. And if we add a Gaussian component here, that residual is then gone. And then we use the method UV multifit using nested sampling as described by Behzad earlier, so I will not talk more about that. I will just continue directly to the results. So first on the stellar disk, we have here, sorry, the font size is quite small, but I will work through this. We have here the size in milliarc second as a function of frequency, and on the other plot we have the flux as a function of frequency. We see that contrary to what Behzad had for earlier, we have the size of the star that decreases towards higher frequencies. And then the flux density increases obviously towards higher frequencies with a spectral index of about 1.8. Sorry, and then this leads to brightness temperatures in the disk between about 2000 Kelvin as expected. Right, now if we look at the difference in time, so for the different epochs, I just highlighted here on this plot, we have the major axis observations within a few days, and we have highlighted here for phases around 0.6, so when the brightness is low, compared to what we have when the brightness is higher. And we can see there is one point here with quite large error bars, but we can see the difference in the size of the star. And yeah, observations within a few days. We can also see some little variation, even just within a few days on the size of the star. If you look at the flux again, since this is at a lower, at a phase of 0.6, these are lower fluxes compared to what we have for a brighter phase. And again, for observation within a few days, we can see some variation as well in the flux. So now characterizing the extra component, first on the flux, we also have fluxes that increases towards higher frequencies, but with a spectral index that is flatter, so 1.3. If you look at the flux ratio in band 6, we have that the flux of the Gaussian, the extra component, is about 10% of the disk. But we see as we go toward high frequency, this decreases. So for band 9, our band 9 observations, we found that the extra component is between 4 to 8%, sorry, of the stellar disk. If we move on to the size now, we can see, well, there is an outlier here that I have to investigate a bit more. But in general, all the other spectral windows for band 6 and band 7 show that the extra component, the Gaussian, is between around 4 to 15 milliarc second for band 6 and band 7. And you might notice the very large error bars for band 9. This was because we couldn't really characterize the size because the spots were so small. So the values of the temperature that we get from this will be lower limits. In terms of size ratio, we have that these extra components are about between less than 10 to almost 30% the size of the disk. Right, so here are the brightness temperatures that are derived for this extra component. We have temperatures, as you can see, that reach quite high values. So all of them are above what is expected for the brightness temperature of the stellar disk. So these are indeed hot spots. If you look at the variation of these spots with time, we have here flux density of the extra component and the size for observations of within a few days. This one observation here is, well, brighter than the other observations, even if it's just 1 day apart from the observations around it. And it's because in the visual, this is also brighter. So something is happening there. But if we do not look at that one point and see the other epochs, we see that they are fairly consistent in terms of flux and size of the extra component of the spot. So that was for a few day observations. If we now add the 2023 observations, so almost 2 years later, we can see that if we add this one point that was not at maximum, but just at 0.2 phase, we have an increase in the size of the spot, as we have seen in the images. So the spot here is then less hot. So now I talked about hotspot activity. What really are these hotspots, and what is their nature? What is their role in mass loss of AGB stars? The answer is I don't know yet. But if you recall, Theo had this plot in his presentation showing the emission around the star and how it has expanded from 2017 to 2022. I don't have the epoch for that for hotspots, but I have 2021 and 2023. And well, this expansion here is in roughly the same direction of the hotspot that I have from 2021. So maybe this is linked to shock waves. Maybe the hotspots are linked to magnetic mass ejections, or also maybe similar to solar-like magnetic activity. But we will need more data using other probes from other wavelengths in order to investigate the properties of this hotspot and their role in the mass loss of AGB stars. So I will end with a little teaser. How about hotspots in other stars other than Myra? I have said in the introduction that we have hotspots for W Hydra from Voucher's paper from 2017. Sorry, this is a typo. And now we have new AMA observations. So from this year, we have quite a few with a 1 month separation between the observations. And yesterday, Keishi talked about W Hydra continuum and said it was not very interesting. And it was because that observation was taken at minimum light. So if it's similar to Myra, then that was then expected. And since this phase here is pretty similar to what Wouter had in December 2015, we expect very interesting results that are coming up. So stay tuned. And these are my conclusions. Thank you for listening.
Questions from Miora? Yes.
Hi, Yoshiomori from Monash. That was a really interesting talk. Thank you. So you have data at maximum and minimum light of the light variability. I was wondering if you could comment or speculate on behavior on maybe like the ascent towards maximum light, those kind of intermediate phases in the light curve, and how the hotspots might behave there.
I expect that the hotspot, we have seen that one intermediate point where the hotspot becomes bigger and then less hot. So I expect it will continue and then kind of not be detectable at least anymore, and then reappear again. But we don't have the data for it, so yeah. We also have proposals, but they were rejected. So.
Yes, Charlene.
Thanks for the great talk, Mira. What if it was magnetic fields? What kind of strength of magnetic field do you need for the hotspot? I don't know if this is a fair question to you because magnetic fields, but do you have an idea of like how strong the magnetic field would have to be in order to explain that?
Yeah, no, I haven't looked into that yet. Probably Mats over there knows about it. But
what strength of magnetic field would we need to get a hotspot on a not a solar type star, but a giant? I mean, in the sun, it's 1,000 Gauss or whatever for
Working on it.
Working, it's super. Thank you. Thanks, Pierre.
Okay, I think we are on time now, so let's thank Miora again. And the next talk is by Luis Marinho, and she'll talk about molecular formation in the innermost regions of the O-Reach and C-Reach AGB stars. Go ahead.
Hello. This is a bit small. So we keep it like this, just to be sure.
Can we get a full screen maybe, or presentation mode? Okay, so I think we go on like this then if,
Like this?
it's not working yet.
Okay, I hope it will be big enough to read. Sorry. So hi everyone. I'm Luis Marino. I'm actually a postdoc in the Instituto de Física Fundamental in Madrid. And I'm going to present my work on the molecular formation in the inner region of oxygen and carbon-rich AGB stars. So this is a really recent work, preliminary, but let's do it. How it's working. Ah, okay. It's gonna be like this. So should I tell you to change the slide or? Okay.
Maybe, I don't know, Matthias, if you can re-download it, because on our side in the OneDrive, it's full screen. Maybe it's an issue of the download. Thank you.
So I guess we wait for a minute or we change Okay. So, Luis,
So I'm not
we're
there.
going to switch the talks to see if we can get yours to work.
See you later.
Yeah. And we have Benjamin Harabravo instead talking about especially resolving magnetic activity in the surface of the red supergiant VX Sagittarii. And that talk is in full screen, so then we can go with that. Ah. So we have a change. We'll go back to the original plan. We have Luis Marinho talking about the molecular formation in the innermost regions of O and C rich AGB stars.
Hello again.
I'm now.
Okay, so I was saying that I was a postdoc in Madrid, okay, and my work about AGB stars. Sorry, I need to get focused again. Okay, so even if we are talking about AGB stars for a moment now, this is really interesting stuff because they provide a very strong mass loss rate to ejections. And so they provide a lot of molecules and dust into the interstellar medium, and a lot of different species have been detected, so it's really interesting. And in my work, I'm focusing on the difference between oxygen-rich and carbon-rich stars, in which, well, in the envelope, we can see different type of molecule from oxygen material and carbon material for the two kind of stars. And when we see the chemical equilibrium models, sorry, yes, for the oxygen and the carbon-rich star, there's some molecules that are way higher than we expected from the equilibrium. And so my work is to understand why from those molecules that are listed here are different from the models. And so what kind of phenomena can explain that? My study is, for the moment, focusing on the HCN that is observed in the two types of molecules. And so for carbon-rich stars, we observe it from the photosphere. And for oxygen-rich stars, we only detect it at a few stellar radius from the stars. And it's way higher than we expected from the model. This is also the case for SIO in the opposite way, as you can see there. That's the same, that for oxygen-rich star, we detect it at the photosphere. But for carbon-rich star, we detect it at a certain distance from the star. So there is a lot of possible phenomena involved, like the photochemistry through UV field, but also through the shocks at the stellar surface. And so my work is to understand why it's formed away from the star and what can create it. I had 3 stars to work with ALMA observation that was did a few years ago. So our character is Aketau, that had all rich stars, and IRC plus 10 to 16, a carbon-rich star to compare. And so we want to provide constraints with these observations and compare them to the model to see where the HCN is actually formed and what's the difference between the two types of stars. So for that, the first step was to modelize the star and its envelope. So first we have the dust. So for that we use Dusty. So we needed a few initial parameters like the density. That was from different models. And so with Dusty, we compared a grid of different models to determine parameters such as the dust opacity, the SED, and the dust temperature at the condensation radius. So it was done for all the stars. So we have an example for Aketau here, where we just find the best model from in our grid. For the gas, I was trying to modelize the CO emission lines. So we have in different archives a lot of different lines. And so we did that with the Ratran algorithm to try to modelize all the line available that I found to determine the mass loss rate and also the temperature of the gas profile in the envelope. So again, it was done for the 3 stars to have the best model as possible and the closest to the observations.
And so we go back to HCN, which was the point. In my stars, I have the observation for the ground state line, the G423 line. That is the one that we try to modelize, except for the carbon-rich star, which is the H13CN. And so for that, I use a code, the LVG code for large velocity gradients that is developed in my group in Madrid. And so we consider that the HCN is formed away from the star. And so which model reproduces the best the observations? So we have different results in the figure presented here. So we have the intensity and the distance from the star. The dotted line are the observations, so it traces the brightness, the mean emission through different ranges from the star, so we get the mean profile. And we have different models in the color that try different distance where to put the HCN. And the vertical line is actually the size of the radio photosphere. So what we focus on is what's happened after this line. So for the first carbon-rich star, we can see that the emission starts at the stellar photosphere. Okay, that was what we expected. And for the oxygen-rich star, we can see here this little loop, kind of, for the two stars. And the model, the red and the violet, it's if the HCN is formed at 4 or 5 stellar radius. And so we see that to reproduce this typical shape, we need to get the HCN away from the star. In my observation, I got another line, the vibrationally excited one. And so here we have the ratio of those two lines, the excited one and the ground state line. And again, we compare this to different models, and we found that the best model is actually with the HCN at 4 stellar radius. And so with such constraint, what can explain that? We have different possibilities, as I said at the beginning, through photochemistry, so with a UV field. That can be either from the interstellar medium coming to the envelope, but the HCN is formed too close for the star to be really impacted by that, so we remove this possibility. There's also an internal UV field from UV radiation that have been detected around the AGB star and can impact the chemistry. And also the shocks induced where the HCN with such scenario can be formed exactly at this distance, so it's really current, but we cannot really discriminate which one of those two possibilities is actually happening. I think it's both, but we will need more model to do that. Okay. And recently, it was last week, for the, I go through the IKETAO observations, and actually we think that there is a disk around these stars. So here we have the HCN emission, and this symbol represents the peak of the continuum emissions, so that are not centered in the HCN emission. So we think that there might be a companion, maybe, so we need to explore that. And so there is also the possibility that the UV field is actually from the companion, or from the star, the AGB stars itself. So we will need to do more work on that to see which one is it. And so for my conclusions, we think that the HCNs so form away from the stars, and so that the equilibrium model is not enough to reproduce it, and we need to involve other phenomena, and that we need avoiding this distribution of HCN to be consistent with what we observe. So we have two possibilities to be implemented, the shocks and the UV chemistry. And so, as I said, this was really the early stage of work, so there's still a lot to do. So including a UV field in my observation and in my model, sorry, to be consistent with the observation, especially for IKETA, where we think there is a companion, has that been detected in many other AGB stars, and to couple it with a 3D hydrodynamic model, because if there is a companion, we will have a 3D structure that need to be taken into account, and implementing the shocks. So for that, we will need also more observations. With ALMA, it will be great. And to extend our model with other molecules, because I work on HCN, but as I said, there is a lot of other molecules that we don't fully understand, so it needs to be extended. And there was supposed to be a thank you, yeah.
So questions for Louise? Yes, Angela?
Angela Speck, UT San Antonio. You didn't give all of the details of how you used DOST and some of the choices you made, but I'm wondering whether, when you showed, so there's two things. The difference between the O-rich and the C-rich stars should have a huge impact on just the formation of HCN anyway. You've got a much lower partial pressure of carbon if it's an oxygen-rich star. And the other is that when you showed your little table of published mass loss rates, the carbon star had a much higher mass loss rate. So could you maybe comment on how that information fed into how you were modeling this with the mass loss rates and the lower carbon abundance?
So the mass loss rate was determined with the modelization. And I don't exactly know why IC plus I216 had a much higher mass loss rate, but of course this is implying the different chemistry. But what I wanted to do is to have more stars with different mass loss rates to see how the mass loss rate impacted it. And I think it's mainly for oxygen-rich star at least, not for carbon, but it will be important for where the shocks are happening, because if it's stronger, it will be at different distance. So it needs to be taken into account, but for the moment, I haven't done that.
More questions? So if no one else has a question, I'll ask a question. For RCRT, there are sphere observations of it.
Can you repeat? Sorry.
For RCRT, we have sphere observations that from a few years ago, in which you see a very like X-shaped structure, which we thought it was probably related to a binary companion. And then you talked about a binary Chuai tau, and I was wondering if you see anything weird in terms of the molecular emission around CRT that would be consistent with that.
Yeah, for this star, also in the ALMA observation, we observed this really axis emission. But it was like the peak of the emission is at the same position as the continuum. So for the moment, it was not for me obvious that there was a companion, but maybe with sphere observations, if it's the same, maybe there is one too. But I guess a lot of AGB stars have a companion, so it would be really coherent that this star also have a companion.
So if no one has a last minute question, let's thank Louise again.
Thank you.
And we move for the second time to the talk by Benjamin Harabravo on spatially resolving magnetic activity in the surface of the red supergiant VX Sagittarius. So whenever the slides are there, you can start.
Well, in the meantime, I will introduce myself. I'm Benjamin Jara-Bravo. I am a PhD student from Universidad Andrés Bello here at Chile. And my professor in charge is Professor Keiichi Naka. So, nice. So, well, a lot has been talked about mass loss. It is one of the key elements in terms of stellar evolution. It can define basically the fate of the stars. And also it is a major agent in terms of the enrichment, the chemical enrichment of galaxies. But first, if we want to characterize the magnetic fields, the magnetic field behavior in terms of mass loss and know how these fields can drive or even enhance another different kind of methods, we need to first characterize typical magnetic field levels in the stars. So here I'm showing you the magnetic field behavior of the well-known star Red supergiant Betelgeuse. As you can see that it has been calculated using mostly spectropolarimetry, magnetic fields level of the order of a few Gauss in surface. So if you follow this kind of behavior, there is a kind of periodicity in terms of magnetic field versus the time. And you can see that in principle it has a periodicity of the order of 2,000 days, which can be related in principle with a long secondary period. This means that the magnetic fields can have an active behavior in terms of stellar physics. So, how, at the moment, the magnetic fields has been calculated in the surface of the star. But what about the circumstellar envelopes? Here you can see data from Blemmings et al. In 2005. Jadlowski have already introduced you to the onion distribution of different kind of maser species. Here you can see an image, maser characterizations of the distribution of maser along the big Sagittarius stellar surface. So in this research, Blemming, they calculate the magnetic field associated to those specific detections using the Zeeman effect. And finally, if you can make a plot of magnetic field versus stellar distance and plot all the different species, you can make an extrapolation down to the photosphere, and assuming a specific size of BX Sagittarii, we can assume that there must be a magnetic field of the order of kilogauss along the stellar surface. So most of the detections has been made using spectropolarimetry, more specifically using the Zeeman effect. That is basically when a line got splitted in presence of a magnetic field. Here you can see three different behaviors, three different levels of magnetic field strength, and you can see how the lines got splitted. However, spectropolarimetry has a very big limitation, and this is the spatial resolution. As an example, you can see in the blue lines represent the spectra of the sun. The line integrated along the whole source surface with typical values of a magnetic field of 1 Gauss. However, when we move to spatially resolved observations, represented by this red line, more specifically with a spot, you can see clearly the magnetic component with similar spectral resolution. And this is clearly the Zeeman effect associated for a 4 kilogauss magnetic effect. But before to continue, just in case you're not familiar with interferometry observables, the more important, the visibility one, here I want to explain two main things to take into account for the Okay. Okay, I will continue. So the two main things that I want to explain you in terms of the interpretation of the visibility is that lower visibility tends to indicate more extended structures, and the second one is that commonly there is a correspondence in terms of the flux and the visibility. But this is nearly true mostly for ideal cases like LTE effects, but what happens when we include dynamic surface or even magnetic field? So this is something that I will show you in the next slides. So the observation were taken using the AMBER interferometric instrument from the VLTI, and you can see in the absolute curve that we have two different epochs. The minimum light corresponds to, or you can clearly identify that we have observation located at the two very extremes along the light curve, making an ideal scenario to study temporal variation. Here you can see a spectra with a resolving power of 12,000. And you can clearly identify that, well, in this plot of flux versus the velocity space, that this spectral line, more specifically the titanium, shows a redshift component in the minimum light, but in contrast, the next observation in the maximum light show a velocity shift of the order of 30 kilometers per second, specifically in the blue part of the line. But more interesting is this, that at the moment you can see that in the same position where the redshift absorption was, you can see now a kind of bump feature. So is this emission? Is this a continuum? Fortunately, we have interferometry measurements and I will show you with this. So this bump feature has something very interesting, is that the absorption and this bump feature associated has the same, or both are within the same visibility dip. And this is interesting. It repeats mostly on some, or more strongly in terms of the titanium line, meaning that in principle, both are the same element and comes from the same extension. Or press OK or cancel, please. I cannot.
There is a box on the screen. Thank you.
Thanks a lot. So the main thing is that this is a confirmed emission. So let's talk about the magnetic field, as this is in the title. All the lines are affected by these dominant velocity fields represented by this visibility dip, but more specifically in the short baseline. However, you can see this kind of scandium line that is one of the most sensitive magnetic lines that we have in our dataset. This is the only one that shows this kind of behavior of a double peak as completely asymmetric with respect to the line center of here. Therefore, we use Simon effect, simulating that there must be emission associated to those peaks, sorry. And we calculate a magnetic field of the order of 5.6 kilowatt in the stellar surface. So in principle, this must be a preliminary result. However, what happened, is this completely magnetic? Is this dynamic effect or a blend? Well, we will confirm in the next step of this work. So to make a very broadly speaking of how the project will go, we will use image reconstruction. First, we will reconstruct one image along each spectral line. With this, we will create a data cube, as you can see here, combining spectral and spatial information. From this cube, we will extract a different position along the stellar disk, spatially resolved spectra. And with this behavior, this approach combined or made a different spectral line with different magnetic sensitivity will allow us to recover the magnetic field at those specific result position, creating the first magnetic map in a red supergiant. So, thank you very much for your attention, and I will be more than happy to solve any question.
Questions for Benjamin? Yes, go ahead.
So it's not.
Oh, it's not on?
Now.
Okay. You mentioned Betelgeuse, and that was on my mind all the time when you talk about Myra. So Betelgeuse variation, I mean, red supergiant is different, but are we going to discuss Betelgeuse here?
No, at the moment, no. I have
some comments?
Yeah, I had some comments about Betelgeuse. Is that mostly?
In the meantime, I can tell you there is a conference here next year about red supergiants and supernovas, so there will be Betelgeuse there.
Very interesting, yes. So here you can see basically the main prediction that we made of kilogauss in the stellar surface. However, the red points corresponds to BX Sagittarius measurements, and the solid boxes corresponds to typical red supergiant values. And you can see that there is a kind of difference in terms of the slope of the behavior of the magnetic field, meaning that probably, or at the moment, this BX Sagittarius is the only star where it shows a dipolar behavior in the along the circumstellar envelope. However, Betelgeuse could follow this trend that not in principle or should be explained with less magnetic field. So if we made a kind of plot, there is a different slope, and assuming typical values of BX Sagittarius in the y-axis, we can get lower levels of magnetic field, probably less than of the order of kilogauss.
Thank you.
To you.
Other questions? Yes.
Hi. Thanks for the super nice talk. Just the slide before this one, where you're talking about the spectropolarimetry detection. I think you mentioned something about 1 Gauss.
About, sorry?
The spectropolarimetry detection. I mean, it was something like 1 Gauss, the magnetic field detection there.
Yes, the problem is that, no, not the problem, the limitation is
Yeah.
that magnetic fields makes an average of the whole stellar
Yes,
surface.
for this, yeah, indeed.
Yeah, and that's why, for example, in the next slide, in here
Yeah.
specifically, the sun, we cannot see the real behavior, the real magnetic behavior. This spectrum, this for you, you cannot see, but this spectrum from the spot is hidden in this contribution. However, it is not so big if we take into account the definition of flux of the intensity in over a specific area. The star spot is low, has lower intensity, and also it is smaller.
Yeah. Okay, so that explains then the 1 Gauss to 1 kilogauss or
Yes.
2 kilogauss. Okay, thank you so much.
But they have the same spectral resolution, or nearly similar. So that's why spatial result, in principle, can be the only way to detect this real behavior.
Thank you.
To you.
Claudia?
So we have a comment online by Fabrice Serpent, who mentioned that the magnetic plot from Flemings is et al. 2005, is since 2005.
Yes.
And you have several publications showing that the magnetic field is varying in 1/r and not 1/r to the third. And moreover, magnetic field at 2 to 5 stellar radii in weak Sagittarius has been estimated to maximum a few Gauss. There is a paper from 2006. So you have the comments online. Thank you, Fabrice. Anything else you want to add? If any, you can open your microphone.
No, thank you. Do you want to comment on that? Or?
Yes, sure. Yes, I have a comment on that. It is respect to the Maser distribution. Technically, all these Masers come from different detection from different papers. And there is a possibility that the magnetic field can be related with the light curve, which I'm not sure at all. But all the points from silicon, oxygen, water, and OH Maser come at different position in the light curve. So in principle, it should not be showing the real behavior of BX Sagittarii, since we are comparing minimum light and taking into account that this star has a variability very high, even compared with a Mira star. This is the bigger one. And from minimum to maximum, in our specific epochs, we have like 3 magnitudes of difference. So in principle, magnetic field can be related with that. So I'm not sure that about this recent publication of Flemings, but it can be good to take into account that.
Okay, so I think we are at time now. Let's thank Benjamin again. And do we have any announcements, or do we just go for lunch? We have announcements.
I just would like to apologize for the technical issues that we had. It's in fact related to a global worldwide shutdown of Cloudflare. That's basically shut down a lot of servers. And so the people there trying to minimize the impact on our conference. So we are doing our best and also online because we had this interruption. This is a little beep that you heard. This was a tentative reconnection of the online conference. So yeah, sorry, there is something that we cannot do.
No, I think we should thank you all for all the work you're doing. Lunch now.
Hello, hello, hello. Could everyone please start converging to their seats? Thank you very much. Okay, let's get started. So for this first afternoon session, we're going to be focusing on chemistry. We're starting off with dust and then slowly going over to the gas phase. And for our first talk, we have Beth Sargent, who is setting up. And could we, yes.
Hello. Good afternoon. I'm going to be talking about studies of alumina dust around AGB stars. So I am an affiliate at the SETI Institute, and I have a picture here of our team. So we're a lab astro team. We're, a lot of us at the University of Texas San Antonio are doing lab work, and then we're also doing astro studies. So this kind of comes off of decades of studies, spectroscopic studies in the mid-infrared of AGB star dust, going back to IRAS, LRS, but also all the missions since then, space-based like ESO and ground-based, various ground-based facilities that have found a wide range of spectral shapes for the circumstellar dust around AGB stars. Studies going back probably, I think, even before the Little Marinin and Little paper in 1990. And so people have invoked various classification systems on these studies. One that seems to be popular is the SE system that was originated, I think, with Sloan and Price in the late 90s. So in this system, SE8 is the typical amorphous silicate type profile like you find in many different astronomical environments. The question is, what's at the other end of this classification system? So different people have proposed various things over the years. Let's see, Tamanai et al., 2009, have proposed a number of things that, some of which include aluminum, like spinel and Al2-TiO5, also anatase, TiO2. Another approach was by Guha Niyogi et al., 2011. They suggested iron-rich crystalline silicates to explain various of the features seen in the spectra. So this study was something I did in 2018, where I was looking at both Spitzer IRS and ISO SWS spectra of various AGB stars. So the features in question are a feature at 11 microns, another at 20 microns, and then a pair of features at longer wavelengths, 28 and 32 microns. I believe there was some confusion in the ISO era about some of the features because there were various instrument artifacts, but the Spitzer spectra are pretty clear about those features. So this study, my 2018 study, came about doing a literature search on alumina optical constants, and I came across a laboratory study from the late 90s by Carlos Bacharaman et al., 1999. And in that study, they began with commercial samples of bayerite and boehmite. These are aluminum hydroxides. And they would heat the samples to various temperatures for various durations of time, and then characterized what they got both by X-ray diffraction and I think NMR spectroscopy, and also obtain infrared spectra of the samples. And from the infrared spectra, they derive optical constants. And so I noticed that some of the features seem to correspond to the features that we'll see sometimes in these SE1 type spectra of AGB stars, like the 20 and the 28-32 micron features. So I constructed models to fit a sample of a few dozen, 24 sources, but there were some sources were observed multiple epochs. And so this plot is from that paper where I'm fitting the different features. I have some amorphous silicates, I think it's amorphous sensitite, amorphous alumina, and then one of the samples where boehmite was annealed, and then another where bayerite was annealed. And so those are the components that are giving these 20, 28 and 32 micron features, and the blue curve, you'll notice, gives an 11 micron feature. So that's what this paper was about. To give some context about aluminum, there have been various detections of aluminum bearing molecules around AGB stars by ALMA and other facilities for AGB stars like MIRA, where they found ALO, ALOH, ALH, and other stars as well. There was a paper by Decine et al. 2017 where they were proposing specifically AL2O3 clusters of various small numbers of clusters to explain the 11 micron feature that is often seen in these stars. Okay, so there was this study using the Pacharman optical constants, but the optical constants, when they report what they characterize, a number of when the samples were heated at various temperatures, they would be mixtures of polymorphs. A polymorph is the same composition, solid, but arranged differently in terms of its crystalline structure. So in some cases, they would find mixtures of theta and I believe delta, or theta and alpha, alpha being corundum. And so we wanted to follow up on these studies by trying to produce the different polymorphs of alumina in various ways. We're trying to understand how would the alumina form around AGB stars. So we have one of our collaborators is Joe Knuth, who has a facility in at NASA Goddard to produce smokes. He's produced various smokes over many years. And also we would obtain commercial samples and sort of try to follow what Pacharman et al. Were doing, but add additional types of samples. So we have both NASA and NSF projects to do these studies. So we have obtained spectroscopy in the lab, both at mid-infrared wavelengths, where we've obtained transmission measurements for various different of our commercial samples. Here's the derived N and K from our measurements for the set where we start with gibbsite, and we also have for starting with amorphous alumina and bayerite and boehmite. And so I'm comparing the gibbsite here with the N and K from the Pacharman data. So this is mid-infrared work that we're doing, and we also are doing spectroscopy at shorter wavelengths because we want data over a wide range of wavelengths in order to be able to do radiative transfer calculations. So we have made use of electron energy loss spectroscopy, EELS spectroscopy, and this is where we are comparing our results, which are the black lines, to various published data for other polymorphs of both corundum, and I think there's a gamma alumina up here as well, and I think also some non-crystalline samples as well. We've done, and so the goal of this is to use our laboratory measurements when doing SED modeling and other modeling of actual stars. So this is using a MIDI VLT, a VLT MIDI spectrum for R Craterus. And so this is a model using 2Dust modeling code. And this is using, I think it's the Erickson et al. 1981 gamma illumina for mid-infrared, and then our data where we have annealed a smoke, an Al aluminum oxide smoke at 900 Celsius. And so that was used in the radiative transfer model. Ongoing work by our team. Our graduate students working with us have been working on different things. Michael Preston, who's just successfully defended his PhD thesis, did modeling of RT-VIR. So this object kind of has an unusual spectrum in that it's sort of a plateau from the 10 to 20 micron regions. So he used 2 different shells for this one to model the SED. Sean Dillon is working on code that will compute opacities to use for Dusty so that we can compute opacities from custom shape distributions. So here's a comparison to published data for olivine from Fabian et al. 2001. And on the bottom right, this is where we're doing characterization of samples that we've formed, that we've produced in the laboratory. This is work by Cody Cly, X-ray diffraction for bayerite, heated to various temperatures. And you can see the X-ray diffraction pattern changing as the temperature increases. So conclusions. This series of 11, 20, 28, and 32 micron features are well matched by these non-corundum or non-alpha polymorphs of alumina, also known as transitional aluminas. And so we're employing measurements at optical short wavelengths and mid-infrared wavelengths to try to get optical properties over a wide range of wavelengths. So one thing that we seem to find is that there are annealings that tends to produce a wide variety of the polymorphs. And for a little more on processing of dust, stay tuned for Angela's specs talk right after mine. Thank you.
Thank you very much. Time for questions. Anyone? Okay, I'll go first. No? Who had a question? There, to you. Yes.
Hi, so very interesting, all these transitional aluminas that you're talking about. How do you expect the spectrum to vary as a function of time? Should all these species be there as the star pulsates, or will these emission features vary depending on, as a function of time?
So that's an interesting question. The Guha-Niyogi paper that I referenced looked at, I think it was TCEF, and there were ISO SWS spectra for that star, and it was like 7 or 8 epochs. And this is late 90s. And you can actually see some of the features changing, like the 13 micron feature, which I fit in the models, or we fit in the models by corundum. That one seems to, if I recall, the strength was kind of varying over the course of a light curve, a period. And I think you could see some changes in some of the other of the features that I'm talking about also over the period. So there is some change. All of the features seem to be there over the whole period, but the strengths kind of changed.
Okay, any other question? We have time for another quick one. Okay, then I'll go myself. You mentioned that for RT-VIR, there was like a fitting model with 2 shells.
Right.
So is that also in any way spatially constrained by anything that we see? For example, the sphere data are also RT-VIR, right? No? No, then not. But are there spatial constraints on those?
Yeah, so I think in that case there's far infrared, like 70 micron data for RT-VIR, and you can see the emissions kind of go tens of arc seconds, I think, away from the star, and that's sort of in the ballpark scale of what was predicted by Michael Preston's model for that star.
Thank you. Okay, then let's thank Beth again. And as already highlighted, we're going to hear a bit more about processing of dust now by Angela Speck. So please take it away.
Okay, it's almost there. All right, so thanks to Beth for introducing our team. And so this is a mixture of observational astronomers, lab folks, material scientists, volcanologists, the whole gamut. What I'm going to talk about is how we get crystallization, because we do see crystalline materials around AGB stars, and this is just a novel ways of doing this. So I want to start with just thinking a little bit about the dust, and this is definitely oversimplified, but what I really want to get to here is that you have dust that's forming, and what forms is going to depend on the density and the temperature, and as well as the chemistry. At the same time, you also have things that are forming clumpy stuff, and so that's going to have an effect on what's able to form. You also have the pulsations and the shocks that are going through that we've already heard about today. You also have, in some cases, the star itself moving through the interstellar medium fast enough that we see a bow shock. In fact, in that Herschel image of RT-VIR, we see a bow shock. And so there's lots of places where you can have interesting excitation and how that changes across the system. Beth already mentioned this, so I'm going to skip over it. Basically, one of the things we care about is the polymorphs, and so just understanding that things can have different crystal structures. But we also have crystalline versus amorphous. Most of the time when we say amorphous, what we mean is a glass. That is, you have very short range homogeneity. That is, if it's a Forsterite composition, you've got a little Forsterite unit, but the one next to it is kind of not at the right angle. Or you can have things that are like nicely aligned, but you can have those alignments in different ways and get different polymorphs. You can also have things that are single crystals, that are mixtures of crystal grains, that are mixtures of different compositions of crystals, and that also have glass in them. And all of those are going to affect whatever spectra we look at. And when we look at the spectra, what we see is something that goes from something that looks a lot like the classic 10 micron silicate feature, and as we get more crystallinity, we see more of these sharper features. This is actually annealing data where a glassy sample was heated up to see what happened as you heated the sample. And this is just a zoom into one of Beth's view graphs, in fact, from her paper. But what I want you to see here is that the alumina polymorphs, you can see this is corundum, so this is the most stable form of alumina, but we've also got amorphous, so this one here that's a dot dash, it's also a dot dash here, that's just a temperature difference. That is an amorphous alumina. We also have this one here that's kind of bumpy. That is one of those annealed samples that Beth was talking about from the Pesharman data. And those are showing us what sort of different features we can get from different polymorphs of alumina. So the first thing I want to talk about is not about alumina, it's about something called recoalescence. And what I'm going to show you is a video, okay? So what you're looking at is, this is a platinum crucible full of lava. And as it cools, I want you to see what happens. Okay, you see there, it started getting hotter again. So we started out with something that was cooling, and then it got hotter again. This is what we mean by recoalescence, literally get hotter again. And this has to do with the fact that a crystalline structure is more thermodynamically stable than a glassy one. And so as you crystallize it, it releases energy. This is, I just put this in case the video didn't work. So this is just a static version of it. The point is that as you start to see that, you can see it propagating through.
And so what you're seeing here is this graph is just showing you temperature versus time. Don't worry about the bottom one. That's not a mineral that's likely to form in space. But this one is, basically, it's got some iron in it, but it's a pyroxene. And you can see here, as it's just cooling off, and then it gets to here, and the crystallization kicks in, and it gets hotter. The solid line is where it was basically the changes looking at the whole of the surface area of the crucible, so as you're looking down it, and the dashed line is where you're just looking at a small piece of that. It's a few pixels, okay? And what you can see here is that as you get to here and it crystallizes, the temperature changes by 150 degrees Kelvin. And so as you are cooling your sample and it's going to crystallize, and then it's going to heat up. And so your crystals are going to be hotter than your surrounding amorphous material. Now, this is something that we can measure. We can measure how much energy is coming out. This is done with calorimetry. What we're looking at here is, if we start at this end, we've got, it's cooling, and as it cools, it releases energy because of crystallization. But we also get that as we're heating up. So this is where we've got a sample, we're heating it up, and as it crystallizes, we also release energy. This is where we're taking in energy in the red to melt it. But the point is that the area within those peaky things, that gives us the amount of energy that's released in this. So we can quantify this in the lab. Now, how does this relate to AGB stars? Well, what I've got here is a pressure temperature diagram. It's temperature on the Y, pressure, log pressure on the X. What it's got in the blue and green lines is, this is basically the formation temperature for thermodynamic equilibrium for forsterite and enstatite, so magnesium-rich silicates. The gray area in the middle, right here, is showing you where it would be a glass. So up here, you would form something crystalline. Down here, it's going to form something glassy and amorphous. This flow here that you're showing, this is what we calculated for TCEF, which we basically use just the expansion velocity and mass loss rate that's published, and the range has to do with different publications. And this then gives us an idea of where the dust should form. And so you can think of it as being, it should form down here where it's going to form something glassy. But imagine that this thing, you've got all sorts of things going on. You've got shocks going through. You've got the star, it's forming dust when it's coolest, and now it's getting hotter again. You heat that stuff up, and you can crystallize it, and it can increase by 150 degrees. And so now you've got something that's going to be much, much brighter than the surrounding material. I'm not going to go into that. You can ask me questions. The point of this one was that basically, flux goes as T to the 4. You don't have to have a difference in the temperature that's very much to have a difference in what you're going to see. And so it's possible that for AGB stars, we're able to see crystalline materials because they get hot, and then we can't see them again when we're looking at them, say, in the interstellar medium. Okay, there's another mechanism I want to get through, and I only have 5 minutes. Thankfully, Beth did most of the work for me. So she already mentioned Joe. This is Joe in his lab, and this is where he makes these chaotic samples, and that's his dust-generating machine. Basically, he throws in hydrogen gas, a bunch of metal-bearing molecules, and he's basically using a flame to make these particles, and then we can play with them. And we've done both annealing, so we've taken these particles where basically he threw in stuff to make something that's aluminum and oxygen, so something like alumina. And then what we see is that if it's not heated up at all, it's completely amorphous. And as we heat it up, we're getting crystalline materials. This is similar data to what Beth showed. What we've got here is there's no features, it's completely amorphous. This is a specific crystal structure that is the eta alumina, and then here we have the alpha, the corundum, and that's what's happening as we change the temperature. I'm not going to go into all the details, but here's what you're seeing in an electron microscope where these rings indicate those crystal structures. Now, the other thing we did was we used an electron microscope. What we discovered was that as we put our smokes that are more amorphous than amorphous, they're messy, they're chaotic, we start to see crystallization just from the electron beam, okay? And so what you're seeing here is this is what you get from the electron beam. The top left, what you're seeing is basically no structure in here. It's no crystals. Here, there's still no crystals. There's one little spot there that says that you're starting to get some sort of crystal structure forming. And then it's hard to see on here, but you can see some more. And so as time goes on, as we're exposing it to more and more longer and longer time scale of the electron flux, we're seeing more and more crystal structure. And what we get is that this is now that eta form. What we found is that even if we keep illuminating it, we just make bigger crystals of eta alumina. We don't go as far as making the stable form, which is corundum. Just to show you that this is showing you whether we did this by annealing the smoke, so heating to 1,000 Kelvin, that gives us that eta alumina and not yet giving us corundum, or we do it through electron irradiation, we get the same material. This is important because in the electron irradiation, the sample is very, very small. We want enough of the sample to be able to take spectra. And so we can make it in different ways and still take spectra of it. Okay, and so what I want to finish with is basically, we normally think about crystallization in terms of annealing, but there's two different ways that we can use this. One is, annealing is just the heating, but also then the recoalescence effect that I talked about. The other is electron irradiation, whether the electrons are coming from, there's a poster on maybe having some weak plasmas around AGB stars. We heard about the hotspots. There are places where we're going to get some electrons. This is probably going to be more effective as we get into the planetary nebula phase where there's a lot of electrons. But we also have that once you start the process of the electron flux is making the crystallization happen, now you're starting to crystallize, you're going to release energy so you can then propagate it. So it may be something that the electrons start it and then it can propagate through all of your grains. And these are things that we really haven't considered when we're thinking about our models of what's going on in the dust around AGB stars. And I'm going to end there. Thank you.
Thank you very much. Questions? Yes, you can.
Hi, Angela. Thanks for a great talk, although confusing for me. But so in the very beginning of your talk, you had this image where you showed the inner wind all the way out to the bow shock. Do you expect the dust grains to change significantly from the inner wind out to and including the bow shock?
So that's a really good question. What I would say is yes. How you test that gets a little trickier. So just thinking about it in terms of the evolution of a star and what the timescale is for getting out to that edge, you might, depending on the timing, there might be something like a third dredge up that then gives rise to a change in chemistry, in which case you would absolutely see a difference. You also saw that I had a gradient through where you're going to form the oxides closest in, and then as you move out, you're going to form some silicates, but exactly which silicates is going to change depending on the chemistry and the density and the temperature. You can also have really interesting effects where as you deplete from the gas certain elements, that will change what forms. And so that's also something that may give you a stratified structure throughout. Beth mentioned Michael Preston's dissertation work, where his outer shell was entirely made of alumina. In fact, it was the theta alumina. And the inner shell had all of the more common features in it. So I would say yes, and I can justify why that might happen theoretically. Hard to actually get the observations up.
More questions?
Hello, I'm Marie from Lion Observatory. Thank you for the very interesting talk. I was just wondering, like, when you heat up the dust, again, as it crystallizes, would that affect any, the chemistry on top of the dust? And if you're still accreting as a dust grain, how does it affect the composition or the layering? Do you have any thoughts?
I think this was our conversation at lunchtime. Sort of. So what I would say is, if you're, it depends on what's forming on the outside, right? And so if you've got something that is going to be destroyed, and we heard about how you have fallback and grains being destroyed, then yes, the heating up might cause that to disappear. You're also going to get probably a gradient just because once you've formed your materials and it's far enough out that you can start to incorporate new things on it, that's also going to be happening anyway. If you want to find out more about that sort of thing, I would go to Alan Whittington's poster. He's going to do his flash talk this afternoon, but he's the volcanologist, so he understands this stuff better than I do.
Thank you.
Okay, thank you very much. Let's thank Angela again. And then we switch to Marie van der Zande, who is going to tell us about chemistry throughout the AGB outflows.
All right. Let me figure out what goes in which hands. Okay, so first of all, I'd like to thank the organizers for inviting me to be here. I'm very happy to be in Santiago and to talk to you about the chemistry behind AGB outflows. Because I'm not going to talk about the star, I'm only going to talk about the outflow. That's where all the interesting chemistry happens to me, at least. And of course, we know that these AGB stars are characterized by lots of mass loss via a stellar outflow. Everything that the outflow is launched by dust formation, more specifically pulsation enhanced. Well, it's a pulsation enhanced dust-driven wind. We've already heard a lot about that. But it's the outflow that strips a star of its outer layers and can do so quite efficiently. So mass loss rates between 10 to the -8 and 10 to the -4 solar masses per year. That's a lot. In fact, it's so much that it's this process of mass loss that determines stellar evolution. Thanks to their outflows, these AGB stars are very important to the chemical enrichment of the interstellar medium, so why galaxies care about them, I suppose. About 80% of the gas, 35% of the dust comes from AGB stars. And if you look at just newly formed stellar dust, they're thought to contribute about 70%. So let's take a closer look at the outflow and all of the chemistry that can happen inside of it. So here it's a schematic. On the left, you have a bit of an AGB star and then the outflow surrounding it. And the outflow can be divided into 3 main regions. And each region is characterized by their own chemical and dynamical processes, and they are very tightly coupled throughout the outflow. So in the inner wind, close to the star, the chemistry is taken out of equilibrium because of shocks caused by these stellar pulsations. And then a bit further out, we reach the region where dust is able to condense from the gas phase. So this is the region where your material is accelerated away from the star and drives your outflow. And then finally, in the outer region, your material reaches its terminal velocity, 5 to 25 kilometers per second. And the chemistry within this region is a very rich photochemistry. The densities are much lower at the outer end of the outflow, so this means that the interstellar UV radiation field can more easily penetrate this region and create a very reactive soup of atoms, ions, and molecules. Now, I'd like to highlight just First, I'd like to say that the chemical composition of your outflow all depends on the elemental carbon to oxygen ratio of your star itself. So C over O ratio larger than 1, we have more carbon than oxygen. Now, carbon and oxygen really enjoy being carbon monoxide. So all of you can assume that most of the oxygen will be locked up into CO, leaving behind only carbon. And then similarly, if you have a C over O ratio smaller than 1, you will have an oxygen-rich outflow. It's all thanks to carbon monoxide, well, mostly. Right. So I'd like to highlight just the large gradients we have within these outflows. So we go from a very dense, hot inner wind to a tenuous, cold outer region. And it's because of these large gradients that we have such a rich chemistry throughout the outflow. We have 3 distinct types of chemistry, all within one object, so that's quite unique in astrochemical terms. And this also includes dust formation, so it's thanks to these large gradients. And AGB outflows aren't just rich in types of chemistry, it's also rich in chemical composition. Some 15 types of newly formed dust grains have been detected. And if we look at the molecules, some 100 molecules have been detected in AGB outflows. And that's roughly 1/3 of all the molecules detected in space. So they're very rich chemically. Now, studying the chemistry of AGB outflows isn't just by doing observational studies, which molecules are where, etc. That's something that Thaisa will talk about more tomorrow. But in order to understand why we have some molecules present and why some molecules aren't, we have to use chemical models. And again, we can distinguish 3 main groups. So you've got chemical models that are geared towards the chemistry in the inner ring, so the non-equilibrium aspect of it. Then the more common chemical model of an AGB outflow is a photochemistry model. That's a gas phase only chemical kinetics model, really valid for the outer regions. And then over the past few years, I extended such a photochemistry model to include also dust gas chemistry. So gas phase species can accrete onto the dust and form little reactions on the dust grain as well. Now, for the rest of my presentation, I'd like to talk about how chemistry is essential to study the outflow's driving mechanism. For that, I'll talk about dust formation, but also the shaping mechanism, and I'll go a bit deeper into companion-induced structures. And I would like to end by taking a deeper dive in the uncertainties of the model as well. So let's start with dust formation. So there's several ways in which you could study dust formation in an outflow, but first, sorry, I'm all over the place. I'd like to highlight that dust understanding stellar evolution is actually a chemical question, because it's the process of dust formation that launches the outflow, and it's the outflow that kills off the star. So if we don't know how dust is being formed, we don't know the evolutionary timescales. And it's not just a chemical question, it's also a kinetic question. So we go from gas phase monomers that chemically react and form larger gas phase clusters that then reach a certain cluster size that condenses into a seed particle, which can then grow by accreting more gas phase species. But just solving this issue is quite complex because we don't really know which monomers we should include and also exactly how they cluster together. That's also lots of question marks around it. So it's a chemical question with still a lot of open question marks. And if we don't understand how dust is being formed, we don't know stellar evolution really, but also we don't know the exact dust composition or the grain size distribution of all the material that's expelled into the ISM. So to study dust formation, you can take different approaches. And for the carbon-rich outflows, you have the nanocosmos team that built this huge stardust machine. So that's outflow in a tube, 7 meters long and not 20,000 AU long. So that's much more compact. And by doing this, they can mimic a carbon-rich outflow, so dust formation, including processing in the ISM. And this is one of their results. So by including C2H2, acetylene, to abundances that are more comparable to what we actually find in a carbon-rich outflow, you see that much more dust grains are being formed. So that's in the bottom panel. They also have a different size distribution. We have more smaller grains and more larger grains, and they go from tiny dots to being quite porous little creatures. So you can do this in the lab if you have a lot of money and time and expertise. So for oxygen-rich outflows, we've been taking a complementary approach, which is by combining observations and theory. So this, here on the left, we have AlCl, on the right, aluminium fluoride around W Aquila. You can see that these molecules are present quite close to the star itself. Now, this is work by Thaisa Danilovic, and together with Tom Miller and John Plain, we really try to reproduce these abundances that we find. We tried, but I wouldn't really say that this is a good fit. So here on the left, you have in black AlCl, on the right ALF. The dotted line is a retrieved abundance profile, and the solid line is what was our best model. So you see that AlCl and ALF are present very close by to star and then drop off quite dramatically. And that's something that our model can't reproduce. So in our model, which is gas phase only, AlCl and ALF are destroyed by interstellar UV photons. So our envelope is much, much larger. So the fact that we can't reproduce this quite short lifetime of ALCL and ALF means that probably those molecules are going into dust. But that wasn't included in the chemical model. If you want to do that, you have to go to a friendly theoretical chemist and ask them to calculate all the different cluster configurations which are stable, how you can go from one to the other. It's quite a lot of time, quite a lot of energy that's being spent to create these clustering schemes, and then you can go ahead and include that in your chemical model. So in short, I think it's safe to say that dust formation really needs an interdisciplinary approach, a very astrochemical approach, observations, chemical models, and laboratory experiments. And there's also all these other things that I didn't talk about, like Angela's work, for example, that's very complementary. And then we also can look at pre-solid dust grains. Now, we don't know how the dust is being formed. Well, we've got some clues, but we do know that it's there. And if it's present within the outflow, well, that's something that I did in a dust gas chemical model. So I just assume the dust is already there. I start my model after it's formed. No worries, we can continue. And here I show you parent species in an oxygen-rich outflow. The dashed lines is for gas phase chemistry only. The solid lines is when I include dust gas chemistry. So this is a dense outflow with cold dust. So I'm really making it very favorable for gas phase species to accrete onto the dust grain, which is something that happens for some species. For example, water, here in red, really enjoys accreting onto the dust and forming an icy mantle, so 5 orders of magnitude of a decrease here. And SIS and SIO also tend to go down by 2 orders of magnitude, which is somewhat in line with what has been observed for such dense oxygen-rich outflow. So actually, by looking at abundance profiles, so not just abundances, but really the profiles throughout the outflow, we can also say something more about the dust that is present within such an AGB outflow. Also, because the type of dust and its grain size distribution also determines a little bit the depletion level of your gas phase species. So if you go back to this picture of the different types of dust grains, chemical models, I think it's safe to say that including dust formation is a missing piece in the puzzle for us to get a chemical model that covers the entire outflow. And this is something that I'd like to tackle from next year onwards with my ERC starting grant. So hopefully in 5-6 years, we'll know more. Right. Let's now move on to the second part of my talk, which is companion-induced structure. So I think we've heard it already many times, and we will hear more about it in this conference, that most AGB stars aren't alone, but have a companion. And if your companion can be a star, can be a planet, these companions can really shape the outflow into a more complex structure. Now, it's quite difficult to find these companions because, well, the AGB star is producing all this dust. It's also very bright, so it's difficult to directly detect them. But if your companion is a star, it will have a radiation field. And this can really affect the chemistry throughout the outflow, because now you already have photochemistry in your dense inner wind. And in fact, we found that there's several chemical traces of hidden stellar companions, depending on your type of outflow. And this has been applied already to IRC 10216. We know that this star is probably having a companion because of all the shapes, but we haven't found it yet. And Mark Siebert went in the ALMA archive and found HC3N close to IRC 10216. And HC3N, abundantly present close to a star, is one of these chemical traces of a hidden companion. So chemistry appears to suggest that its companion is a solar-like star. And when it comes to X-ray radiation, then we'll hear more about that later by Alonso Hernandez. Right. Another nice example is SIN around W Aquila. So W Aquila is one of these stars which has a known companion, solar-like companion, and SIN is one of these molecules that we again predict to be abundantly present close to the star if there's a solar-like companion. And as you can see, there's some emission very close to the star, but it's only in a wedge. And if you then take a PV diagram of that wedge, you see that there's an arc. Now, I'm sure that Thaisa will talk about this a bit more tomorrow, but she interpreted this arc as a tracer of a highly eccentric orbit. And by using this SIN emission, she devised an astrochemistry-based method to constrain the orbital parameters, so combining observations, chemical modeling, and hydrodynamical modeling. But this already shows you one of the main constraints of my model. My models are mostly one-dimensional, and that's not one-dimensional, that's a wedge. I can predict that it's supposed to be there, but I can't predict that it's a wedge. So we really need to go into 3D. And ideally, we'd like to compare all these wonderful hydrodynamical models to observations. But the issue is that hydrodynamical models give density as an output. And in order to compare densities to observations, you first need to calculate the chemistry to get an abundance. And then you can do radiative transfer modeling to compare it to your observations. And you can do this for CO because it's relatively, well, and CO enjoys being CO. It doesn't really do a lot of chemistry. But for everything else, you need to calculate the chemistry. And that's non-trivial since, okay, chemical model doesn't take a lot of time, but if you have to do it all of the time in your hydro model, it's becoming unfeasible. So I really think that 3D chemical and hydrochemical models are essential to bridge the gap between theory and observations, because we already have all these wonderful observations of all these molecules. Now, there's two ways in which you can go about closing the gap. And one way is to post-process your hydro simulation. So you take the density, temperature, radiation field, and you then feed it into a chemical model. And that's something that's being done in the star formation community, and also that one of my master students is working on at the moment. But if you want to have a hydrochemical model, so having the link, I think we can take a look at machine learning and use, because if we emulate rather than calculate the chemistry, you can really significantly speed it up and couple it to your hydro model. That's something that Camille Landry will talk about more tomorrow, I think, yes. And now a bit more hypothetical when it comes to companion-induced stuff. So something that Thaisa found in the atomium sample is that, well, maybe there is a second pathway of dust formation, namely companion-induced dust formation. Because as your companion moves through the outflow, it creates a wake, and in this wake, dust could form. Because again, we're compressing material, etc., etc. And this is Pyron Grue. As a known companion, you have this tail moving away. We will hear much more about this system of stars throughout the outflow, not the outflow, but the week. I just want to raise some questions about how this binarity could actually affect the amount of dust that's being formed. And if you form it close enough to the star, it could also affect the mass loss rates that we retrieve. And then if you look at this scheme of how aluminium oxide clusters together, if again your companion is a star, its UV radiation field could really mess it up potentially, could improve conditions and make dust produce more quickly, but could also just really blast apart some of your clusters. So maybe it has an effect on the type and the amount of dust formed if you have a stellar companion. And then finally, I'd like to talk about the mantles, the refractory organic material that you could form on the dust grain. So this is something that we include in our chemical model, where your complex ices could be photoprocessed into refractory organic material, so a bit like a sticky goop. This is one of our initial results, where this is a sample of carbon-rich outflows. So you have mass loss rate versus outflow velocity, and the column map shows you the refractory coverage of the dust grains. And as we increase in mass loss rate, we can reach coverages of like a few percent. So not a lot, nothing significant, nothing that's going to affect the interstellar medium in a significant way. But this is just a very simple outflow, smooth outflow, nothing special going on. And over the past few years, I've included some other things in the model to make it a bit more complex. And one of these things is to include a porosity formalism. So in this way, we can act like our one-dimensional model is a three-dimensional model. So we squeeze it into different clumps, etc. So this is one of these results. It's quite a busy plot. The solid line is the coverage that we have just from a smooth model. And then if we squeeze things together into clumps, we can see that we go from a few percent to up to one monolayer of refractory organic material. If you include different companion stars, like a solar-like companion, a white dwarf, you can again amp up the refractory coverage. So at least like 10% or a few tens of percent of coverage for high mass loss rates. If you go to lower mass loss rates, the situation is very different, and actually we can completely clear off the refractory organic coverage because, well, lower mass loss rate, not a lot of extinction, and your companion just zaps everything into atoms and ions. But I think Matthias will talk a bit more about what happens to the dust as it moves into the ISM. It could be coated, could not be coated, I don't know. JWST would be nice. Right, and now I'd like to talk more about the model itself. Because the results that I've shown you are all very nice, thin lines, or just a point, no uncertainties. We don't talk about those, but we should. Because actually what goes into a chemical kinetics model, well, I take a density and temperature profile, and then the main thing of any chemical model is a chemical reaction network. So there's a list of all the reactions that you include, of all the species that you include, so how they can interact with each other. And each reaction has an associated rate coefficient. Then you calculate your coupled sets of ODEs and you get some predictions out, in my case, abundance profiles and column densities. So that's the most simple chemical kinetics model for an outflow. And then I included more complexities such as dust gas chemistry, a stellar companion, and a porosity to mimic a 3D outflow. So that's a lot of inputs. And over the past few years, I've been taking a look at like what happens. So silicon mass has wiggled around the density and the temperature to see how it affects the output. It affects it somewhat, a little bit, yeah, not negligible. And then these three guys, a mess. Lots of degeneracies. Yeah, thank you. Different inputs can give you the same output. So that's part of the 2023 paper. But then the big elephant in the room is your reaction network, because all of these rate coefficients have an error. And I use the latest release of the UMIST database for astrochemistry. So that's 8,760 reactions among 737 species. And each of them has an associated error. Now, in UMIST, we divide it into 5 categories of uncertainty. So we've got A, B, C, D, E, factor of like 25%, 50%, factor 2. D is a factor 10, and E is like no clue. Fortunately, this is just 4 or 5 reactions, so that's fine. And then we also divide them by the method in which they have been obtained. You've got measured, calculated from the literature, and then an estimate. So most of the measured rates have quite a low uncertainty, so 25%, but most of our rate coefficients actually have an uncertainty of factor 2 to a factor 10. So how would these uncertainties influence our model predictions? Like if we put garbage in, do we get garbage out? And maybe some rates are absolute garbage, but does it actually matter? Do they actually influence your model results? And then from a personal point of view, all these complexities that I've been adding, does it matter, or is it all hidden within the uncertainty? So I used a Monte Carlo sampling method to determine the effect of the uncertainties. So you've got your standard rate coefficient, and I then assume it's log normally distributed, and that the width of your distribution is correlated with the uncertainty on your rates. And I then take 10,000 samples, so I create 10,000 reaction networks, 10,000 models for carbon-rich and oxygen-rich stars at different mass loss rates. So 10,000 models for one chemical model. Fortunately, it only takes 2 to 3 days, so it's much more than 20 seconds, but it's not 6 months, so it's okay. And these are some of my results. So also this was accepted yesterday. It's on arXiv today, so if you want to know more, go on arXiv. So here I show you the parents in an oxygen-rich outflow. And the shaded area is the error on your envelope size. So some are quite well constrained, like H2S, for example. Some CS, just like could be anywhere. This envelope could be anywhere, according to the chemical model. And interestingly enough, I find that the error on the mean envelope size isn't because of the error on your photo dissociation rate, because that's the same for all molecules. Instead, it's caused by the chemistry reforming the parent after it's been photodissociated. So if you just use a very simple photochemical model to estimate envelope sizes, beware, you're not taking the actual error into account. Interesting molecule is CO, so there's quite a spread on the envelope size. And we ran it through radiative transfer model. We find that this spread in the CO envelope leads to up to factor 3 of difference in mass loss rates. So not dramatic, not negligible, but also if you're going to use a more fancy way of treating CO photodissociation and self-shielding, maybe that's not necessary because that's like 30 to 50% max of a difference. That's a factor 3. So I don't know, you could make your life easier and not do it. I don't know. Fine. Here are some results for some data species, the carbon-rich outflow. And again, there's a wide range in uncertainties. CN, for example, is quite narrow, but something like C3HCCH here on the right, that's just 2 orders of magnitude of an error. And interestingly enough, the error doesn't necessarily grow throughout the outflow. It doesn't accumulate. And that's because, well, it's a gradient of density and temperature. As we move throughout the outflow, we've got different sets of ODEs, so that reflects that a little bit. And do we need a more complex model? Sometimes. I can go into the details later. But here is our little table of the least and most uncertain data species. Just want to say, observer beware if you're using a specific molecule in chemical modeling to retrieve physics. Some molecules are a bit better than others from a chemical point of view. And in order to determine which reactions contribute the most to the uncertainty, you have to do a sensitivity analysis. And that's what I'm doing now. There will be a guide for experimental work. And even though 2 or 3 days might not be a very long time, it's still annoying to do. So Gijs Vermarie in Leiden is working on speeding this up by using a differentiable solver. So now I've reached my conclusions, semi in time. So AGB stars, important contributors to the chemical enrichment of galaxies, and chemistry is important to understand dust formation, can also help us interpret all these large-scale structures, but beware, there are uncertainties, and maybe we should all take a more critical look at our models. Thank you for your attention.
Thank you very much, Marie, for a nice overview. Questions? Yes.
Hi, Marie, thank you. Ana Escorza from Tenerife. Did I understand correctly that you can differentiate a main sequence companion from a wider companion from a non-companion just by looking at the chemistry of around an AGB star?
Yeah, you can do that, especially like a solar-like companion has the strongest effect. A white dwarf, that it's white dwarf, red dwarf almost has no effects. But for a smooth outflow, you can see already the effect of a solar-like companion and a white dwarf in the higher mass loss. Yeah, you can just see that for a smooth outflow. You can, if you use a porosity formalism to mimic these structures, you can definitely also, you can quite clearly see that some molecules disappear, other molecules pop up. So yes, you can use chemistry to distinguish these companions.
Cool. Why are we not doing this for all targets?
Yes,
What do you need?
Yeah, so indeed, if you're observing a star, maybe not look at just the usual suspects of CO and SIO, etc. And yeah, Taisa and I submitted a large program last year, but we will resubmit it this year. Let's put it, yeah, we'll try again.
Cool, good luck.
Thanks. Okay, next question for Leen and then an online question.
Marie, great talk to
Thanks.
keep us awake after lunch. What a nice piece of energy. I have 2 questions. First of all, you also said that one of the reasons for studying the uncertainties is also understanding the reactions that we just can neglect. Can you give us an answer on what fraction of the reactions can we just neglect so that we can simplify our networks?
Yeah, so for the sensitivity analysis that I'm doing now, I can determine which reactions contribute most to the error. But of course, all reactions, well, maybe not all, but it doesn't say, it's just how much they contribute to the error, not to the result. So that's an important distinction. But when it comes to how much they contribute to the error, it's about 80% are not statistically relevant for the error. So you can really whittle it down. But because it's almost 9,000 reactions, the relative contributions of one particular reaction is quite small. So I'm not sure if, yeah, that's something that I'll do in the next step, So I'll determine for each, because that's another thing, it's an outflow. So for each molecule at each radius, you could have a little list of reactions which are most important. So I'll begin a little bit with those.
And then the more open question, you're thinking about the known unknowns. What about the unknown unknowns?
Yeah, that is indeed something you need to think about what you don't know. That's also why I did the uncertainty analysis on the simplest model. It's a gas phase only, smooth outflow, and I treat everything else as a complexity, just also to see if this complexity is needed. But then if we have a better grasp on the simplest case, then maybe we can also know what we know and know what we don't know, because maybe we've been biggling things too much. Like, for example, the cyanopolyones in irocetin 216, I don't think it was needed according to the chemical model. If you include the uncertainties, everything just blurs into one another. So yeah. Unknown unknowns. Right.
So we have a question online, first by Wout Gezert. He writes, impressive talk, Marie. And his question is, for fixed CO ratio, does the chemistry significantly change if you go to low metallicity, or are the yields of molecules dust just lower? Thanks and greetings from Leiden.
Yeah, hello Wout online. So yeah, this is all just for a galactic AGB star. I haven't really modeled any extra galactic lower metallicity stars, but we do know from dust yield, well, they still produce dust. Just depends, that's other people know more about this, of course. They still produce dust. They still have molecules, but exactly how much that's different that I don't know immediately. But yeah, they still produce dust. Only when you go to really high redshift and you run into problems with the chemical composition, that's something that I'd like to look into in the future as well. So yeah, stay tuned, I suppose. Yeah. Right.
Was there another question online? No, I think we also covered our time. So let's thank Marie again. And then for our next talk, we have Ramla Krishnan, who is going to talk about chemistry around a sample of carbon-rich AGB stars.
Yeah. Hey everyone, I'm Ramla Krishnan. I'm a final year PhD student at Chalmers University, Sweden. I'm planning to defend in around 2 months from now. So for the past few years, I have been looking at the circumstellar chemistry of carbon-rich AGB stars. And the one good thing about starting your talk just after Marie is that I don't need to introduce circumstellar chemistry anymore. And so I have been mostly looking at line emission using ALMA. And it seems that there is a debate going on here since yesterday whether the AGB continuum images with ALMA are boring or not. But as you can see here, whatever we decide on the continuum case, we can all agree that the line emission is anything but boring. And so I'll jump right in and start here. So this is a list of all the molecular species that has been detected in in AGB CSCs so far. So it's more than 100 molecules. And you can see it's from very small like diatomic species to very complex carbon chains. So it is in this sense that we say that AGB CSCs are an astrochemical laboratory, if you will. And most of these species, especially the complex carbon ones, they are found in carbon-rich AGB stars. So in this talk, we'll be focusing on carbon-rich stars. So speaking of carbon stars, to begin with, what we should note is that the most of the things that we know today about these kind of objects is from this one particular object. It's a nearby high mass loss rate, very bright carbon star called IRC 10-216 or CW Leo. So it's one of the most observed objects at many different wavelengths. And you can see here there is a lot of continuum, a lot of lines, spatially resolved emission, all sorts of things. And this star has been very well studied. And so most of our chemical models of these kind of objects are fine-tuned or calibrated on observations of this object. And in my PhD, what we try to look at is if this star is really representative of carbon stars in general, or how unique is IRC 10260. So we wanted to test the archetype status of this object, which is often given to it in the literature. So we started by choosing a sample of 4 other AGB stars. So these are also carbon-rich stars, and in some sense, they are all very similar to IRC 10216 in that they are all very high Maslow's race objects, but they have some diversity in their carbon-12, carbon-13 ratios, which could point to different evolutionary pathways, for example. So we have these objects, and what we did is we went on to get these ALMA band 3 spectral surveys of these objects. So we have this ALMA data for 3 of these sources, and then for LL Pegasi or FGL 3068, we only have single dish data, unfortunately. So then we have very high resolution, I mean, in a circumstellar sense, high resolution images. So somewhat sub-arc second, but let's say roughly around an arc second resolution. And we also have very good spectral resolution as well. And you can see that there is a lot of line emission here, especially in the IRAS 15194. That's mostly because it has a lot of 13C, and then it just has isotope log lines everywhere. So then we went through all this huge data set, and we found that there is more than 300 emission lines from around 49 species, including various isotope logs. And we see pretty much everything that we have detected in IRC 10216 in these sources as well, even though they are like farther away. So we see all the usual suspects, the carbon chains, the cyanopolines, and also the silicon-bearing species like SiO, SiS, and the silicon carbide. And also, well, HCN, HNC, and the 13C isotope logs of all these species. And with ALMA, the benefit is that you can also get spatially resolved information of all these. So you can kind of see where they are coming from, where the emission of each molecule is coming from the circumstellar envelope. And we see mostly 2 types of morphology. So we can see a centrally peaked emission, as you can see there, for HCN. So you see this typically for parent species which are formed close to the star. And then also you can see a more ring-like emission at the systemic velocity. This is for daughter species which are formed farther out by forward association of the parent species. And that's not all. You can also see a lot of complex structure, including arcs and spirals and whatnot, as you can see here for HC3N for one of our stars. And similar complexity has already been seen in IRC 10216, as you can see from Agundas 2012 in the plot there. So we see all these kind of complex morphology, and the first thing we did with it is we make azimuthally average radial profiles of these. So this is to determine the order of the chemistry, in a sense, meaning which species come from what part of the CSC. So you can kind of walk through the circumstellar envelope from near the star to farther out. And this is something very necessary if you want to determine accurate abundances as well, as we will see. And you can see that, so the 3 plots here are from our work, and then the plot on the top there is for IRC 10216. And it's very obvious from these plots that the order of the chemistry is very similar. For example, all the carbon chains, they peak almost exactly at the same place in all these stars. And for example, you can see CN is one of the most extended species in our list. So once we have a observational determination of the emitting region of all these different molecules, we went on to calculate some local thermodynamic equilibrium abundance estimates for these species. And you can see that we have a wide variety of molecules, starting from SiO and isotope logs to CS, HCN, all these, and even like C3H2. And what you see here is that, so these are, I would say, rough LTE estimates in a sense. So you can see some spread, but I would like to note here that the uncertainties here are also from a factor of a few and even up to an order of magnitude on some of these. So we wanted to get some more robust estimates of the abundances. So then we went on to do some non-LTE radiative transfer. And the method we adopted is relatively similar to what a previous speaker mentioned today morning. So we start with the dust modeling and then go on to the gas and the other molecules. So I can quickly walk you through this. So for the dust modeling, we use the Monte Carlo MC Max model, as it's basically fitting the SED to get the stellar and dust parameters. And from there, we, using those as inputs, we fit the CO emission lines. Most of them are single dish, but there's also some interferometric ALMA lines there. So I do this in collaboration with my colleague Miura here. So then from the CO line fitting, we get important parameters like the temperature and density profile, mass loss rate of these objects. And with those constraints, we can then move on to estimating molecular abundances. So you can see here our best fit model for CS for the different stars. And so these are the line fits, and you can see we managed to constrain these abundances relatively well. And what I really want to focus on is that the power of having interferometric or spatially resolved information is that, as you can see, this is our chi-square map for CS for IRC-1016. And if we only had single dish observations, you can see we only managed to constrain it as a blue line, which is like the typical banana-like shape you get in chi-square maps with large uncertainties. But then when you bring in the spatial information from ALMA and you use, instead of one single spectrum, you use a cumulative radial profile of the emission, then you can constrain the abundances much better. So you can see that the contours close within our parameter space, and you get much robust uncertainties. And also, if you have multiple isotope logs, we could model all of them and then combine these models to get even more rigorous estimates of the uncertainties on our models. So I'll skip through this in the interest of time. And so some of the results we see is that, for example, for all our species that we have done radiative transfer modeling for, we see that the e-folding radius of the abundance profile, so we use Gaussian abundance profiles. So the extent of the abundance profile increases with circumstellar density, as expected due to more shielding from photodissociation. And also we get very good estimates of different isotopic ratios. So the sulfur and silicon isotopic ratios in all our stars are almost identical to their solar values, which reaffirm the fact that there is no isotope selective nucleosynthesis of any of these species before or on the AGB for these stars. And then we also determined that, so you can see two sets of spectra here, and on the top, it's the same model except for the fact that we include infrared pumping and not. So in the top one, we have infrared pumping, and the bottom one, we do not. And you can see that the lines are way underestimated, even up to 70% in some cases. So this signals that it's very important to take into account higher vibrational levels and include radiative excitation when you model such species, or else you would be severely overestimating your abundances. And then also with Marie, I also did some comparisons of my radiative transfer abundances to chemical models. And you can see, so the blue ones are the abundance profiles of CS for 5 of our stars from radiative transfer modeling. And then the green and the red are chemical model abundance profiles. So what we aimed to get out of this was to compare different photodissociation rates that were given in the literature for these species. But unfortunately, given our uncertainties, we couldn't really determine which if the red one or the green one was a better fit. But still, you can see the way the method works. For example, here for SIO, the top 4 plots, you can see that the radiative transfer abundances and the chemical model ones agree relatively well. But for SIS, which has the bottom 4 plots, you can see that the chemical models significantly overestimate the radial extent of the SIO abundances. So this can help, studies like this can help fine-tune chemical models and the inputs that go into them as well. And yeah, I think that was almost everything I wanted to say. So I can also quickly add that we also plan to extend such studies to also carbon stars of different mass loss regimes. For example, all the stars we compared with IRC 10-16 now, they were of very similar mass loss rates. All of them were very high mass loss rate objects. So it would also be interesting at some point to see how the stars would compare if we go for like different Maslow's threat regimes and also for stars of other spectral types like. And for the upcoming changes to ALMA, like what Liz was mentioning yesterday, the wideband sensitivity upgrade and also possibly the ALMA 2040, these are expected to make spectral surveys like what I showed you much more cheaper and easier to do. So we are looking forward to stuff like that as well. Thank you.
Questions for Ramlal? I'm not going to ask any myself. That would not be cool. You going to force me? No? Ah, Theo, thank you. Rescue us.
So, Ramlal, when you show these differences in the abundance profiles of the chemical models and the ones you observe for SIS, I think it was, right? I see that these sources, they have like the abundance is not the same to start with for all of them. Is there a difference that when the abundance is higher, it deviates more, or is it too difficult to say?
No, I don't think we can discern something like that from this. So what we do with the chemical models is that we give them so as starting abundances, we just use the values we get from the radiative transfer modeling. And the only thing we compare are the e-folding radii or the extents. And I think from just these four, it's a bit difficult to see if there is a correlation between the peak abundance and then the extent of difference between the RT and chemical models.
And then the abundance difference to start with, is it more a metallicity, like a chemical composition effect, or is the sulfur going into other molecules? Do you know what is going on there?
You mean why the different sources have different initial abundances? It's just it's the best fit model that we constrain from the radiative transfer grid. So, I mean, I would say that there is, for the e-folding radius, we see a clear trend with circumstellar density, for example, but for the peak abundances, we do not really see any correlations like that with other properties of the star. So, and also, I would say that they are not that different. So, I mean, so this is one reason that we also concluded that the stars we studied now are very similar to IRC 10216 as well, because other than this typical expected trends with density, we do not really see any major changes in the abundance profiles.
I'm going to have to cut you off. Yeah. Thank you very much again. And then the next talk, we will go to the oxygen-rich side of the spectrum, and Bianca Els is going to tell us about SIO.
Okay, good afternoon to you all. My name is Bianca. I'm a student from UST Cassie in Korea, and today I will be talking about SIO detached shells. So detached shells form from a short burst of enhanced mass loss through sudden eruptions, often linked to thermal pulses or through two wind interactions. So as an example, as an example here is the carbon-rich AGB star TT Cygni, and it hosts a very well-known detached shell visible in the CO spectrum. So it is about 68 arc seconds wide and is estimated to be about 7,000 years old. So this center panel here represents the size velocity diagram, where a parabolic shape indicates a spherical shell expanding with a constant velocity. slide there, detached shells is often the nomenclature associated with CO line emission. They tend to typically be very large, spherically extended structures with several thousands or AUs of distance between them and the central star. However, in this work, when we say detached shell, we are in fact referring to the SiO-V0 thermal emission, which is much closer, maybe about within tens of AU from the central star, but they are still technically geometrically detached from the star itself. So while CO detached shells are observed in both carbon-rich and oxygen-rich AGB stars, this thermal CO detached shell tends to only be seen in oxygen-rich AGB stars. And the SiO-V0 emission often shows a composite profile composed of both a non-thermal maser component and a thermal plateau, but though some stars do only show this thermal plateau instead. So we did a more in-detailed study with WXPCM, which is a well-known oxygen-rich AGB star, which is located about 740 PC away from us with a very high mass loss rate. So in its SiO spectrum, we see both this thermal plateau and the maser peak, which suggests a very complex conditions within its circumstellar envelope. So the Atomian study by Dessen et al. In 2020 shows this kind of CO line structure with a complex spiral, which is in its outer circumstellar envelope. And we asked, do we see the similar structures existing much closer in the inner regions, and can we trace this through the SiO? And if we do see this kind of similar structure, does this support the companion hypothesis, or does it possibly rule it out? So to explore this, we analyzed the morphology of the SiO combined with ELMA and KVN observations. So here are the ELMA spectra of various maser transitions, and the SiO-V2 transition is our strongest maser here, and as you can see, it's peaked and very narrow. However, our SiO-V0 transition is very spread out in its velocity. This will be our thermal component, and it also has a very thin maser peak here. And this is of particular interest for us to get this kind of structure. So these are the 0th and first moment maps of the SiO-V0 transmission. So what we see in the 0th moment is this clumpy ring-like structure around the star with two notable voids in the northwest and southeast direction. So from the first moment map, if we color code it correctly, we can see that the majority of this gas is blue shifted, which lines up with our spectrum here, and only a small section here is red shifted. So this, we interpret this shell as being the product of an episodic mass loss event, and suggest that the voids that we see are due to some kind of bipolar outflows, which may have pushed away the material along that axis. We compare the shell position to the position of the star, which is seen in these yellow contours here, and we can see that there is about a 20 milliarc-second offset. So this offset roughly translates to about 15 AU at this distance of 740 parsecs, and we propose that the offset results from an anisotropic expansion or even intrinsic anisotropy of the thermal pulse itself. And we also noted that a modest velocity gradient of around about 5 kilometers per second is sufficient enough to create the offset that we see over time. So by decomposing the integrated image that we see there, we can look at the individual velocity channels and trace the spatial distributions of the emitting material as a function of velocity. So the ring appears smallest in the red shifted part of the spectrum, growing towards the stellar velocity and then shrinking again in the blue shifted area. So this pattern supports a spherically expanding shell consistent with an episodic mass loss ejection. So to quantify this expansion, what we did is we fit ellipses to each channel and then insert this radius into this equation right here. And assuming a systematic velocity of about 8 kilometers per second, we can determine the gas expansion velocity, which gives us about 14 kilometers per second. And with what we see in the first moment map, this corresponds to 46.4 AU in radius for our shell. So we can then figure out what the expansion timeline is like, and what we ended up with is 15 years. Now, this is suspiciously short, considering the fact that thermal pulses are typically separated by 10 to 100,000 years. So we've either been extremely lucky to just observe a thermal pulse, or there's perhaps something else at play here. So confirming this would require archival IR data and some historical maser monitoring as well. So if we look a little bit more in detail in our maser maps and so on, we can see that from ELMA, we have our water maser peaked at the stellar velocity, which is rather strange because if you look at the same water maser, different transition, of course, we see that it doesn't peak at the stellar velocity and we get our typical blue-red shift. However, our SIOV 1 and 2 spectra do align and have the same shapes. If we look at the maps here, our water maser from this observations doesn't show us the red shifted part of the outflow, but this is mainly because this is a total power spectrum and this is cross power, but it is there. And our SIO rings give us our typically seen shapes, but with a little bit of local bulging here in the northwest section. Our SIO masers do look a little bit strange here and don't overlap as much, but we do see, however, that our SIOV2 and water masers do, however, completely overlap over here. The rest of our masers do especially agree with each other as expected. And if we compare the KVN and ALMA maser results, we can see when comparing the continuum from ALMA and the SIO ring center from KVN, the central position of the star doesn't actually align, but we've attributed this to some asymmetric uncertainty in the KVN. Nonetheless, the rest of our masers do spatially correspond well enough to give us confidence in our results. If we look at some 2015 water maser emissions, though, we can see very strongly the red-blue shift. And we can see that it does align with our northwest-southeast axis. Now, if we look at the whole maser and thermal emission of these SIOV naught shells, we can somewhat imagine a spiral and say, hey, it does match up with the CO line emission. But as we've confirmed already, this is a shell and not a sort of disk type thing. So this would be an incorrect interpretation. So conclusions from that gave us that WXPAC is an oxygen-rich AGB star with a clumpy SIO detached shell, observed with both ALMA and KVN. The shell shows two distinct voids, which are made by bipolar outflows as traced by the water masers, and our 20 milli arcsecond offset between the shell and the star is attributed to some asymmetric expansion of the thermal pulse. And these features of clumpiness and episodic ejection are all early signs of the processes that will eventually shape the star's planetary nebula. But I wanted to ask if WXPSC is a unique case, so we have extended our study to include more AGB stars that have a SiOV0 emission that has a thermal plateau and a maser. You can see that W1302 Aculae doesn't have a maser, and neither does CW Leo. And CW Leo, of course, is oxygen-rich, carbon-rich and not oxygen-rich, but this is theorized to be due to some shock-induced chemistry that shows us that it does also have SiO masers itself. Now, I'll run through this quickly because there's no time, but we have our correlated data back for IK tau, and we do see the expected structure within its spectra, same to our original source. But if we turn this into a map, unfortunately, we only see the maser peak here. This is not due to the fact that it doesn't have a detached shell, but rather that the KVN beam is too small to capture this weak diffuse structure. So we did give in a proposal to ALMA, however, we were unfortunately rejected. I'll just skip through the other results that we have from the KVN, but basically with our KVN and ALMA, hopefully in the future results together, we can look at the morphology of SiO detached shells of more stars to see if the structure that we already have seen is unique or not. And yes, I'll end it there.
Question, Devika?
Hi, Bianca. Thanks for that nice talk. So full disclosure, I'm also an ALMA newbie and I've had proposals rejected. So I share the same sentiment there. Could you go to slide 10? And this might be a question simply because I don't understand the data enough. So here you have in H2O emission, ALMA weak peak, but KVN double peak, strong blue shift. So how do you see the difference if you're still looking at the H2O emissions? So
how do I see the difference?
Yeah, so I'm just trying to understand a little, well, maybe to better phrase the question, could you explain this data a little bit more to me for the H2O emission and SiO?
So normally what we see for the maser spectra for H2O is the double peak of blue and red shifted.
Yeah.
But I'm assuming that at this time, which was 2017, because of the way that masers change in strength with the star, it was at a part of the phase where this red shifted part was too weak to be.
Got it.
To
The
see.
maser changes its strength and intensity.
Yes.
In some, got it.
Which is why later on, when I show this here, we use 2015 when it was stronger.
Thank you. Thanks.
Thank you.
There's an online question first.
So we have a question from Taisa regarding the bipolar outflow. Is this caused by a companion, and what approximate orientation would you expect for the orbit?
Right, yes. So that's something that we had thought about is normally we know that bipolar outflows and companions are linked. And if we do look at the CO emission, we do see that complex spiral there as well. But so far there has been no detection of a disk, a circumstellar disk either. So we can't really say, even though there is a bipolar outflow and there is some kind of spiral shapes that do indicate there could be a companion, there's no real direct and even stronger evidence of a companion there. So I'm not quite sure.
Can I add one?
Is there another online question? I think
No, yes.
Javier can go first, and then we have to maybe take it into the break.
Thank you. It's again about the water lines. Can you show us what was the transition you observed with ALMA? Because the numbers, you have a table by the end of the presentation with all the lines observed with the different.
So for this WXPSC.
No, it was at the end of the presentation where you have. Yeah.
This one.
Yes, exactly.
This is planned.
The double horn is a typical 22 gigahertz measure that is pumped at a particular distance from the star. But the other water measure you observe with ALMA is this 14,410 to 15,313, which is a totally different energy. So even is water, these are measures. And then of course, if you look at one measure with a totally different distillation energy, it's tracing a totally different environment. So it may happen that this ALMA water measure traces, the gas which is very close attached to the central source, and you see the systemic velocity, while the other, because of the pumping and amplification, you see the front and the back, and then you get the blue shifter and the red shifter. So for me, it's not surprising.
Okay.
It's just a matter of a totally different transition with totally different excitation energy.
Okay, thank you for your comment.
Okay, then with this, we can thank Bianca and all the other speakers from this session again. And if there are any further questions for any of the speakers, please put them on the Slack or take them into the coffee break. We should be back at 4. Yeah.
Hello, welcome everybody to the last session of today. So we're gonna continue. Well, my name is Carmen Sanchez Contreras from the Center for Astrobiology. And we are going to continue with a last talk discussing the outflows of AGB stars, which is given by Jaime Alonso Hernandez. So I guess we are all ready. The floor is yours.
Where is my presentation? Here it is. So, hello everyone, my name is Jaime Alonso Hernandez. I'm a PhD student in the Center for Astrobiology under supervision of Carmen Sánchez Contreras, Dr. Carmen Sánchez Contreras. And I'm going to talk about our work in the characterization of the circumstellar envelopes surrounding AGB stars with ultraviolet and X-ray emission. And in first place, I would like to thank the organization for giving me this opportunity to expose my results. So, in first place, I will start with an introduction about these ultraviolet and X-ray emitting AGB stars. Well, I think I don't need to introduce AGB stars, but we know that one of the main problems is the identification of stellar companions, mostly related due to the fact that they are very luminous and intrinsically variable stars. However, AGB stars tend to concentrate most of their luminosity in optical and infrared wavelengths because they are cool stars. So if we are able to detect an intense ultraviolet emission, this could be indicating the presence of a hot companion. This was proposed by Sahai and collaborators in 2008, and they performed a survey with GALEX, and they effectively found these AGB stars with ultraviolet excesses. Just mention that these excesses could be also related with chromospheric activity, for example. There are other physical processes that can produce this ultraviolet emission. However, they also found that in some cases there is some time variability in different time scales. In this case, with Hubble, they found variability in time scales of hundredths of seconds. And in some cases, they also found the presence of X-ray emission. The X-ray emission is clearly related with accretion processes. I've divided my talk in 3 parts. In the first one, I'm going to talk to you about my work in the characterization of the molecular gas component. In the second one, in the molecular gas chemistry. And the last one, the characterization of the gas component. Okay, I would like to start this part talking a little bit about the demography of these ultraviolet emitting AGB stars. Here you see the IRAS color diagram, and you can see that most of the ultraviolet emitting AGB stars are located in the lower left part of the diagram, which indicate that they have low infrared colors. This indicates that their envelopes are small. We also found that near ultraviolet emission is relatively common in AGB stars, whereas far ultraviolet emission is more rare. In this work, we performed a survey over CO emission lines in a sample of 29 ultraviolet emitting AGB stars with 2 transitions, and we performed the first characterization of ultraviolet emitting AGB stars as a class. We performed a characterization of these envelopes. We estimated the most important parameters on the envelopes and compared them between them and with other stellar parameters. And we found that their envelopes are compatible with the radiatively driven winds, and that only studying the bulk of the envelope is not enough to differentiate these AGB stars from common AGB stars. However, we also found that the intensity of the CO emission in comparison with the infrared emission at 60 microns is statistically lower than in larger samples. This could be indicating the presence of CO photodissociation by the high energy emission. In the second part of the talk, I will talk to you about the molecular gas chemistry. Just a brief introduction. Well, Marie already did it and explained it very well, but ultraviolet emission can drive a different molecular chemistry. This was studied previously by Marcelino Agúndez, mostly the interstellar radiation field, ultraviolet emission in the effects on the chemistry, and more recently Marie studied it both from the interstellar radiation field but also from an internal source. In these diagrams you can see how the abundance of different molecular molecules can change due to this internal ultraviolet emission. In this study, we did the same with X-ray emission. We would like to know the effects of X-ray emission in the circumstellar chemistry. We performed this study with three approaches. The first one, observational, we performed a spectral survey over 4 AGB stars, 2 of them oxygen-rich, 2 of them carbon-rich, 2 of them with X-ray and ultraviolet emission, and the other 2 only with ultraviolet emission. Later, we performed radiative transfer analysis to estimate the abundances, and finally, we compare with chemical kinetics model. This is an example of the observations. This is H2+, it's a well-known X-ray tracer, and we observe this source, the Dracon, is a carbon-rich X-ray emitting AGB stars in 2 epochs, and you can see that there is a variability in the intensity of the H2+ emission lines. This is likely related with the intrinsic variability of the X-ray emission. Here are other samples of emission lines of different molecules. Oops. Okay, and here is the comparison with chemical kinetics models. In first place, we studied the radial abundance of carbon monoxide, and we found that it is expected to have depletion in the internal abundance due to the X-ray photodissociation. In order to ensure which effects are produced by X-ray and which effects are produced by ultraviolet emission, we performed 4 different models. One a standard model, other with only ultraviolet, other one with only X-ray, and the fourth with both ultraviolet and X-ray emission. And here you can see that this depletion in the CO abundance is only produced by X-rays, but not by ultraviolet. This is related with the photodissociation energy of carbon monoxide, but also with attenuation of the ultraviolet emission. Here is the radial abundance of H2+. You can see that there is a large difference between the predictions from the models with X-rays and without X-rays, and the empirically estimated abundances agree very well with those of the X-ray emission, in which we found an enhancement of some orders of magnitude. This is more related with the photoionization of molecular hydrogen. This is a game changer in terms of astrochemistry because the H3+ radical is very reactive. Well, molecular hydrogen is the most abundant molecule, so a small variation can produce large variation in daughter species. Here you have the molecular reactions that lead the production of H2+. We also found 2 other molecules which are related with the X-ray driven chemistry, HNC and HC3N. Here you have the reactions. In the first place is also related with the presence of with the ionization of molecular hydrogen. In the second case is related with photodissociation of HCN. Yeah. Here are interferometric maps from the NOIMA interferometer in France to perform a follow-up. We found that there is also a large scale spiral embedded in the CO emission, and we effectively found that the H2+ emission is concentrated in the internal regions of the envelope. Yeah. Okay. In the last part of my talk, I'm going to talk to you about the task characterization. We performed this study with SED modeling. For this purpose, we gather different photometrical measurements from different surveys and also perform aperture photometry in hair cell PAX images. We also use Gaia, ESO, and IRAS spectra. And yeah, we perform the CD modeling with the stellar models of COMARS and also with DUSTY as a radiative transfer code. Here is an example of the different parameters that we use in the modeling. We have the stellar temperature, the inner radius temperature, the density power law index, the opacity, and the correlation between the outer and internal radii. We have to assume the dust composition and the grain size, and you can see that even though the single uncertainties are relatively small, there are large degeneracies between the different parameters. Here is also an example of the PAX images. We found that in some sources there is a slightly extended emission. This is also good. This is good because we can use these radial brightness profiles to better constrain the envelope. And here are some results. We estimated some different parameters and performed comparisons. We have found the typical evolutionary trends in AGB stars and the typical ranges for the different parameters. And one interesting result that we have found is that in some cases the gas-to-gas ratio is statistically lower than in larger samples of AGB stars. There are different scenarios to explain these low gas-to-gas ratios. Could be related with photodissociation, as I mentioned before. Could be also related with the effect of ultraviolet and X-ray chemistry in parent species related with the formation of dust. Could be also related with the properties of the dust, could be different as an effect of the companion. And there could be also an enhanced production of dust due to the presence of the companion itself. And could be also the effect of some binary induced structures can be mimicking the CDs with different dust masses. Other interesting result that we found was the effect of attenuation due to the dust. This is well known, of course, but we would like to present it and to better know the internal ultraviolet emission. In this plot, there is not a clear trend. We are showing it as dark markers, the observed ultraviolet emission, and the purple markers are the opacity corrected emission. We have found that in some sources there is a large difference due to the opacity, the dust opacity, and here you can see the corrections for oxygen-rich stars and carbon-rich stars. There are different trends, and this is related with the opacity curves. In the case of carbon-rich stars, the opacity in the near ultraviolet and far ultraviolet is pretty similar, whereas in the case of oxygen-rich, there is a difference between the near ultraviolet and far ultraviolet opacity, which produces this effect in the ultraviolet color. This is the ultraviolet color. So yeah. These are my main results, and just an advertisement. I'm looking for postdoctoral positions. Thanks.
Thank you, Jaime. Time for questions.
Thank you for the interesting talk. I was wondering for your sort of range that you find in dust to gas ratios, do you find a correlation with like the UV flux of these sources or not? Do you know the UV fluxes, etc., of your sample? Like, did you make those plots?
Yeah. No, we are still working on it, but it seems that there is not a clear correlation.
Oh, yeah, interesting. Cool. Thanks.
Any more questions? Oh, okay. Let's thank again, Jaime. Okay, now we move on to a slightly different topic. We're going to have an invited talk by Barlabases on the role of AGB stars on understanding the formation of the solar system. Okay, go ahead.
Okay, thank you. Thank you very much. I will give this talk on behalf of Maria Lugaro because she unfortunately couldn't come this week for this wonderful conference. And also thanks for the organizers for inviting me. Yes, as already introduced, I will now talk about the formation of the solar system. In this talk, I would like to answer two, maybe if I have time, three questions. How can we understand the solar neighborhood using barium stars and also stardust grains, the terrestrial planet formation using AGB stardust, and the environment of the sun's burst using radioactive nuclei produced by the AGB stars. So let's start with the first question. What are these barium stars? Why we do care about these stars? So thanks to Anna Scorza, I have this very nice plot where I can explain you. These stars are chemically peculiar stars in a binary system where we have a little bit more evolved star that already evolved to the AGB phase previously and polluted the secondary star with some S-process enriched material. And now the AGB is a white dwarf star, and we can observe either a barium dwarf or a barium giant, which are still not in the AGB phase, but with the S-process enhanced material. On the other hand, we have the stardust grains. These are coming also from the AGB stars. They ended up in the molecular cloud and then in the solar system protoplanetary disk. When the solar system formed, they were still around, and now we can observe and analyze these grains in the laboratory through the meteorized. So how can we compare these two completely different results and completely different data? First, again, starting with the barium star data. Here we have each of these grain points is one barium star from a large homogeneous study. And on the x-axis, we have the metallicity, the Fe over age, and on the y-axis, two different S-process elements, cerium and yttrium ratio in a logarithmic form. So we compare to solar abundances. And we can see that the data and the different AGB nucleosynthesis models have a very similar trend. So if we move to higher metallicities, the trend is decreasing. They very well agree with low mass AGB models. On the other hand, we have some stardust data from the literature. These are large micrometer size grains. And here we show the delta, so the permeable variation of the strontium and barium isotopes. Most of these grains are located in the middle of this plot. We are now concentrating on the strontium ratio, and these range between -2000 and 0. So the question is, how can we translate these different data, and how can we identify through this data the AGB parent stars of these grains? So here, this is a bit complicated plot. Here we have the x-axis, the cerium over yttrium ratio that we also have for the barium stars, and the strontium 88 over strontium 86 variation in this data notation on the y-axis. And we have a parametric S-process model, this butterfly shape, which is the edge of the models. So that's the limit, basically. And we have many stellar S-process models, again, below 4 solar mass, because these can very well fit the barium star data with different parameters. And we are looking for the strontium, delta strontium ratios between -200 and 0, as we have seen in the previous plot, that the stardust grains are located mostly here. And what we can see from this plot, that the cerium over yttrium is negative if the strontium data are between these -200 and 0. So we have to look for these barium stars, which have negative cerium over yttrium to identify the parent grains. So if we go back to the same barium star data and we have a normalization for this negative cerium over yttrium, we see that most of these stars have a positive iron over hydrogen ratio. So we can say that the large micrometer sized silicon carbide grains must have originated from these AGB stars that are older than the sun, since they have to be here to see them in the meteorites, but they have also supersolar metallicity. How can this be? So how can we connect the metallicity and the age of the stars on the observations? So if we take a look at the chemical evolution of the stars and the Milky Way, when the stars die, they produce metals that is then ejected into the interstellar medium. From the interstellar medium, the molecular clouds form where the stars and the planet also form later. So so if we go back in time, the older stars should have less metals. So this is not the same as we have seen previously. How can that be? Oops. So in a study of Nissen and collaborators, they found some stars that have high metallicity, but they are old at the same time. So these are these red data in the solar neighborhood. The sun is in the middle, this black dot. And as I said, according to these meteorite data, some supersolar metallicity stars have to be here when the sun and the solar system formed. So how can that be? Here comes the galactic chemical evolution in the picture. There are some models that are called two-infall models. So back in time, the stars had not that much metals. So this is again a phi over age in the y-axis. And as the galaxy evolved, they were moving to higher Fe over age. But then some fresh material was infalling again to the galaxy. So then the Fe over age dropped. And then again, coming closer to today, the stars were again evolving to higher metal content. So this is, of course, not a perfect model, but it describes fairly well these old but metal-rich stars. So now we can move to the second question, how we can understand the terrestrial planet formation using the AGB stars. So the stardust was already here, that's what we know, and also it carried the S-process signature to the solar system protoplanetary disk from the AGB parent stars, and we can check what happened to this stardust in the disk during the formation. So in this plot, we can see that the previous AGB stardust and gas and also some supernova dust could come to the molecular interstellar cloud of the parent interstellar cloud of the solar system protoplanetary disk. And then also the interstellar dust is mixed with the interstellar dust. And then through different processes, it depends on the size, the mineralogy, and also the heat to the dust. There is an isotopic difference at the end when the disk, protoplanetary disk is formed. So here you can see that also the red points, the size of the red points is changing, and also the interstellar dust amount, this gray coverage of the stars. And at the end, we see that the relative to the ISM dust, there is an enrichment of the stardust closer to the sun. And also here, the heat is described with this, or showed with these different colors. So the dust closer to the sun, of course, experience more heat. So for the stardust, let's check the molybdenum isotopes molybdenum has 7 stable isotopes, and here we show again the delta variation, this permeable variation, relative to laboratory standards for the different molybdenum isotopes. And here the red points are the points from core collapse supernovae data, and the field symbols are the AGB data, and the different colors show different studies. So the red line is just a fit to the stardust from the AGB stars. So this is the effect of the S process on the molybdenum isotope. So they are all going from minus some hundreds to close to 0. Where is the solar system? In the middle, in a very tiny little dot within 0.1. And here, if we zoom in, we see that the Earth is the most enriched in S-process material in this very tiny little dot. Here we zoom in again. So what we see here is the Earth is the richest in AGB stardust in the solar system, but that's a problem. How can that be? Because it was a mixture of material in the ISM and the stardust. So how can be the Earth the most enriched? One scenario is that the richer material fell in the sun. Unfortunately, we don't have data from Venus and Mercury, but then it could be that they are even richer than the Earth. Second scenario is that the enrichment didn't happen during the protosolar disk, but later when the Earth formed, there was a pebble accretion, and that is causing this enhancement of the Earth in S-process material. Okay, do I have time for? Okay, then I will go to the third question. It's about how can we understand the environment of the sun's birth using radioactive nuclei produced by AGB stars. So as I showed this picture before, here we have basically 3 parts when we can check the we can use the radioactive nuclei. It's, as I said, this meteoritic analysis. Then that's at the birth of the sun. It's a clock at the birth of the sun. Then we have models, stellar nucleosynthesis models for the different stellar sites, and also the galactic chemical evolution models. And the question is, how long did the molecular cloud lived before the sun formed? So our molecular cloud. And for this, I was not involved in this project, but they applied these radioactive isotopes, three different radioactive isotopes, to find out this so-called isolation time between the birth of the sun and the molecular cloud. And at the end, it came out that it's approximately 10 million years after the birth of the molecular cloud when the sun born. So it's a relatively long-lived and massive cloud that is the origin of our solar system. So if I go back to the summary and the conclusion, we have seen that the stardust grains and the barium stars both require that there has to be an old and metal-rich population of stars here at the solar neighborhood when the sun was formed. And we have also seen that the Earth is the most S-process enriched body in the solar system. So that's also a very good test for the terrestrial planet formation scenarios. And I would like to thank also for the support from the different institutes and projects. And thank you for your attention.
Well, thank you very much for your talk. According to the program, this was an invited talk, so we have plenty of time for questions and discussion if you like. So who wants to start?
Hello, I'm Seneca. Very nice talk, very nice slides. Question about the molecular cloud and the age, these 10 million years. I mean, there were molecular clouds also before those 10 million years, and I'm not quite sure I can follow how you reason that this particular molecular cloud was 10 million years old, because the age of molecular cloud is a very hot topic and much contended. And so how can you be so sure that this number is a good number?
Yes, thank you for your question. I was not involved in this study, but I am also a bit confused. So here, as you see, the palladium and hafnium isotopes give somewhat higher value, but the lead is very uncertain. So this is just an approximation based on these two isotopes. I think in the paper they don't write exactly this number. So this is just from Maria, that it's approximately 10 million years. Yes, it's very uncertain, but still much better than previously.
This misses the point. The point is you use that method. And I mean, if you believe the method, then probably you find this age. But the method, I mean, you get 3 radioactive ages, and to determine an age of a molecular cloud, that doesn't, I mean, I don't quite understand what the logic is, the precise logic, how to reason.
Well, yes, I think they used, that's why they use a different, how do they, half-life for the isotopes, that they could do the best what they did. So unfortunately, this is not my field of expertise. I am from the barium star project part. So, yeah.
Just a question out of ignorance. I do not know or understand what this 2-info galactic chemical evolution model is, and what is then the, you said something as that there was fresh material delivered. What is, can you explain that better to me?
Yes, so basically in the model, if you imagine the galaxy as one box or amount of stuff, then it's coming from out of the galaxy, fresh hydrogen coming into the galaxy. And that is mixing again and again.
And from where then? You say outside of the galaxy? Take to me. Yeah, I see that when you add something, when you add more hydrogen, then that you will have a decrease in your curve. But where is the hydrogen coming from? You say outside of the galaxy, but how? What is then outside of the galaxy? What is then the delivery or the messenger that gives you the hydrogen?
Oh, that's a good question. Actually, sorry, I don't know. It's very far from my field of expertise, so I have to check it.
Okay, good. Yeah, I don't know either.
Hi, Matthias Merker from Chalmers in Sweden. It's cool to see that AGB dust grains contribute to the solar system, but can you tell how much those grains would have changed since they were created around the AGB star? Like, how similar are they to what they originally were?
I think we think that these are preserved as they were in the AGB. So, yeah. So they were in the interstellar dust. They were covered by these mantles, and then we think that they must be around as they were in the AGB, inside these meteorites. So hopefully they are still very similar to the original. But yes, so as I said, this is absolutely not my field of expertise, so I think there are many more people who know much more about this than me.
Anyone else wants to make another question?
As to the Earth being so barium rich, one of the ideas, right, is process rich, right? One of the ideas for the formation of the moon is that there was this impact, and then some of the material, you get this, the Earth becomes molten again, and then reforms the moon, and this is why our moon is so big compared to all the other planets. Could this be an explanation why our Earth is so different than some of the, is there a way to tell, or is this a way to validate theory of the moon formation? And is the moon also as process rich?
Yes, I think this is still an open question in planet formation to tell about the moon and the Earth's formation.
Thank you.
I can just comment on the grains. So those dust grains, we think, look, I mean, if we compare the C12, C13 ratios measured in pre-solar silicon carbide grains, they match up with the C12, C13 measured in real AGB stars. That's why we think that there hasn't been much processing in the interstellar medium. So, I mean, maybe there's been, and also the grain, so essentially those grains formed in the outflows, and sure, maybe stuff, there's stuff on the outside of the grains, but when it, the stuff that survives that we detect from the meteorites, that's that part per million tiny fraction left. Everything else was essentially melted when the solar system formed. That makes sense. So.
Anyone else? If not, thank you very much again. And we move on now to a contributed talk by Matthias Merker on a somewhat connected topic, the role of AGB stars in the origin of dust in the interstellar medium. Go ahead, please.
Is this better? This is better, yes. Okay, great. Yeah, thanks. So my name is Matthias, and I'm from Chalmers University of Technology. And I actually prioritized meeting all of you over going to a dust conference in Arizona last week to present this work. So I'm really happy I got a chance to actually present it here, and I'm really happy to meet all of you. I'll be actually talking about the dust that we observe in wind ISM interaction regions. So you should maybe more take my title as a spiritual guide light rather than expect actual answers on the role of AGB stars. And in the same spirit, this is probably a talk that I'm giving on something that is as much work in progress as I've ever done before. So I'd really appreciate as much input as possible after the talk or during the remaining days. But yeah, so why do we actually study stellar dust at all? And basically this is because it helps us enrich the universe chemically. And we have sources both in AGB stars and in supernovae. And in both of these sources, we synthesize elements that then get incorporated into dust grains and are released into the ISM as seeds, where we have continued growth or destruction, surface processes that in one way or the other affect the chemistry in the ISM of galaxies. But all this processing in the ISM, it depends on the seed properties. So what kind of properties the grains that come from these stars have. For example, the size or the structure and the composition. And this is why in all the dust talks, we talk about sizes, structure, and composition. But the reason why it's so important to study dust grains is because they're really essential for understanding how the universe evolved chemically and how we form new stars and new planets, as we heard just in the talk before. However, there are tons of issues about this, both in the early universe, where we observe higher amounts of dust than we expected, but also in the local universe. Models are very ambiguous and unclear about how to explain the dust in galaxies. And a lot of this depends on the basic or the lack of understanding of the basic properties. And in recent years, theoretical models show that we might grossly overestimate the amount of dust in our radiative transfer models. So there are more problems than this. These are just some of the most common ones. So what do we think happens with dust? If we look at the dust that we see in the ISM, I think there's seems to be consensus that most of the dust that we see is not the pristine stellar dust, but it's dust that is a consequence of some kind of growth on seed particles. So we have a seed grain, and then we have stuff growing onto it or reactions happening with it. So this efficiency of the growth on the grain depends on the properties of the grain itself. So depending on how large it is or what its composition is in the structure, you'll have different growth efficiencies. But that is really difficult to incorporate comprehensively. So generally, I think what we assume is, and I've spoken to people several times now already during this meeting, is that the dust gets formed in the inner envelope of the AGB star, and then it's just not changed anymore. So we think the dust stays the same. And because it's really difficult to have all these complex networks of dust growth, all of these growth processes are included in some kind of sticking coefficient that is then varied in order to match the observations that we have. But this sticking coefficient hides actually all these physical properties of the dust grains. Another quick note on the balance between AGB stars and supernovae is that I know that Martin in his first talk sort of made the case that AGB stars are really unimportant in the early universe, maybe in the very early universe, but there are signs that in the earlier universe, AGB stars might be important. I've also seen different estimates of how much of the stellar dust is from AGB stars. I found a number of 90%. And then we just heard a really nice talk on that pre-solar dust grains show that they must come from AGB stars. And so AGB stars could be more important. It could be important in addition to, and obviously, so I usually give this talk for people who don't intrinsically believe in the importance of AGB stars. But so hopefully I'm running in open doors here, but yeah, AGB stars could be important, and that's good for all of us, I guess, to know. So I got interested in this, and I wanted to see what kind of dust does the AGB star actually put into the ISM. And then because I'm shaped by my former PhD supervisor, Hans Olofsen, and detached shells, I started looking at detached shells, and we heard a little bit about these objects before. And these are big shells of gas and dust surrounded by, around carbon stars, and that were created in a thermal pulse. And so I looked at the dust of these shells, and the beauty with this is that we know exactly where the dust is from the star. And if we look at SED models, we can determine the temperature of these dust grains. But because we know where it is, and it's spatially resolved also in our observations, what decides the temperature of these grains is not how far away it is from the star, because we know where it is, but are the properties of the dust grains. So the composition and all of those things. So we modeled a few of these stars, the SEDs, and because they're around carbon stars, we used amorphous carbon grains, and we concluded that the grains in the detached shells are relatively large, certainly larger than 0.1 micron, but actually I think for some of the models we got something more around 1 to 1.5 micron in radius, which is larger than we typically expect around in the inner envelopes of AGB stars. But based on this work, then I thought, okay, but this is a detached shell. It's win-win interaction. This is still not in the ISM. Let's look at what happens when these winds collide with the ISM, which is really where the dust transitions into the ISM. So in 2012, there's this paper with POX observations at 1760 micron of wind-ISM interaction regions. And here we see, oops, I shouldn't point out that screen. Shouldn't here. So here you see these really nice bow shocks in thermal dust emission of these wind-ISM interaction regions. And the first analysis in 2012 sort of assumed standard grain properties of 0.1 micron and a grain temperature, and they determined the masses in the interaction regions, showing that it's feasible that this dust mass comes from the stellar wind. But I revisited this data during the pandemic, actually. And now I actually explicitly modeled the three-dimensional shape, thank you, of these interaction regions, and used the spatial constraints, just like with the detached shells, to determine the properties. We varied the grain sizes, thinking that that would affect the temperature. And we modeled also, we monitored both amorphous carbon and silicate grains. And then we tried to constrain the masses by explicitly modeling the ratio between 70 micron and 160 micron. So for the carbon-rich sources, this worked really nice. So here you see the observed ratios between 70 and 160 micron, the red dots, and these gray bars give you the range of models depending on the grain size of the amorphous carbon grain. So you see for all the carbon-rich sources, I find a model that fits. And generally, also here, the grains should be relatively large, around 2 micron. For the oxygen-rich sources, it turned out to be a lot more complicated. For most of these sources, none of the models actually fit the observed ratio. And generally, what happens is that the dust in the models gets too warm. So this indicated that there's something wrong with the underlying assumptions in the model. And we tested several things like the SED from the star, different slopes of the opacities and stuff like this. But we didn't really come to a conclusion in this paper. So then recently, I decided to test new opacities. I used the dust opacities from Demick et al., which are cosmic dust analogs. They have irregular shapes. These aren't the dust grains that I use, but it's a pretty picture, so it shows the different shapes. And they derive optical constants in the lab up to 1,000 micron for different temperatures of where the dust grains were formed. An interesting thing here is that they measure the far infrared slope rather than extrapolating. And so here you see the amorphous silicates that I used in the first paper. And then here you see the amorphous carbon. And this is an example of one of their grains. So you see the opacities really change in the near infrared and optical, where the star emits most of its light, and how it emits in the far infrared. So that will really dramatically affect the temperature. So I just picked these grains. I tried several compositions, but just here I have these grains here. It's called XO35 in their paper, formed at 10K. I assume a constant radius of 0.1 micron. So here you see the opacity for that particular grain compared to the SU silicates grains. And what I have to do, though, is these opacities are still they don't reproduce observations because the grains now become way too cold. But if I put a mantle of metallic iron onto the surface of the grain, so this is sort of what I imagine it looks like, it changes the opacities like this. And it's not a lot of iron. It's just between 0.75% to 1.5% of the core mass. And that will increase the temperature of the dust. And you can see here the observation at 70 micron and 160 micron. And in the same color scale is the model. And you can see that I actually fit the ratio pretty nicely. If I don't have this mantle of iron, or if I have iron inclusions like MgFe SiO3, the grains get too cold. So this is without iron at all, and this is with iron inclusion. And you see the absorption here is still too little, so the grain gets too cold. So I need to have it on the surface of the grain, covering a fraction of the grain surface. I also tried to put carbon around it, just to see, but I need a lot of carbon, thank you. Around 30 to 50% of the core mass. So this is not sort of just speckling the surface, it covers the surface several times over. And you can see here the opacity for that grain, and this basically mimics a carbon grain. So I think the iron on the surface is more likely. So yeah, as I said, this is a work in progress. The dust masses that we derive are still consistent with what we think could be from the buildup of a stellar wind. And for the carbon stars, again, this is the older work, we see an indication of larger grains, but the standard dust that we assumed does not really work. So we sort of have to change how we understand dust grains around oxygen-rich sources for sure. And this is also indicated by the talk that Theo gave. So I tested new opacities for silicate grains, and they are really different from what I think we've commonly used before. And I think we need some kind of mantle, some kind of dirty grains on the surface. But I think here, this is actually only where the work starts, because there's so much more that we have to look into to see what the grains are in these wind-ISM interaction regions. But I think eventually it will hopefully lead us to a little bit better understanding of what kind of dust is actually put into the ISM from AGB stars. And I'll end with that. Thank you.
Thank you very much, Matthias, for your talk. Questions? Hi.
Hi, Matthias. Thanks for this interesting talk. I've been recently working with two of these AGB stars with large-scale structures, and I have a couple of ideas on how to work with these things. We can talk later. I think it's also important for the future to have something that could be observing in the far infrared and with some spectral resolution to better constrain the temperature. And regarding with this thing, there is a proposed NASA mission, PRIMA, which is gonna be something like Herschel, but with improved capabilities and would be able to do this kind of thing. Would be good for the future.
Yeah, that would be really, really great. I mean, the Herschel data is already really cool and great, but especially at 160 micron, the detection limit really limits some of the stuff that we can do. Yeah, absolutely. That would be cool.
Thanks.
Sorry, Hans again. Question, I mean, just definition and clarification. You mentioned stellar grains and interstellar grains, and then maybe also pre-solar grains and so on. Can you help us clarify and distinguish all these terms?
Yes, if I can help you clarify what these terms mean in my head. I don't know if, I think it depends on which field of astronomy you ask. But in my mind, so what we call dust grains, ISM people might concede could be seeds. So they wouldn't call them dust grains, they would call them seeds on which actual dust grains grow. And I've had a lot of arguments with ISM people. And then I guess the solar system people would call these something else. But I think what we actually are seeing is simply a evolution of the grain, or whatever it is, of material that is not gas and goes from the star into the ISM and then into planet forming disk.
Okay. But the stellar grains, are those the ones that come from the AGB stars? Is that what you mean? Stellar grains, you use the word stellar grains.
Well, I tried to make the difference between a stellar grain and an ISM grain.
And what is it?
Well, I would say an ISM grain might be a grain, a material that has grown on a stellar grain, possibly.
But then the stellar grains are the grains that are left from the AGB star. Is that what you mean?
Yes.
Ah, yeah, okay.
I think, yeah. Okay. But this is, I mean, this relates to my question before, whether the grains we see in the solar system are still unchanged from the AGB.
Yeah, because in the ISM, the grains are already kind of fluffy and fractal, but the AGB grains, AGB star grains, they are just seeds and round and whatnot.
Yeah, but as I understand, yeah, indeed. And what I understand though is that whatever you want to create in the ISM will depend on what your AGB seed looks like.
We have also a question line afterwards.
Yeah, quickly, Xavier Bois from ESO Chile. I didn't quite get why you went to iron mantle straight away. Is there any other metal you could try, or have you tried?
No, I mean, yes, sorry. No and yes, and that's, no, so first I tried the clear grains, and those got I hope that would solve my problem, but they got way too cold. So I needed something to make them warmer. And I just went to iron as my first step. Why? Because people talk about iron inclusions in grains, and they talk about that the grains get too warm to form, so I figured that might heat up my grain. So I tried this, and it worked. It actually worked beautifully. And so then the next step, I thought, like, okay, maybe I should try something else as well. And then I tried carbon, and that seemed to be too much. And then the conference came. So I had to I had to stop, but so this is the stuff that I would really, really appreciate during the rest of the week, and suggestions of what other things I could try, and reasonably try, because the options seem endless to me, but yeah.
Yeah, we have a question online by Peter Shikluna. He says, first, great talk, Matthias. And I'm curious if you explore different approaches to solve the grain properties for the layered composite particles.
Sorry, what was that last bit?
Did you explore different approaches to solve the grain properties for the layered composite particles?
No. But I think we should. I think some of the next steps, for example, would be to look at spectra. I mean, I'm looking at 70 micron and 160 micron, which are just 2 points. And I think there's probably a lot more information to get. So we should use different approaches.
We have time for one last question.
Thanks for the interesting talk, Matthias. Marie van Zande, Leiden. Do you already need to have the iron spickling? Does it only happen in the dust shell, or is it also closer by the star?
I don't know.
Because I took a look at my chemical model, and because I did include some iron for and it does accrete onto the dust, but only further from the star. So then you can accrete iron onto dust grains, and also magnesium and sodium, which was included in the model as well.
So generally, people tell me that nothing can happen to the dust grain after it's formed because the densities get way too low and stuff like this. So based on that, I would think it would have to get speckled relatively early on in the inner envelope.
Well, depends on your outflow of density, but it happens at around 10 to the 16 centimeters. So just FYI.
Yeah, that would be really good.
Okay, thank you very much. I think we need to leave the questions here. So thank you very much.
Also.
And now we have one last talk by Hans Olofsson on the mass loss rate characteristics on the upper AGB and slightly beyond. The floor is yours.
Okay, thank you. So this is a project that involves quite a number of colleagues that are here at this conference. And now I have to learn how this works. No? So how does it work? What do I press? No, now I pressed everything. Huh?
Point it at the TV, above the TV.
Well, that's good. Nah. No, okay. But can I get it in full screen? I can continue talking. So it concerns putting constraints on how the mass loss depends on initial properties, present characteristics, how it evolves with time, and how morphology changes possibly. Now that's a heavy task, so we concentrate here really on the latter two. And now I wonder which one I should press again. Please inform me.
Matthias, can you put it again in full screen, please?
Yeah, okay. So while I'm working on that, so the sample. Sorry. Yeah, it's late in the day. I mean, really, and I'm an old man. I mean, you have to live with it. So the sample consists of 77 OHIR stars within 3 degrees of the galactic center. We believe the sample is narrow in mass, and these are lower mass stars, age about 4 to 7 gigayears old. They are essentially equidistant, and they're all in the high mass loss rate phase on the AGB. And this is just to show the the OH 1612 megahertz flux density distribution and to see where you find, so this is, and how do I point with this one or? Yeah, okay. So this is the OH flux density distribution and of our sample. I've just indicated where two well-known OH IR stars would be located. So W Piscis, that was discussed earlier today, and OH 26.5, if they were scaled to the galactic center distance. So we observed all these objects with ALMA, 3 12CO lines, 2 13CO lines, 1 C18O line, and also continuum. And the detection rate is very high, especially in 12CO and 13CO. We detect essentially everything. And then we looked at the possible classification of the sources, and we based this on the SED characteristics, the CO line characteristics, and the variability characteristics. And when we look at the SED characteristics, the stars divide up in 2 distinct groups. 48 of them can be well fitted using a standard dust envelope with a relatively small inner radius, while 26 of them require an envelope that is detached from the central star. And when we looked at the CO line characteristic, we find that 57 of the objects have centrally peaked brightness distribution and AGB-like line profiles, while 17 of the objects have extended, often complex brightness distribution, or they have non-AGB-like line profiles with line wings and so on. And when we looked at the variability, we found that there are close to 40 sources that are large amplitude and regular variability sources, while there are 33 that are low amplitude and show no regular variability. And if we add this all together, we find 4 classes based on this. And we have the A sources, which we believe are on the upper AGB, 50% of the sample. The B sources, which have just reached the tip of the AGB, stopped pulsating, and these are 10% of the sources. The C sources have just left the AGB, and 10% of the sources fall in this class. And then we have the D sources, which are well into the post-AGB evolution, and those are about 20% of the objects. So some quantitative results then. We first looked at the SCDs and the variability, and we did this for all classes. And the results is the following. We have the luminosity distribution of the objects, and they don't differ. The classes all have essentially the same luminosity, and it suggests that the mass is low, about 1.4 solar masses. And then we have the period distribution for the class A sources. Those are the only ones pulsating, and they have relatively long periods. And then we derive the dust mass loss rates through modeling the SED. And here we can see a clear difference between the different sources, so that the mass loss, the dust mass loss rate goes up by a factor of 20 when going from class A to class D. And we also get an idea of the characteristic timescales here from the inner radii of the dust envelopes. And for the C sources that have just left the AGB, the timescale is about 150 years. But the D sources that are into the post-AGB, the timescale is about 500 years. And then we looked at the CO data, and we analyzed here only so far the A, B, and C objects, because for them we can use a traditional model for modeling the CO lines. And starting with the observational input, this is how the brightness distributions look for the AGB-like objects. They are all very similar. And what we've done is that we extracted line profiles by convolving these data with 3 different Gaussians 0.5 arcsecond, 1 arcsecond, 2 arcsecond, and 3 arcsecond, full width of half maximum. And this is the input data that we have. So we can have up to 20 data points per object. And this is just to show you how it looks. These are the extracted line profile for an object. Yeah. And the conclusion we get from this when we look at it is that the data set is very homogeneous, implying very similar circumstellar structure for the class A, B, and C objects. Of course, with the caveat that this is within the CO line emitting region, this conclusion. And this is just to show you the homogeneity of it. And I've taken an example where I've calculated intensity ratios between different apertures, so to speak, or Gaussians. And the thing to take home from here is that the scatter around the mean for all these data points for the different lines and the two different species, the scatter is very low, less than 10% really, compared to the average. And this is another example, the line shape. And I've used the class formula to fit the lines, and they are all very well fit by a soft parabola as we expected. And because you see, so H is the shape parameter, and the spread around the average here is also relatively low. So then we come to the radiator transfer analysis, and of course we have to put in a circumstellar model for this, and we really take a standard circumstellar model. So we assume a constant mass loss rate, constant expansion velocity. We put in a kinetic temperature law. We have an infrared radiation field. We assume an abundance of 12 CO. And then we take CO photo dissociation from the work of Saberi. And so then the only free parameter for the 12 CO modeling is the gas mass loss rate. And for 13 CO, the only free parameter is the 13 CO abundance. And once again, we can conclude here that the circumstellar model actually results in very good fits for all the data. And I exemplify it here. These are all the data points that we have. So in 4 apertures, in 3 different lines for 12 CO, 2 different lines for 13 CO. And it's the model divided by the observational result. And you see the average is very close to 1, and the scatter is less than 15% around the median, around the average. And this is to show you the radial brightness distributions that we have in 3 mass loss rate bins. And this is an absolute scale, so it's not normalized. And you see the fit, which is from the model, which is the red data points here. And it really fits very well. And the only thing is that for the 1 to 0 line, at very high mass loss rate, we start to lose flux. So then the results, these are the gas mass loss rates. And you see the median is about 2 times 10 to the minus 4 solar masses per year. So these are really high mass loss rate objects. And there is no difference between the A, B, and C classes. And I reproduced here to the right the dust mass loss rates that we derived. And if we convert that then into gas to dust ratios, it will have an influence, of course, so that if you look at the Class A sources, which we believe are on the upper AGB, we get a reasonable gas to dust ratio. But for the others, we get, I would say, an unreasonably low gas to dust ratio. And the reason for that is that the change in mass loss rate that's occurring, we cannot yet see in the low J CO lines that we have observed. It's only seen in the dust. This is the kinematics, so they have relatively high gas expansion velocity, a median of 15 kilometers per second. And another interesting result is that when we derive the circumstellar 12 CO to 13 CO abundance ratio from the radiated transfer modeling, which we think is a good estimator of the 12C, 13C ratio, we get a really good low value. 4.3 is the median, and you can see essentially all of them lies below 10. All right, so if we now believe that there is a chronological relation between these classes from A, B to C to D, we find the following timescale, that the A class spend about 2,500 years on the upper AGB when the mass loss rate is higher than 5 times 10 to the minus 6. The B class spent about 500 years at the tip of the AGB. The C class about 500 years just beyond the tip of the AGB. And then we have a time scale of about 1,000 years for the post-AGB objects. And then finally, an interesting thing that we've found when we looked at our data, and that is that about 20% of the objects have relatively large circumstellar structures around them. And we think that these structures are due to CSM-ISM interaction. You can see some of them clearly have something that look like bow shocks. And I believe this is a phenomenon that's not been seen in CO before. And we think it's due to the fact that these objects move with very high velocities, many of them. The systemic velocity stretch from less than minus 300 kilometers per second to plus 300 kilometers per second. And they move in a medium which is probably much denser than the medium in the solar neighborhood. There is one problem here, and that is if you do not observe these objects with sufficiently high angular resolution, and you instead add up everything you see here, you're really in problem, because it turns out that the emission from the interaction region is about 10 times stronger than the CSM interaction is. So if you're not able to discriminate the proper emission from the circumstellar envelope, you will draw completely incorrect conclusions about mass loss rates and so on. So that lead me to the conclusion. So it's a sample of lower mass stars on the upper AGB and beyond. We can divide them into 4 classes, and we find that the CO line characteristics are very homogeneous through the classes A, B to C. And the standard circumstellar model fits the data very well. The mass loss rate, the dust mass loss rate increased by a factor of 20 from class A to class D. This is not something that's seen in the CO data, because there we derive the same gas mass loss rate for objects for classes A, B to C. And we derive a 12C, 13C ratio of about 4 for the classes A, B, and C. And we find complex circumstellar structure that is emerging in the class D sources. I didn't show you any more examples, but there's some beautiful brightness distribution for some of these sources. And then finally, we find this evidence of circumstellar interstellar interaction in also CO lines, something that's been seen in dust before with Herschel data. So thank you. Sorry about the hassle.
Thank you very much for the nice talk and the impressive data set. I think this kind of work is really needed, especially if you're interested in the transition to the post-EGB phase.
Yeah.
So, well, are there any questions?
Hi, Hans-Me. You have given us at one of the last slides some lifetimes of different classes.
Yeah.
How have these lifetimes been derived? And secondly, they're really short, 500 to 1,000 years. Is it compliant with statistics to have so many stars being detectable within such a short lifetime?
Yeah. So this is something that we're working on for the moment. So I probably shouldn't say too much about this. I mean, we're trying to do this in a proper way now. The way I've essentially done this is that I estimated a kind of dynamical time scale for the class D objects. And then just seeing how many sources I have in the different classes, I came up with something like this. But we are testing now to see really, you know, applying a star formation history, the time the stars evolve on the up to the AGB and so on, and see whether we could actually fit this well for a reasonable star formation rate and so on.
And also a reasonable sample, since you have a large sample of stars detected in such a short lifetime.
Yeah.
Which is amazing.
Yeah, absolutely.
Ramlal?
Hi, Ramlal from Chalmers. So you said we use the same R half for 12CO and 13CO, right? In the additive transfer module. Is the difference due to self-shielding or stuff like that negligible at these densities? Like how valid?
I discussed a lot with Mariam Saberi, who made the photo dissociation models about this. And she said for the high mass loss rate sources, you could use the same photo dissociation radius. In the end, it doesn't really matter because the lines are not excited all the way out to the photo dissociation radius. So you could let that float around a little bit without changing the result at all. So it has no major influence, I would say. I mean, the only reasonable thing to do would maybe be to make the 13CO envelopes a little bit smaller because they're not as good self-shielding. But then you get an even lower 12C, 13C ratio because you have to raise the 13CO abundance to compensate for that. So.
Hans Seneca. Hello, Hans.
Hello.
Another Hans.
Yeah.
So you mentioned the median mass loss rate of 2 times 10 to the minus 5.
Yeah.
But median implies some variation.
Mm-hmm.
And so I guess I didn't quite catch what the range of variation is.
Mm-hmm. Okay, so I would say the far majority of our stars lies between 5 times 10 to the minus 6 to 5 times 10 to the minus 5. So an order of magnitude spread in the mass loss rates.
Franz Kerschbaum, Vienna. Dynamically, how far away is this interaction zone with the ISM?
Yeah.
I did not see the scales, therefore.
No, I'll see if I have the scales here.
Yeah.
Yeah. So these are 6 times. These are 6 times 6 arc seconds, and 1 arc second is 8,200 AU.
Oh.
And then you can calculate.
So out there is obviously some CO left, so this is not photo-dissociated there.
No, apparently not. Yeah.
Obviously, yeah.
Yeah, it's
quite far away.
It's an interstellar molecular medium. That's
yeah.
There. Yeah.
I do have a question as well. For the post-AGB objects, do you find for any of those indications of fast ejections, or are they just expanding slowly as AGBs?
No, absolutely not. I mean, at least half of them have line wings. Not any sort of extreme line wings, but yeah. So you see here down to the right. So that's a typically non-AGB like line profile where you have line wings. Not as I said, not extreme line wings, but so there is a center AGB like line profile, and then the line wings come up.
And the fast outflows are bipolar, you would say? I mean, like in this case?
Yeah.
And they are resolved? Can you estimate the kinematic age of these fast outflows?
Yeah.
And how is it compared with the time since they left the AGB phase?
Yeah, so this is essentially where I get that time scale from, about 1,000 years.
Okay. But from the inner radius of the dust, you said
Yeah, that's they are comparable. So, I mean, we have to look at this a little bit more in detail. For the moment, we focused on the class A, B, and C objects because there we could do a standard radiative transfer modeling of the whole thing. And for the class D objects, which are clearly different, we will have to analyze them in a different way. So, but the time scale is roughly around 1,000 years for these, give or take a factor of 2 in either direction.
Okay, thank you very much. I think we'll probably need to close the discussion here, right? Because I think we have also a poster. Okay, so then let's thank Hans again.
Okay, so let's move to the last session of today. I'm Aga Corporaal and I am going to chair this session on behalf of the LOC. So the next poster session will be basically the same as from yesterday. So I'll call your name and the slide will be brought up and you have 2 minutes to present your poster. So the first up is Miriam. Either, please open your mic.
Okay, thank you. Okay, that's my poster. Well, this is about thank you. This is about a planetary nebula in the Large Magellanic Cloud. The spectrum that is, can you put it up? Showing the spectrum? No? Can you put it smaller or something? We are not seeing the whole thing.
Can you unzoom a little bit? Because
Okay, that's it. Well, oops, not that small. Not that small. Up. Okay. There you see the spectrum of the planetary nebulae. To the right, up, it was a normal planetary nebulae, highly excited. And in 1994, it suffered a Wolf-Rayet event. The central star developed a very interesting wind showing a spectrum of a Wolf-Rayet star of nitrogen, which is very strange. We follow the evolution of this event. You can see in the figure up to the left, the evolution in the ultraviolet spectrum. You can see that the star got much brighter, 4 magnitudes, and then it became going down slowly. We follow this event and we built a non-LTE atmosphere models. Then we could derive the stellar parameters. You can see in the low part to the left, the evolution or the differences between the stellar parameters. The luminosity grows from 5.4 in log to 4.6. In this event, the stellar temperature was all the time a little higher than 1,000 kilokelvin. The radius of the star grows from half solar radius to 1.5 solar radium, and there was a mass loss calculated. The interesting thing is the abundances of the star. It was practically a helium star. And then the star was going down slowly. 30 years later, 2024, this object was observed with the local volume mapper, and the spectrum this time is shown in this figure 3. And you can see that there is no star anymore. The stellar wind has disappeared, and we are seeing the nebular spectrum very similar to the one in 1988. Very high excited nebula. So,
okay, thank you.
That's it.
Thanks. Next, Mark.
All right. Hi, everybody. I'm Mark Siebert. I'm a postdoc at Chalmers, and my poster this week is on this very unique and surprising red supergiant star that we found in some ALMA data we were looking at. So for some context, this was part of a larger program to observe this cluster called Stevenson 2 or RSGC2. And we observed 13 of the some 26 or more supergiants in this cluster to get their mass loss properties, to get a better handle on how red supergiant mass loss occurs. And we didn't expect to see much in terms of spatially extended objects in this cluster because it's at about 5 kiloparsecs or 6 kiloparsecs, and our beam was about 0.5 arc seconds. So we were really only tracing scales of several thousands of AU. And then this source, DFK52, looks like that. And it shows this extremely extended and complex wind, both in its CO emission and also really surprisingly in its continuum emission as well. And that little blue blob in the bottom right corner is the wind of VY Canis Majoris on similar physical scales. So this thing really dwarfs already one of our most extreme objects that we know about. And the luminosity of DFK52 is about 10 times lower. So we're really, this thing is unlike anything we've seen before. We don't really know how this kind of ejection sort of happened, but we think it was maybe some kind of binary interaction and all this detached material was thrown out. And based on some kinematic modeling we did, we think that this happened about 4,000 years ago. So if you want to learn more, come and talk to me on my poster, and happy to talk more about it.
Thank you. Next up, Heather.
Thank you. Hi, everyone. I'm Heather. I am from the University of Canterbury in New Zealand, and I am 3 months into my PhD. So I am interested in globular clusters using the Gaia ESO survey data to look at their abundances. And in particular, I am looking at the magnesium-aluminium anticorrelation. So it's observed only in the metal poor and massive clusters. And so it is thought that AGB stars could be key polluters for causing especially the aluminium enrichment. So there are 2 main anticorrelations, magnesium, aluminium, and sodium and oxygen. Sodium and oxygen is seen through all of the clusters that I have, but magnesium, aluminium is not. So I have sort of 2 parts of my poster. One is on the current AGB versus current RGB abundances and seeing any differences between those, but then also tracing previous generations of AGB stars and their influence in the what we now observe abundances. So sort of a past and present look and seeing, do we find other abundances that can tell us about the masses and the properties about these previous AGB generations that have polluted the clusters. So if you would like to talk about the influence of AGB in globular clusters, I would be happy to chat. Thank you.
Thank you. Next up, Laurent.
Hello, my name is Laurent Schauermann from the National Radio Observatory in Socorro, New Mexico. I'm here to present the bulge asymmetries and dynamical evolution survey. We have used the infrared color to select circumstellar envelopes that are likely to have SIO masers. We have thousands of sources towards the bulge. Many transitions can be observed at 43 gigahertz and 86 gigahertz with VLA and ALMA respectively. We used less than 1 minute per source, so that's really efficient. We used the line of sight velocities for galactic dynamics. We have a detection rate of well over 70%, meaning more than 15,000 stars. They're all oxygen-rich AGB stars. We use the spectra for pumping models and maybe also define what type of AGB star it is. For the distances, we use multiple standard candle spectral energy distributions. I can tell you all about that at my poster. We subdivide the shapes of the spectral energy distributions depending on the pulsation period or metallicity. We yield distances for the distances we yield give us stellar properties like luminosities and all those kind of things. We used all these stars with the distances and populations for determining the structure of our galaxy and how it's distributed there. Next slide, please. Here I show you some of the results that we have. Upper right is a typical spectra that we see. It's very nice. Upper left, some of the velocities we obtain and the modeling we do with that. Below that, we show that our distances are very comparable to other people's distances, but we can get further out. So, for example, on the lower right, you see that we actually get our stars into the bulge. Thank you.
Thank you. Sundar should be online, so please unmute yourself.
Hi, can you hear me?
Yes.
Okay. Hi, everyone. This poster is about a utility that we've been working on to enable Bayesian fitting of SEDs or spectra using neural networks that are trained on your existing grid of model SEDs or spectras. It is one solution to the problem with model grids that end up having unsatisfactory coverage in some parameters or perhaps non-linear parameter dependencies. We've already tested it on AGB SEDs, and there's a sample fit there. If you're more interested in talking about this, it is relatively flexible and can be applied to, it doesn't care about the physics. As long as you have a model grid of some sort, you can use this to compute Bayesian fits. So please come and talk to me. I'm poster 23, and I'll be very happy to talk to you. Thank you.
Thank you. Gabriel.
Hi everyone, so I'm Gabriel Tomasini, second year PhD at OCA in Nice. And so I think that the slide is speaking for itself, but the poster is about probing the impact of binarity in AGB atmosphere using cobalt. So what we did is to change the potential cobalt from a single neutron potential to a binary potential with a centrifugal term. Next slide, please. And so this is work in progress, but what we did is basically use the same methodology as AMAT 2025, and we discovered two different frequencies at two different locations in the box, and with two different responses to the companion mass. So for the first one, it's located at the stellar radius, and we observe frequency broadening. So it's the bottom right plot, which is not observed on the second one. And so the second frequency is located more on the ejected mass, and we observe so not a frequency broadening, but a shift on the energy location in the box. So if you want to know more about this poster, come to see me at poster 24. Thank you.
Thank you. Next up, Alfonso.
Good afternoon, everyone. My name is Alfonso Trejo from the Institute of Radio Astronomy and Astrophysics from UNAM in Mexico. And this work is part of the Nearby Ball Star Survey project which covers various aspects, but essentially mass loss in gas in nearby AGB stars. So we focus on a sample of nearly 280 AGB stars within 2 kiloparsecs from the sun. So all these are bettered AGB stars, essentially confirmed through various methods. And we want to cover those production rates that are above 10 to the minus 10 solar masses per year. And so, as you can imagine, many of the stars don't have detections. So the little table on the left shows you the detection rate. Essentially goes up to 40% or something at 12 CO 3 to 2 transition, and a little bit less in 2 to 1. And the box plot over there centers around 10 to the minus 10 for the shell size. So this is essentially all the distances per star, and then you transform that into AU. So that is roughly 10 to the minus 10. So we are able to derive the ratio between the shell sizes, essentially all the combinations from the 4 lines we have is 12 and 13 CO 3 to 2 and 2 to 1. And then some correlations are as expected. For example, 2 to 1 to 3 to 2 is roughly 1.5 times the ratio for the shell sizes. And the plot on the right essentially is the subsample with all the combinations of lines. And also the most populated one is, again, the 12, 3 to 2 and 2 to 1. And then so we are able to draw some reasonable fits. And anyway, this is work in preparation in a draft. And essentially, we're wrapping this project. So if you're interested, this is poster 25. Thank you.
Thank you, Alan. Alan?
Hi, I'm Alan Whittington from the University of Texas at San Antonio, and part of the team that Angela Sargent presented earlier. My lab is the hamster lab up there, the heat and mass transfer and experimental rheology lab, a very tortured acronym. Anyway, we've been playing around with alumina, torturing alumina actually. So we've been taking various hydrous alumina phases, minerals like gibbsite, barite, boehmite, and some amorphous aluminum hydroxide, heating it up to different temperatures. The top left graph shows that goes through a series of phase transitions, ending up always at corundum on the right and the blue at the highest temperatures. Always goes through this intermediate eta phase, and then it can go through some other ones as well. We've been studying the kinetics of the transition by heating for different durations. And then my favorite thing is the thermodynamics of the transition. So on the right, those are not spectra, those are calorimetry graphs showing the apparent heat capacity as we heat the samples up. Peaks means that there is an endothermic reaction, usually water leaving. Troughs means that there is an exothermic reaction, usually crystallization. And as Angela mentioned earlier, if that happens very quickly, it can actually heat the sample up spontaneously. And on the bottom right, we have the chaotic smoke samples made by Joe Knuth at NASA Goddard, which are the closest things to, I think, the likely real structures of stardust. Very fluffy things, and we can talk about them if you want to stop by the poster. Thank you.
Thank you. Next up is Katan.
So hello, I'm Katat Wong from Uppsala University in Sweden. So in the poster, I'm presenting some imaging results of a system of highly excited exchange lasers in carbon-rich stars. And these lasers come from image in the far infrared regime. They are just essentially the same phenomenon as masers in the millimeter and microwave wavelengths. And on the slide, I show two examples of spectra from ACA observations. And on the poster, I show more images from the main array data of ALMA. And on the poster, I demonstrated how self-calibration was able to improve the dynamic range and of the images. And also thanks to the broad bandwidth offered by the double sideband setup of ALMA band 10, we are able to cover large several HCN transitions in multiple vibrational states from the ground states up to V equals 2, tracing different excitation energy levels. And so on the poster, I have showed some more images and maps. And the poster is mainly about observational results, but we do have some ideas or speculations on the pumping mechanism. And if you're interested, feel free to talk to me. Thank you.
Thank you, Claire.
Thank you. Hello, everyone. I'm Claire Worley from the University of Canterbury in New Zealand. So my poster is looking at finding the signatures of polluters in the disk sample of the Milky Way galaxy using the Gaia-ESO data release, which has a whole lot of abundances in it, but for this particular poster, I just wanted to look at the elements that are indicative of AGB pollution and using the high resolution sample. So the first figure there, the first panel there just shows the mean and standard deviation of the element abundances for this sample, so you get an idea of what their distribution is. And then we were using principal component analysis to try to extract the dominant chemical signatures in the sample. So that's what the 4 remaining panels are. So sort of a look at this. The most dominant signature appears to be from core collapse supernova because everything's enhanced, or there's contributions from all the elements. The second panel or second signature may be more indicative of type 1a supernova because the lighter elements are enhanced as opposed to the heavier elements. And then it gets more interesting or more complicated for the next 2 signatures. So for the third signature, so the little purple one there is carbon, so enhancement and relative enhancement in carbon, and then some enhancement in S process, so maybe low mass AGB. Though there's something interesting happening with the heavy S, so something else going on there as well. And then the fourth signature, we've got sodium as the tall brown bar, so maybe more indicative of intermediate mass AGB. Though the S process, so the heavier elements down the end are sort of alternating, so not sure what's going on there. Happy to have discussions about that if anyone's got some ideas. Yeah, poster 28, thank you.
Thank you. Miguel, we should be online.
Can you hear me?
Yes.
Yeah. Thank you, Your Honor. The case here is simple. Can I have the next slide, please? So we have a plaintiff, pi1 group B, a suspect, pi1 group A. You have the characteristics here. Please, next slide. We have some evidence. First, we see a third body in the system, here seen with ALMA. We know that celestial body can cause attraction and sometimes motion. And indeed, we observe the motion of pi1 group A, measured by Hipparcos and Gaia. And we see also gas motion in a Keplerian way around the system. Next slide, please. So the conclusion is simple. Pi1 group A is having a secret relationship with a third body in the system, pi1 group C, and it is a main sequence star or a white dwarf, and we have these orbital properties. And this star is stealing material. So I repeat, you are now stealing material from the environment of the system. Unfortunately, the case is incomplete, and we need more data to properly identify the star and its trajectory. But you will hear more about this case later in the conference this week, and I thank you, Your Honor, for your attention.
I'm a science advisor.
Sorry.
Okay. Well, um, why high energy astrophysics? And this is why I'm coming here to learn a little. Of low mass X-ray binary that is a V star in a very late stage of evolution. I think is becoming very close to be a white dwarf. And there in that system, we detected with a VLA an ejection event that that took about 2 months, and where in this simulation that I had here, it was observed relativistic phenomena that were produced by jets that are well explained by general relativity. Now, in the year until for the last 30 years, this source has shown usual changes in the direction of the jets up to 5 degrees approximately, which are very well explained by general relativistic effects. But in the year 2023, we detected a very unusual change in the direction of the jets of 30 degrees that we reported in April of 2024 in APG. And here is shown the ejection. And this is a very powerful ejection. It's equivalent to the kinetic energy that will have the moon moving at 98% the speed of light. So it's enormous. And the second very powerful source also is fed by an AGB, which is a source, a black hole binary system called Cygnus. Well, that doesn't matter. So why is this is also important for cosmology? You know, black holes grow in the early universe at super Eddington rates. And we can understand very well the super Eddington mechanism from the studies of microquasars in our galaxy. And one of the surprising results is the discovery of what are called little red dots, namely black holes that we believe are intermediate mass black holes growing very fast at super Eddington rates. And they cannot see in the X-rays these sources as the microquasar I showed, but neither in the radio waves. And this is a mystery, how if there are black holes there growing like hell, do not produce this indication of radio jets. And Well, and we are working now, submitting next week an article to Astronomy and Astrophysics where we can explain why radio waves cannot get out from these little red dots. That is one of the most important discoveries in the James Webb Telescope. Well, I think this is an idea that not only for galaxies, but also for understanding how are produced the super Eddington phenomena of accretion that are related to the production of relativistic jets in the universe. Using microquasars, you can understand this. So microquasars are very good for impatient people. And the reason is
like that. That's
everything takes time in very rapidly. You don't have to wait millions of years, as in the case of the AGNs, to see their evolution. Thank you.
Okay, thanks a lot. So this ends this session, and I think there's still some announcements by Claudia, so please go ahead.
Yes, first, a big applause to all the speakers and also the chairs of today. So I have 3 announcements. The first one is, since we care about sustainability and we don't want to waste food, please, if you're not coming for lunch, let us know at least the evening before, because, well, that's why, because we don't want to waste food. Then remember to send us questions for tomorrow. So we have a discussion tomorrow. It will include all the talks between Monday and tomorrow. So we created a Slack channel. You can send me an email, any thought, anything that you want to follow up and discuss. We will have 45 minutes, so there is plenty of time, and we have a very beautiful setup to chat. So please remember this. Otherwise, I will have to invent some questions. And no, well, thank you. And last, but not least, tomorrow, the coffee break in the morning, we will take the conference picture. We don't have a lot of people. Well, yeah, Julian is good with Photoshop, but we would prefer to have you in person. So please come. And that's all from my side. Have a good evening.